tech changes while we wait for his presentation.
All right. Well, thank you very much for the opportunity to speak here today at a late-breaking session. I'll be presenting a result from CHIME on the radio brightest flash of all time, which is CHIME speak for the highest signal-to-noise ratio FRB that we've ever detected. So before I kick off, this work was kind of collaboration work in the truest sense of the word. We were drawing on expertise from all corners of the kind of CHIME collaboration. And all this work was kind of synthesized together heroically by Amanda, who led the effort to turn this into a great science paper. Thanks for that. Great. And so this burst, which we've kind of affectionately titled RB Float for the Canadian affinity for root beer, especially for some people at the top. Amanda and Jason, I'm looking at you. And so this burst is interesting because it's extraordinarily bright in the data. So that gives us a high precision. So the first kind of word that went out about this burst was in Natal by Mason, where basically we had detected this largely very high fluence burst towards a galaxy that was only 40 megaparsecs away. So this puts the burst at an energy that is kind of not atypical for the FRB population, but because the burst is so close to us, it gives us a really high fluence. Now that in and of itself is not unheard of in the literature. Certainly there are publications of side lobe FRB detections in CHIME that have kind of similarly high fluences. But what makes this burst special and kind of different from those cases is that it was detected at near maximum sensitivity in the CHIME telescope. And so what we can see here is a function of CHIME's primary beam and synthesized beam sensitivity as a function of declination. And the white line kind of shows us here at 60 degrees that the burst was detected at near optimum kind of sensitivity. Then in the axis that's collapsed here for right ascension, we formed several synthesized beams across the sky in that direction. And this X marks the spot. So this burst was detected within the full width half maximum of one of those, putting it really at kind of the highest sensitivity that we can achieve. This means that our high fluence burst converts to a very high signal to noise ratio signal. And that's great for a lot of different science, including kind of Outrigger localizations. So coincidentally, this burst also is the first localization with each of the Outrigger instruments, which, as a reminder, kind of ascend in baseline length from CHIME to KKO, then HCO, and finally GBO on 3,300 kilometer baseline. So each of these CHIME Outriggers is kind of like a 1/8, or in the case of KKO, I think even smaller, version of the array that lets us perform higher precision localizations. In this case, the high sensitivity or the high signal to noise ratio of this burst allows it to be localized to several tens of milliarc seconds, which at the very nearby host galaxy gives us a projected localization of 11 by 13 parsecs in actual distance. Now that's awesome because it allows us to really investigate the kind of the circumsource medium and say something about the progenitors that we might expect for a burst like this. So what do we find? So if we do dive into some of the spectral information that was retrieved from Keck, the Cosmic Web Imager, we see that in H-alpha and in O2 that the burst kind of is on the outskirts of a high intensity line emission region. If we kind of take spectra on that star-forming clump and at the FRB localization, and then we kind of perform some line ratio testing, we can see that the spectral lines that we get there are consistent with being on this like star-forming path of the field galaxies that are kind of in the region. And so we think that this is an indication that basically the FRB is on the outskirts of a star formation region at a separation of about 190 parsecs in projected space. Similarly, the H-alpha emission measure at this localization kind of gives us some estimation of the DM that the burst accrues as it passes through, or well, if it passes through this H-alpha region. That kind of implies that it gets like 60 to 110 parsecs of its DM, which is only 160 total, which implies itself that the burst is kind of at a depth of between 10 and 50 parsecs through this region, if indeed it is background to that clump. Similarly, there was JWST follow-up of this localization. And so we kind of coordinated an effort, which was mostly led by Wenfei, to kind of cooperate with these people and publish a companion paper with Peter Blanchard to make a great interpretation that combined this JWST data with the localization that we had. So they identify a couple of different near-infrared counterparts that are near to the localization, naming them NIR 1 through 5. And they kind of go into depth on what the NIR1 could be, which is this faint globule here within the 1 sigma localization region. They say basically it could be a red giant or a massive main sequence star that is at the location, and that could be in a binary with a compact object producing your FRB, and it could be, undergoing common envelope phase or Roche lobe overflow. And similarly, a dust echo, it could explain the emission at this region. So they're going to do follow-up later to see if a transient nature can be ruled out. The things that they rule out at this location include kind of young star clusters and globular clusters, pulsar wind nebula, and supernova remnants, and similarly an isolated magnetar. Some of these are like not bright enough to explain the emission that is seen at this region. They do make a point of noting, though, that the young stellar population kind of in the general vicinity of the localization means that if it's not an IR1, there's a pretty good chance that this burst is associated with core collapse supernova from it's the remnant that comes from that process. So moving on from the localizations, we also can do great morphology study with a high signal to noise signal. And so we do some scintillation and a scattering analysis, measuring kind of a scintillation bandwidth of about 14 kilohertz and a scattering time of about 0.4 milliseconds. As we've seen in a few other talks this week, you can use this to form kind of 2 screen constraints on where you expect an extragalactic and galactic screen to be. If we do something similar and we estimate a galactic screen from NE 2001, this gives us some constraint on where the extragalactic screen can be, and it has to be within about 60 parsecs of the FRB location. If that FRB location is then backgrounds to this H alpha region, and that H alpha region is causing the scattering, it kind of means that our FRB has to be localized very close to that star-forming clump in 3 dimensions. Similarly, with polarization, we see some stuff for the first time in FRBs, including this known effect in pulsars. That's the flattening of the polarization position angle as you average out over scattering. Underlying that averaging, we see that it's kind of got a larger swing than most non-repeating FRBs. And similarly, the galaxy RM is consistent with 0, although with a wide error bar, which makes it the lowest of any polarized non-repeater. So that's the things that we find, but what do we not find? Because that can be just as important. Well, in supernova studies of this galaxy kind of go back a long way, or at least the optical data to look for those transient events. And so we end up with pre-burst data about 20 years on this galaxy that shows that there's no kind of optical emission consistent with a supernova at that location, ruling that out for that period. And I believe this is the longest baseline of optical data pre an FRB, which is exciting. Similarly, we don't see any compact persistent radio emission at this location at a number of different frequencies. So I think this is at 4.9 gigahertz with the HSA and then 9.9 gigahertz with the VLA, placing the kind of deepest limits on non-repeating source using radio follow-up that rules out a nebula 10 times brighter than the crowd. Similarly, we don't see any X-ray emission here, although there was kind of an initial reaction that there was an Einstein probe transient similar to that location. Subsequent Chandra data rules out that as being coincident with the Outrigger. But we place kind of upper limits on the maximum X-rays that can be emitted from this location that puts a stopper in it being a bit of a ULX instead. And so that's inconsistent with one of the interpretations from the JWST data. Now to the meaty part of this is that we get good constraints on how repeater-like this FRB can be. So previous to the burst, we have about 265 hours of FRB data, kind of over 6 years of regular monitoring from CHIME. And there was a dedicated campaign following this up with Omar and others that gave us kind of hyperflash data amounting to 210 hours in these kind of different bands shortly after that burst. So as a reminder, the hyperflash is the high cadence kind of monitoring from these telescopes distributed across Europe. And by forming those, you get really sensitive limits on what repeater emission can come from a dedicated kind of line of sight. So if we put all of this together, we can trace out on this curve, kind of as a function of energy, the cumulative rate that we see, given that there are no repeat detections found in subsequent data. And this allows you to trace out basically an energy curve that looks like so. So our data on the right is the kind of actual data that we fit to this point. That was the burst that we observed at this energy. And because no bursts were detected at lower energies, your cumulative rate kind of flattens off quite substantially. Now then, your error bars are covered here in the 3 sigma region. Also plotted here are the observed repeat distributions in energy from other repeating sources. And what we find is that the shape of these increases so much in the number of bursts you see as a function of energy that there's just no way you can fit that distribution, regardless of its absolute rate scaling, into the allowed region for this 3 sigma statistic that we have here. And so this means that basically this is one of the tightest constraints on repeat, like saying something is definitively a non-repeater that we have so far, with some caveats about clustering, given that some of the hyperflash data is quite centered in time. But we're pretty convinced. And so this is analysis that you can do that is empowered specifically by having high sensitivity at that localization, given that it traces through the chime beam, and that the rate required of high energy events to have this detection within the small part of the chime beam that is very high sensitivity has to be large enough to push this cumulative rate out here to make it high. And so that gives us, that's a nice conclusion from the paper. And so with that, I'll kind of leave you with the key takeaways from this that are, for the first time, we have the chime outrigger localization with all 3 of the outriggers giving us a sub-arc second localization. And we also kind of propose that this burst is localized in 3 dimensions with scintillation and a scattering analysis that puts it within 10 to 100 parsecs of the H alpha region that it was found on the outskirts of. We find that it's kind of not consistent with being a repeater and seems to have a fairly clean radio environment with no PRS. And so with that, I'll be happy to take any questions from people. Thank you very much.
Great talk, Mawson. Oh yeah, I'm Lauren Rhodes from McGill. Thanks, Mason. I had a question about the say continuum follow-up. So in terms of both the radio and infrared, are there plans to continue monitoring, see if anything appears, like this infrared counterpart, are they going to keep observing, see if there's anything that changes?
Yeah, so I know that in the infrareds, they have particular plans to follow up later with JWST to investigate this idea that it could be a dust echo. So dust echo, for people that are unaware, is, you have a supernova or something go off or some kind of energetic event that releases a lot of radiation. And at later times, that radiation gets reprocessed by dust into infrared emission, but that can come at a delay to that event. And so that is like some expanding bubble of light that you would see reprocessed into your line of sight. And so you have to look later to see if it goes away because it's some kind of transient event. And so I believe, yeah, the JWST team plans to do that follow-up.
Thank you.
Any more questions?
Hey, Mawson, this is kind of a plant because I'm pictured on some of these slides. But how do you know? How do you constrain the low energy end of the the repetition rate distribution?
Yeah, so this is like part of the analysis that's kind of well empowered. So this line of sight transits through our beam. We're highly sensitive to that particular line of sight, and so we get good limits in that we don't find any other repeating bursts at lower energies. Given that this burst was, I think, in the integrated time detection system has a signal to noise ratio of like, thousands. And so we really could have found follow-up bursts down to a very low level.
And so the fast. And fast could as well.
basket as well. Yeah, I don't know if there's been particular fast follow-up of this line of sight just yet. There has been. I'm seeing nods in the audience, so they also haven't found anything, I expect. Yeah.
Okay, great. If there are no further questions, let's thank Mawson again. And our last late-breaking talk of the morning will be by Dotan on a periodicity search in one particular FRB.
Hello, thank you for letting me tell you about this periodicity search. So first let's get right into it. Yes. So I think we talked a bit throughout the week. Why should we search for periodicity? Just the very clear smoking gun if you consider a magnetar or some neutron star progenitor. Why I tell you about this particular source is that there's been a claimed detection of periodicity in this, and I was initially very excited and then turned to reproduce and kind of want to dispute that. So how do we actually search? So initially we should choose our data, do some cleaning, some pre-processing on it. Then we should define what our actual, what are we searching for? So setting the frequency range, in this case, like 0.1 Hertz to 10 Hertz. Then the frequency spacing is set by the data we consider. Choose the statistic, either something that will tell you whether the bursts that you have when you fold them on for the trial period, whether they line up or are they still scattered around. You can do it with some H statistics, some bind chi-squared. And for the significance estimation, I repeat the message by Daniela that you should, if you can, do Monte Carlo. So I'll focus mainly on 2 points that I think make the difference in my and Du et al.'s analysis. First, the pre-processing, the threshold on the waiting times. So for this particular source at this particular kind of time of observation, this is what the waiting time distribution looks like. And you can clearly see that there is like a long mode and the short mode. And it's dangerous to take the short mode into your analysis as well, while not taking it into account when you estimate the significance. Because when you have those bursts that are very close by, when they travel in your folding, they will naturally just line up, and your statistic will be very much biased by it, and your significance estimation would turn out to be incorrect, to overestimate the significance. Basically, Monte Carlo is how you get those kind of plots and get this observation that you overestimate the significance. Yeah, so to wrap up, we have this source, and it doesn't seem, when you cut the short waiting times, it doesn't seem to have to show periodicity. So we need to be careful about what you take into your periodicity analysis. Thank you.
Any questions?
This is Casey Law from Caltech. I wonder if there's is there sort of a principled way, like a physically principled way of making that selection between the short and long? Or are we just arguing that they're physically different things? That's the point.
That depends on your interpretation, I guess. You could make either a test, whatever you like, but when you estimate the significance, either do it like consider the number of the ones from the short, because it just, if you sample only from the long distribution, you'll estimate your significance wrongly. So if you reject some of them, then sample from the distribution you actually use. Yes.
Sure.
And we'll take one online question before we move to the next person. Yes, you can go ahead and unmute and we'll have the next speaker come down.
Yeah, can you hear me?
He's online.
Hello.
Go ahead, sorry.
Yeah, it's Pranav from Bonn. Thanks for the nice talk. I had similar question on what Casey said is for a pulsar in waiting times, we will see a nice harmonic peak, a nice peak followed with harmonics. So did you also try to test how to sample the waiting time distribution burst, and if you change or decrease the sample of burst or give a varying cut in the waiting time, does that change the significance?
Can you repeat shortly? I didn't catch what do you want to do with the waiting time distribution?
No, so you're talking here about where to give the cut in the waiting time distribution to select the sample to do the periodicity search on. Is it have you also tried if it gets sensitive to how much you vary this cut, and if you select different portions of the cut?
No, I did not. I just saw, I think in this case, it's very clear that you have two separate kind of components in the waiting time distribution. So again, either you choose one of them and sample from it, or now you need to say what are you doing, whether you keep the number of some number of samples from the short distribution or do something else. But anyway, you should do the periodicity search and the significance estimation on the distribution of TOAs that you do sample from.
Okay,
Great.
thanks a lot.
Okay, let's thank our speaker again.
Alex, go ahead and share screen.
Can you see my slides?
Yes.
Great. So this is Alex Cooper, who's going to talk about emission mechanisms. Yeah, so hello everyone. As Zora said, my name is Alex Cooper. I'm working at the University of Oxford. And I'd like to thank the organizers of the conference for inviting me to talk about FRB emission physics, and also for putting on such a great hybrid conference. It sounds like I missed out on the karaoke yesterday, but it's been a great experience online, so I'm very grateful. Before I start, I just want to highlight some of the great talks we've had already on emission physics. So we've had Navin, who gave a great overview about all different types of... Can you hear me, Lauren?
Yeah, it's all fine. I was just we could see your face now.
Great. Who gave a great talk on, I think, probably every different type of emission mechanism and the physics behind that and the predictions. And Kenzie, who gave a nice overview of the observational signatures and how perhaps they might be more naturally explained in many cases by a magnetospheric theory. So before I start, I want to take a bit of a step back and maybe for people that are slightly newer to the field, try and get at the question of why everyone talks about magnetars when we're discussing the progenitors of FRBs. And so we can look at the broad properties of fast radio bursts to try and understand this. So the first and most obvious thing is that fast radio bursts are coherent, very luminous and highly polarized in many cases emission. And what this points to, both from other types of sources that we observe in radio, but also on the theory side, is large and organized magnetic field structures to get at both the coherence and also the polarization properties. The second thing is kind of in the name, fast radio bursts. So we have these relatively short burst of radio emission on the order of, say, milliseconds or shorter, and this points towards a compact emission region. And so we can roughly say that the lateral size of the emission region is constrained by causality. We have a factor of gamma here, which is the Lorentz factor of the emitting particles or the emitting region. And so if we take typical Lorentz factors mentioned in magnetospheric theory, so on the order of hundreds to thousands, we get something like the radius of a neutron star as approximately the emission region. And of course, if you have much higher Lorentz factors, you can have larger emission regions. So we think that we have magnetic fields, we have a relatively compact object. Does it have to be a magnetar, or can it be a normal type of neutron star? And this is where the source energetics play a role. So what I'm showing here is the kind of corrected FRB luminosity, very typical values, and F here is a beaming fraction, and epsilon is some radio efficiency, how much of your energy goes into the radio burst. And what we can do is very roughly write down what the typical spin down luminosity of a neutron star with a given magnetic field and a given period will be, and we can see that there's orders of magnitude difference here. You can play around with these numbers, of course, but it seems like there's just not enough energy in the rotational reservoir to power these sources. And so we think that this is probably driven or powered by the magnetic energy reservoir. The final thing I'd like to point out, and this point was made by George in his talk on magnetar phenomena yesterday, is that we can look towards these galactic magnetars, particularly at high energy, their X-ray bursts, and make links to what we're seeing on the fast radio burst side. So what I'm showing here is two plots on the left for a repeating fast radio burst, and on the right for X-ray burst from a galactic magnetar. And this is the wait time distribution. So if you've just seen a burst, what is the distribution of time you have to wait to see the next one? And both of these are characterized by these log normal distributions, in this case peaking around 100 seconds. In the fast radio burst case, we have higher time resolution. We heard in the last talk about how this lower bump, which is also a log normal, may be some kind of subburst. In magnetars, we're not able to resolve this, but there's hints that there may be this lower wait time bump as well. So there's similarities here, and people have discussed similarities to things like earthquake distributions here on Earth, both in terms of the waiting time, but also things like the energy distribution. So that's a little introduction to fast radio bursts, why we think that magnetars might be their sources. And what we like to do, and we've seen this slide already this conference and beforehand as well, is classify our types of emission models into magnetospheric models on the left, where you have particle acceleration and radio emission from close to the neutron star surface within the light cylinder, and these non-magnetospheric models often invoking shocks and maser-like emission that occurs from relatively far out from the neutron star or some central engine. And we heard from Navin that some of the lines are being blurred between these two different types of models, shock models that might operate slightly closer to the neutron star surface. But I still think this is a useful way to visualize these models in a simplistic manner. So we've heard a lot about some of the observational constraints. Given the talks that are going to come afterwards, I think it's useful to discuss a little bit about some of the multi-wavelength constraints that we have on some of these models. And particularly here, I'm going to focus on these maser shock models because they're very good in the fact that they have a definitive prediction that we can test with observations. So in the kind of basic version of this, and there's many different iterations of these models, you have some central engine. I'm going to assume it's a magnetar for now. And you have some outflow, which is usually ultra-relativistic and highly magnetized. And this outflow bears some resemblances to other types of transients, like gamma ray bursts, for example, but with two key differences. They're much lower in energy, and they're highly magnetized, and so you inhibit some of the non-thermal particle acceleration. But despite that, we still expect there to be these broadband multi-wavelength afterglows, and we can test for this. We can perform follow-up observations. So I mentioned that this is slightly lower energy than something like a GRB, or a lot lower energy than a GRB. So the way that we can test this is with the brightest and most nearby fast radio bursts. And of course, as we've heard earlier in the conference, we had this kind of watershed moment in 2020 with this FRB-like burst from a galactic magnetar. And you can see some of the discovery plots here. Most exciting, I think, was this detection of an X-ray counterpart. So this occurred, as we heard from George, during this just after this extreme burst storm in X-rays. And the one burst that was associated with the FRB had peculiar properties, particularly in terms of the cutoff energy, which you can see on the right here, compared to all of the other bursts in that burst storm. And so within this maser shock framework, this model of FRB emission, this X-ray counterpart could be something like the prompt or early afterglow emission. And what that allows you to do is kind of tie your predictions for other wavelengths to the data that we have for that X-ray counterpart. And so the first thing we did was in a paper in 2022, go after it in radio. Unfortunately, we were too late to be able to detect the predicted emission, as you can see on the right here across various frequencies. But there was a very fortunate optical upper limit presented in another paper by the Booch 3 telescope. And so the orange line in this plot is an upper limit, time dependent for the duration of the observation, and the red is this X-ray informed prediction from the maser shock model. And so it appears that the upper limit is about an order of magnitude below the predicted optical emission, and so I think this disfavors pretty strongly this nominal version of the maser shock model. So you don't need a galactic FRB to do this. You can do this for nearby or bright sources, and here I'm highlighting some of the work that's being done. So there's a few papers by Charlie Kilpatrick in the F4 collaboration, who's been able to rule out large parts of this parameter space for this maser shock model. Of course, you don't have this X-ray counterpart to tie the different parameters to, but you can still make a lot of progress in terms of trying to rule out parts of this parameter space. And there's a really nice paper by Aaron Perlman with these X-ray constraints, which for this very nearby FRB are starting to get down to the kinds of energies and luminosities that we observed from STR 1935. There's other ways you can do this, and one of the most interesting for me is actually performing radio observations of transients that are detected at other wavelengths. And so I'm just highlighting here some work by Alice Curtin and Yun Tian, performing radio observations either coincident to or slightly before or after short gamma ray bursts. So I think there's a number of papers predicting fast radio bursts from neutron star mergers. The rate just seems too low to explain all of the fast radio bursts, of course, but a fraction could still be powered by these mergers. And I think these kinds of works are really important. So moving towards the magnetospheric models, again, I'll refer you to Navin's talk on day one, which gave a nice overview of all of the different types of models, including many magnetospheric ones. What I want to talk about is focus on what do we actually mean when we say we've got a magnetospheric emission model, and where can we start to make progress here? So I think what we mean is that we have a set of events or a set of mechanisms that eventually will give rise to what we observe as an FRB. So we have some trigger mechanism. So for a magnetar emission model, this might be a quake or some kind of disruption to the surface of the neutron star. You have some mechanism for accelerating particles. You have to have some way of getting the observed emission out, radiate from these set of accelerated particles. And again, this is something we've been trying to understand for pulsars for 50 years. This is not an easy problem. And then we have to think about how does that FRB escape the magnetosphere? What parts of the observed FRB are intrinsic to the particle radiation, and what's imprinted as the wave escapes from the neutron star? So there's many different parts to this kind of complete theory of an emission mechanism, and I'm highlighting some of them here. I'm sure I'm missing out a lot as well, but the point I want to get across is there's multiple ways you can make a fast radio burst. So for example, you could say that maybe star quakes lead to these gaps that are not screened by pairs, which gives rise to the two-stream instability, and you get coherent curvature radiation. But I think it's important to remember that possibly many of these different mechanisms are viable, and possibly there's modularity between them. So you could have, for example, a slightly different way through this path to make a different type of fast radio burst. This said, not all sources should have the same chain, so you can have completely different chains of events if all of these mechanisms prove to be able to produce this kind of emission. I think we can go further and say that not all bursts from a single repeating fast radio burst should have this same chain of events. And also, possibly not all subbursts of a single FRB should have the same chain of events. So I'm highlighting here some of these high temporal resolution observations that have been done where we're seeing these micro shots or nano shots of emission in a broader burst envelope. And I think it's possible that perhaps you have a different type of trigger mechanism or a different region of particle acceleration or a different radiation mechanism that produces these micro shots compared to the rest of the fast radio burst. So we heard yesterday about some of the exciting new discoveries of these long period transients in many talks in the session. And I think it's useful to remember that this is only the third class of these luminous coherent radio sources likely powered by compact objects. So we have pulsars, and a lot of our understanding of fast radio burst emission physics comes from pulsars. But now we have this new class, and I think it's worth trying to understand what we can learn about this new class and how we can apply it to fast radio bursts. So we heard a lot about this yesterday. I'm highlighting here some of the kind of neutron starry properties that some of these LPTs have. So on the left, some of these spectropolarimetric properties of the GPM source, which look a lot like fast radio bursts and are very reminiscent of neutron stars. And on the right, some of these ASCAP sources where we have things like interpulses, mode switching, and of course this X-ray counterpart that Andy spoke about yesterday, which is very reminiscent of pulsations from a magnetar. So if we want to make this analogy, we need to be able to explain how magnetars can produce this emission. The first thing we need to do is understand how magnetars can be spun down to these very long periods, but retain their very strong magnetic field, because this radioluminosity often is in excess of the limits on the spin down luminosity. So they must be magnetically powered. So there's a lot of work going on trying to understand how we can spin these magnetars down, but retain this magnetic field. We heard yesterday about fallback disks, for example. There's other ways you can do this through mass-loaded winds, taking angular momentum away, possibly binary evolution channels as well. I think this is really useful in terms of understanding the evolution of these magnetars. But one of the key questions for me is I think, more directly related to the challenges of the fast radio burst emission mechanism, which is working out how can we get magnetically powered coherent radio emission from these sources. And so me and Zorawar wrote a paper last year trying to understand how this could be possible. And one of the ideas that we've come up with is essentially twisted magnetic fields that are driven by these active crusts. If you go above a certain critical twist, then what we show in the paper is that we expect particle acceleration, pair production, and this broadband radioluminosity to occur. And this is very similar in nature to the kinds of rotationally powered emission we see from pulsars, but here occurring on these twisted magnetic field loops in the closed field line region. The point I want to make is that the requirements for this kind of emission are relatively mild. So the twist that we seem to require to explain these LPTs is maybe 1 part in 10,000 compared to the background magnetic field. The crustal flow rate, this plastic flow as we call it, we think we need on the order of tens to hundreds of centimeters per year. But the luminosity scales very strongly with these parameters. And so you can imagine, for example, if you have slightly larger twists and of course much more sudden and violent crustal events, then you can get to those luminosities. You can bridge that gap to fast radio burst with relative ease. And I think there's a link in the physics as well. So as I mentioned, these are both possibly crustal phenomena. There's many models of fast radio bursts that invoke crustal slippages or star quakes, one of which I'm highlighting here on the left. And it seems like the parameter space for these two different types of models might be similar in some way. You need twisted magnetic fields, you need some active part of the crust. And another point I'd like to highlight is that longer periods in general will have a less dense magnetosphere and perhaps alleviate some of these problems with getting the fast radio burst out of the magnetosphere. The final point with respect to these long period transients, I just want to highlight one of these plots from Andy's paper where in the one epoch where X-ray emission and radio emission were observed in close proximity, the luminosity of the radio emission and the luminosity of the X-ray emission appear to be roughly the same. So perhaps the X-rays are slightly more luminous, but this implies that possibly radio emission from magnetars can be much more efficient than we thought. And I think it's useful to compare this to the radio X-ray luminosity ratio we observed from the galactic FRB from SGR 1935, which was much, much lower. So perhaps this implies that some magnetars can get to much higher efficiencies. Some final thoughts to end on. So I think we're entering this kind of era where we have a whole lot of data on fast radio bursts and not enough theories to explain it with specific predictions. And so to highlight this, I'm showing some of the observations of these hyperactive repeaters. So we have telescopes like FAST, which are observing hundreds of bursts per hour. And also this is kind of complemented by the Hyperflash program that Omar spoke about a couple of days ago, where you have these high time cadence observations getting towards these much rarer but much more energetic bursts. And both of these works, which are on the same source, come to similar conclusions, which is that if you roughly calculate how much energy there is in the magnetosphere, making some assumptions, then these sources should run out of energy on kind of month-to-year timescales based on what we're observing from the FRBs. And so perhaps this means that we don't quite understand what kinds of magnetars can produce these hyperactive repeaters. Maybe we have a much higher radio efficiency, as I discussed earlier. Perhaps there's some replenishment of this magnetic field through, for example, expulsion of the core field, which can be much higher, or perhaps you have these significant twisted components. In terms of the next steps of making progress on fast radio burst theory, and specifically on these magnetospheric models, I think there's a lot of use and value in developing these kind of models that you know are imperfect, but you can start to use to fit the data. So we know that, for example, we're going to miss out on some of these propagation effects that we don't understand. Possibly we're going to make many assumptions about what mechanisms are powering these FRBs. But I think if we want to make progress, if we have, in some cases, thousands of FRBs from these sources, we can begin with simple models and start to try and fit them to the data and get at these underlying parameters. And so I'm highlighting here a couple of works by Voisin and collaborators where they take these simple geometric models, which are essentially emission mechanism agnostic, and start to fit them to repeating fast radio burst sources. And this is not perfect. It's a very simple model, but you can start to get at some of these parameters. The final thing, I think that making this connection to galactic magnetars is crucial. And one of the challenges here is with the observations. So we have one example of a galactic FRB. We have what we think is a handful of examples of extragalactic magnetar giant flares now. But we have tens of thousands of fast radio bursts, and we have on the order of thousands of magnetar X-ray bursts from our own galaxy. And so making this connection is difficult, but I think it's a crucial step towards trying to understand what these sources of particularly repeating FRBs actually are. And this is part of the reason why I'm really excited by these new instruments that have large fields of view, despite being less sensitive, trying to increase this number of either galactic FRBs or local universe FRBs. And what I think this will help us do is actually leverage some of what we know on the theory side of how magnetars evolve, what their burst rate looks like as a function of time, and try and make the connection between, for example, young evolving magnetars and hyperactive repeating sources, or possibly older magnetars that produce maybe one or two bursts and look slightly different, both on the X-ray side in our galaxy, but also extragalactic fast radio burst sources. So I'll leave you with my summary slide, and I'm happy to take any questions now or on Slack. Thank you.
Okay. One question online.
Yeah, firstly, a question in the chat online. Hi, this is Pranav attending from Bonn. I'm curious whether any of the coherent emission models can be modified to account for the narrow emission bandwidths observed in FRBs?
Yeah, so I think there is a lot of predictions out there. There's a number of recent papers that claim, for example, that coherent curvature radiation can get these narrow bandwidths. I think many of the emission models that we have at the moment are focused on these kind of broad properties of FRBs, including the narrow bandwidths. So I think there are ways to get to the narrow bandwidths. Yeah, it's a question of trying to understand, I think, which parameters you need to get to the specific properties of one FRB, and then trying to actually fit those properties with these models.
Questions in the audience? Okay.
Hi, Alex. This is Naveen from Stanford. Thanks for the nice overview. I just would like to add a subtlety to one of your initial couple of slides on the optical counterparts from shock-based maser emissions. The prediction of a bright optical flash from maser emission is only valid in models that consider a paired plasma as the upstream medium where the shock occurs. If the upstream medium happens to be an electron ion plasma instead, then you would not expect a contemporaneous bright optical flash. That's it. Yeah. Thanks again.
Yeah, thanks. Yeah, I was specifically talking about this one kind of first model, but as I mentioned, there's different versions of this now. And for example, some of these occur closer to the neutron star surface and can get around some of these observational constraints.
Okay, we have a question online. Shami, can you unmute yourself?
Yeah, thanks. That was a great talk. I enjoyed it. Quick question, partly inspired by what Naveen just asked as well. What do you think about the non-detections at other wavelengths? How constraining are they beginning to be on some of these models? Like the non-detection in X-rays, non-detection in optical, how's that constraining some of these existing FRB models?
Yeah, so this is really difficult to do for extragalactic sources, even the nearby and very bright ones. The predictions are usually for fluxes lower than we're able to constrain. So I showed one plot with by Charlie Kilpatrick where you can rule out some of the parameter space for some of these models based on optical observations. I think it's difficult to do with the instrumentation we currently have, particularly in X-rays, right? We're just getting down to the X-ray radio fluence of SGR 1935 for this very, very nearby fast radio burst at 3.6 megaparsec. So they are not super constraining, and hopefully this is why I'm hoping that there's going to be more of these either galactic or nearby local universe bursts that we just heard about, so we can try and perform these observations and get more constraining upper limits or detection.
Yeah, there are questions. Please introduce yourself. Yep.
Thanks for the really interesting talk. I'm Pawan from Swinburne. I think you touched upon the radio reservoirs for some of these hyperactive repeaters and ways in which the energy can be replenished. Can you comment a bit more on kind of channels available, and what's your thought on sort of the models which can best explain such prolonged period of hyperactivity?
Yeah, so there was some discussion in the Slack about this as well, which I think is really interesting. I think so. At the moment, what we're doing is we're roughly calculating for a given magnetic field and a given efficiency and beaming fractions that we assume how fast these sources might run out of energy. But these are very simplified calculations, and so I think there's easy ways around this. If these are slightly more efficient radio emitters, then this gets rid of a lot of these constraints. But there's a lot more we think we know that magnetars, for example, are evolving. I think possibly Sam will talk about this in the next talk about how the core field might replenish the external magnetosphere. And also this isn't taking into account any twist that you might have in the magnetosphere, which adds energy to this external field. So I don't think that this is something to worry about in terms of a magnetar-centric model, but this is possibly suggesting that we don't have a complete picture of what kinds of magnetars can produce these hyperactive sources.
Okay, I think we need to go to the next talk. Sam, can you share your slides?
Yep, absolutely. Give me a second.
Oh, yeah. Let's thank Alex as well. So can you start, or I guess present?
Oh yes, sorry, it was a bit silent.
Yeah.
Give me just a second. Is that? Just try and work out if I can maximize this without you losing the sharing. Can you still all see that fine?
Yes.
Okay, great. So thanks so much for the opportunity to give this talk. I'm really sorry I couldn't be in Montreal myself. In fact, I'm actually traveling, so I've been unfortunately dipping in and out of the conference. I'm actually going away from Montreal, technically. So this talk is about, it's kind of a step back in terms of what happens before we see an FRB. And this I'll try to argue is a bit of the problem we really need to understand, and it might help to disentangle some of these models that Alex was just talking about. So luckily Alex has motivated you all, because I don't really have time to do that. But broadly speaking, in astrophysics, if we see any bright source, any unusual source, and then it repeats somewhere down the line, the natural first assumption is to say, is it a magnetar? And it's a natural thing to ask, because this is an object where you've got a huge, not just a huge energy reservoir, but a huge free energy reservoir that you can potentially get out. And you have a valve, so you know the energy doesn't get out all at once because you've got this solid crust in the way. And the majority, I would say, of modeling, and this goes for, if you like, traditional high energy magnetar modeling as well as now FRB modeling, is to concentrate on the emission physics part of the problem. And it's logical because this really directly relates to what we actually see, what we observe. But clearly, the pre-emission stage is crucial too. And emission physics modeling, generally the assumption is we know magnetars have got this energy and we just need to concentrate on the modeling of the particle processes and that kind of thing. And my argument is that you also need to look at the stage before that of, can you get the energy out where you want, when you want? And the reason to look at this stage is that this potentially allows you to constrain and possibly even disprove some magnetar related ideas, initially in the context of high energy short bursts all the way up to giant flares. But the same is true for if the central engine for FRBs and maybe some of these ultra long period radio transients is again a magnetar, it's the same motivation basically. So briefly in one slide, the activity of magnetars, again high energy and radio activity, is likely gated by the star's solid crust. So what happens is you have a slow, unseen buildup of stress in the crust, and then a sudden release in some form, some of a burst. And in the recent years, more attention has been given to that pre-burst stage that you don't actually see. And there's some very challenging physics there, and it's very much a work in progress. Broadly speaking, some of the things that we think we know are that the magnetic field in the neutron star crust, for a sufficiently strong magnetic field and certain other caveats, evolves predominantly under Hall drift, which is a process that takes the magnetic field and essentially breaks it into smaller and smaller length scale pieces. And as you do that, you increase the crustal stress. So the crust is relaxed in the Magnetar magnetic field's original state, and then the magnetic field starts to evolve, and that causes the buildup of stresses. We don't see the buildup of stresses because the crust, to start with, remains in that elastic phase until, just like if you pull an elastic band too hard, the stress becomes too high, you go beyond the yield stress of the crust, and then the crust in some sense has to break. The way which we think it does break is not a kind of brittle failure, but rather this plastic deformation or flow. And that plastic flow, it doesn't directly reduce the stress, it's more complex than that, but it seems to be, it broadly pushes you in a direction of reducing stress. And as it does that, because the corona of the magnetar has its foot points stuck in the crust, as you twist the crust around, sorry, as you have crustal motion, you twist up a coronal loop, and then you get to the emission part of the problem. So Hall drift in this magnetic field evolution problem, Hall drift is this first term here, so it depends on the curl of B cross B. And then the plastic flow piece, the evolution under plastic flow, is this advection term. So it's the curl of the plastic flow velocity cross product with the magnetic field. There's one big problem, I would say the biggest problem here in crustal failure physics is that we don't know how far any given failure extends. And this is really hard to work out. The simulations we have are really truly microscopic simulations. So it's molecular dynamic simulations, and you can't extend that to the whole crust. It's easy to see why if you think you can imagine you have some very tiny region of the crust which has gone beyond the yield stress. You don't expect the entire crust to just start plastically deforming if the rest of it is below the yield stress. And although there are analogies with the terrestrial context and even some kind of statistical similarities, we don't have the luxury of having tectonic plates like in a magnetar like we do on the Earth. So we don't know where a given failure would normally stop. So one way to kind of imagine, to kind of get past this conceptual problem is we can look at what the kind of stress that Hall drift produces, and this is characteristically roughly 1 kilometer squared patches that develop. So those should be, you can imagine, semi-independent cells where the crust evolves, and then because some activity is a lot brighter than others, you get all the way from the lowest energy events like short bursts or some FRBs up to giant flares. There should be some mechanism for those cells to communicate with each other. And each cell should have a long phase unseen when it's in its elastic phase where the Hall drift is increasing its stress, followed by a quick plastic drop in stress. So if you imagine dividing up the crust in this way, so flattered to see this figure a few times before my own talk. If you're in the Hall phase, you have these loops on the left, these magnetospheric loops where the crust is static, so this coronal loop is untwisted. On the other hand, if you then enter the plastic phase, to have a plastic flow that doesn't extend beyond that cell, you have to have a kind of circulation in the theta phi direction, and that causes a twisting of that local coronal loop. So that on its own will give you small bursts. If you then want to explain everything all the way up to giant flares, I know we don't care about high energy here, but that's part of the motivation for the part of the motivation for this is both seeing how you can get radio and X-ray emission. So if you have this kind of communication between cells, you can get a stress evolution looks like this on the left. So I'm not sure how many of those frames are displaying for you, but the point is that when you get a communication between groups of cells, you can get a giant flare, and then you lose a lot of stress in that region, and you're left with more isolated patches of stress afterwards. And broadly speaking, what happens then is you see some very violent activity early on, and then you see smaller bursts and periods of quiescence. The interesting thing about this picture is that it's different from this traditional sketch of a magnetar corona where the entire corona is twisted up. If that really is what a magnetar looks like, you wouldn't expect to see any radioactivity at all because it's basically screened out by this charge dense corona. On the other hand, this this model that's built up from ideas about crustal failure and Hall drift points to a corona which isn't that large-scale self-similar one, but rather is a complex one where you have local regions which are low twist, which might be associated with FRB emission, but the same source, as indeed we saw in like SGR 1935, can have some also highly twisted coronal loops, which you would associate them with X-ray emission. The point here, though, is that if this is all part of the same picture, you should expect some statistical similarities there as well. Okay, so then just moving, kind of jumping from FRBs to these ultra-long period sources then, and the connection isn't obvious at first, and this in fact was a bit serendipitous. I was looking at what happens very early on in the life of a neutron star when it starts to become superconducting. So this happens just a few minutes after birth. And if you've seen these experiments on Earth, what a superconductor tries to do below a certain field strength is to expel a magnetic field that runs through the superconductor. The problem is with a neutron star, you can't expel the field. The field is intrinsic to the star. And instead, the two sort of traditional limiting pictures for what might happen are either you manage to expel the field somehow, so that would be the picture on the left. So you have a crustal field which has no connection with any core field. So this purple region is zero field. Or you have a magnetic field that threads the entire core. And the connection here with magnetar activity is that all magnetar modeling, so that the evolution of this Hall drift equation, assumes that you have to have an expelled field. If you don't have that, it turns out that the simulations just don't display any magnetar activity at all. What's interesting, though, is if you consider this process of how that expulsion might occur, and there's a tension between whether it can, or different factors that dictate whether it can or can occur fully, you also get these intermediate states where you can have the field expelled from, so like the second or the third plot here, where it can be expelled from most of the core, most of this kind of, purple ring, but then thread the purple ring in some select places around the equator or the pole or various more complex geometries. And so having looked at this, I then discussed with some colleagues about let's look at what happens if we evolve the magnetic field in these new cases. And there was a big surprise, which turns out, well, I'll show you the pictures, probably the videos actually. So this is a canonical traditional magnetar simulation. So the field is expelled from the core. It's developing in the crust. You're looking at these black lines are poloidal field lines, and the color scale is the toroidal field. You see a peak of activity around 10, 20, 30 kiloyears. It's around now. And then as you wait longer, the star becomes less and less active. So you expect it to become less and less active into old age, which is fine for a typical magnetar, where we do expect that the activity reduces as you get towards, let's say, 100 kiloyears. On the other hand, we now have reasons to hope, let's say, that there could be such a thing as an old magnetar which reactivates at far later times. And just see if I can play that again. So if we look at then the right-hand plot, so this is one where you've got this equatorial hole. You have the same kind of initial evolution from the outside inwards, but you also, from the cross-core boundary outwards, you get a different kind of, you get an extra piece of evolution. Those two kind of packets of toroidal field meet in the middle, and there's an interplay that means that actually the activity in this model starts to become really enhanced about the point it's dying off in the traditional model. And the star actually seems to be becoming more and more active around the 1/10 of a megayear, probably beyond that, but for numerical reasons we haven't been able to pursue it further. But the point is that this would really be an old magnetar, and it comes about naturally just from considering that early time expulsion process. So the broad message here, sorry, no, it's a bit rushed when you try and get two different topics into a 10-minute talk, is that if you look at, take a close look at the physics that actually gets the energy out of the star, so the Meissner effect and the process of crustal failure, it stops being just a hope that you can explain everything as a magnetar, but it actually becomes natural to expect magnetars to be FRB emitters, or in some cases to become these ultra long period sources. And that doesn't contradict the fact that they can also be typical X-ray bursters as well. So thanks for your attention, and I'm very happy to take any questions. If you want to email me afterwards, that's my address. I'm afraid I'm not on the Slack very much because, yeah, I'm rushing around at the moment.
All right. Any questions? Okay. Please introduce yourself.
Hi, we are from University of CES. So we always treat the star-quick wave as monochromatic waves. So is that a good assumption or a good approximation?
You always treat the what? Sorry, the.
In other words, I mean the spectrum of the star-quick waves as something like a third function here, as just a monochromatic wave. So is that a good approximation?
I don't know that I could say it's a bad approximation necessarily. It's
Maybe we should consider some nonlinear process here. I don't know.
I think it's the actual process of the crustal failure and then the waves you set off from that's sort of I don't think what I'm doing here would greatly constrain that, because it's a sort of a separate bit of the dynamical problem. So really what I've been doing here is a kind of is looking at the long time evolution of magnetars and how at different phases really you have different kind of stress patterns, and you can associate that with different levels of activity. But I think what you're talking about here is really what the dynamics of this process are. So as far as I know, it's a good assumption. I don't have a problem with it anyway. Well, I don't know enough to have a problem with it.
Okay, thank you.
Thanks.
Any other questions?
Hi, I'm Adam Landman from MIT. I was wondering if you had any thoughts on how if there were a companion star that might interact with the neutron star crust and induce any of these kinds of failures that you're describing.
So if you have a companion star of a sort of similar size to the neutron star, you mean, or?
Yeah, or like a tidal interaction of some kind.
Right, yeah. So if you've got tidal interactions, you've got a different source of stress. I think this source of stress that I've got here is is universal if you have a strong magnetic field. That stress though should interact with the tidal deformation as well, in a way that I wouldn't be able to tell you off the top of my head. And also, obviously, if you've got the companion, it might be that you might eclipse some activity that you might otherwise see. Like you might just, if you have a situation where you have any kind of, I guess, for example, accretion or whatever, I think broadly speaking, you would always tend to reduce your chances of seeing any radio emission from that system, probably compared with the isolated star, just because the environment is messier and it's easier to kind of screen out the accelerating electric field that you would need for radio emission. Beyond that, yeah, I'm not sure. The tidal field would definitely cause an extra source of stress beyond the magnetic stress, and there would be some interaction there for sure.
All right, thank you.
Any other questions? Okay, let's thank the speaker again.
Thanks very much.
Our next talk is a pre-recorded talk from New Zealand, which is, I think, 2 a.m. there.
Hi, my name is Clarinda, and I'm currently a master's student at the University of Canterbury in New Zealand. This is work I've done as part of a summer project at Swinburne University in Melbourne of Australia, which was focused on the effects of beaming in fast radio bursts. So the main aim of this project was to look at the directional dependence of the emission, which is what we call the beaming. By trying to reproduce observed energies of known FRBs, we can analyze how beaming may influence their energy distribution. And this theoretical explanation can help us to understand the role of beaming in observed energy distributions, potentially helping us to further constrain the emission mechanisms or progenitors of FRBs. Modeling the energy distribution of FRBs is typically reliant on the number of bursts. So FRBs with fewer bursts are reliant on the cumulative distribution function to be modeled by. So in the case of 121102, where there were fewer bursts, it was modeled with a power law that ranged from the power law index of minus 1.1 to 0.2. And FRBs with more bursts can be modeled by their probability distribution functions. So the burst energies of FRBs are typically between 10 to the 36 and 10 to the 41 ergs. However, the limits on the lower end of the observed energies is caused by telescope sensitivity. Activity windows with more bursts are also more detailed than those with fewer. So with both of these basic factors in mind, we can make the assumption that we are only observing the most energetic FRBs, and those with many bursts are easier to approximate an energy distribution for. In particular, Lee et al. Did an analysis of 1,600 bursts from FRB 121102 over the span of 47 days. They found a bimodality that appeared and then disappeared over a period of days. And they were able to model this energy distribution with a combination of a generalized Cauchy function and a log normal function. And they suggest that this may mean that possibly more than one emission site or beam shape would be required to result in this type of energy distribution. Similarly, Zhang et al. Also did a study on 800 bursts from another FRB, 2011-24A, where they analyzed 800 bursts over the span of 4 days. And they were able to model their bimodal energy distribution with an exponentially connected broken power law. Both of these analyses are using more complicated functions to try and recreate these observed energy distributions. However, they're not considering the beaming. We are going to try and recreate the same observed energy functions, but with beaming and hopefully simpler functions. As we consider beaming to be the effects on the observer's position relative to the center of the beam on the observed energy distribution, we need to consider three main features: the angle of the observer relative to the beam, the shape of the emitted beam, and its underlying energy distribution. Firstly, we assume that we can observe the beam from a random position and angle. So for this, we simulate a bunch of random X and Y angles, which describe the angle of the observer relative to the FRB center of the beam at the origin. And so that we then exclude angles that are outside a R max, which is past that point, an observer would not be able to see a emission from the FRB. So going back to the diagram from before, this shows how we can think about a beam from an FRB source. If an observer is angled in line with the FRB emission, i.e. at R0 or between RP and minus RP, then they will observe the maximum energy. If the observer is positioned further away between RP and Rmax, then they will still observe the FRB, but likely at a lower energy. However, if an observer is located at an angle that is greater than Rmax, then they will not be able to observe the FRB emission. So based on the current literature in FRB beaming, we chose two main beam shapes, a Gaussian beam and a relativistic beam. And so on these graphs here, I just have the strength of the beam versus the angle out from the center. So it goes from 0 to 1. And so at 0, the Gaussian and the relativistic beam are also at their peaks. So at that angle away from the center, it was 0, then you would see the maximum energy. So we also consider the case of a single energy, and we can plot these simple energy distributions and their corresponding equations. So for the Gaussian beam, we are able to choose the width, and for the relativistic beam, we can choose a Doppler factor. We also have to simulate a secondary angle, which is theta, which is drawn uniformly between -1 and 1. We are also able to combine the isotropic beam with the Gaussian and the relativistic beam in a piecewise function to create a central core or a plateau to a certain angle RP. This gives us a plateau region in the observed history diagram, and at an angle greater than RP and less than Rmax, the beam shape is given by either the relativistic or the Gaussian equation. From looking at these distributions, we can see that the Gaussian beam seems to just be giving us a uniform distribution. However, the relativistic beam results in an energy distribution that looks somewhat like a power law. So we are also able to consider different intrinsic energy distributions: a single energy, a power law, a broken power law, and a log normal intrinsic energy distribution. The single energy is unphysical, but we use it as a reference to see the effects of the beam shape. Initially, we did consider the broken power law. However, it had a similar effect to the single power law, and it didn't create any features that would favor a bimodal energy distribution. We also found that throughout beaming, the effect of the broken power law was not conserved. Regardless of whatever beam we applied, we would end up getting just a single power law out of the intrinsic broken power law distribution. For this reason, the simulation results that included the broken power law are excluded from the rest of this talk, as they didn't provide any significant difference to that of the single power law. So the graphs I have here are just the intrinsic energy distributions if there was simply isotropic or single energy emission. Below the graphs, I've also included our definitions for the power law and log normal distributions. For the power law, we are able to change alpha, the power law index, and with our definition of the power law, alpha must be less than -1, so that as E tends to infinity, the probability of a burst tends to 0. For the log normal distribution, we are able to change S, which is the location parameter. Taking all of these steps into consideration gives us our simulated results. Just to run through it again quickly, we first generate a number of observer angles, we then create a beam shape, and then we apply an intrinsic energy distribution. We then get an output of an observed energy distribution. So we can look at the different combinations of intrinsic energy distribution with beam shape. So for this graph, we have the rows being the intrinsic energy distributions, and the columns are the different beam shapes. Any fall off at the low energy end is due to telescope sensitivity, or equivalently, the maximum angle at which the FRB can be observed from. Taking a closer look at these energy distributions can help us understand them better. So firstly, looking at the Gaussian beam shape with an intrinsic power law distribution, we see that the Gaussian just gives it a uniform top, and then there's a power law drop off. And this doesn't give us anything close to a bimodal energy distribution. So then we take the case of a Gaussian with a central plateau region. So we then get a uniform distribution with a singular high energy peak. And so this isn't quite yet a bimodal energy distribution, but we can see that having a central plateau helps to give us this high energy peak. And it also means that if any observed energy distribution that needs to have a second peak must have a beam shape that falls off slower than a Gaussian. So finally, we combine a central isotropic core with a log normal intrinsic energy distribution, a central plateau with a relativistic beam drop-off with a log normal intrinsic energy distribution. We get two distinct peaks. And so therefore, this combination allows us to have a bimodal energy distribution. So now that we're able to create a bimodal energy distribution, we wanted to see if there was any sort of relation between the size of the plateau and the shape of the energy distribution. It turns out there was a relationship between the log of the height of the log of the ratio of the height of the high energy peak to the height of the valley in between the two peaks, and the angular size of the plateau region or the central core. So by I, we define the bounds of the bimodal region between 0.3 and 0.83 for RP. And so after simulating a range of observed energy distributions with varying plateau sizes, we can define a linear relationship in the bimodal regime. So that is the log 10 of the ratio is equal to 1.79 times RP minus 0.53. So we can take our two bimodal FRBs, 2011-24A and 1211-02 that we saw earlier. We can plot their energy distributions, and we can then determine the ratio of the peaks to determine the angular size of their theoretical central core. For 2011-24A, we get a high energy peak just below 60 and a valley just below 50. And then we can do the same thing for 1211-02, and we can plot these onto our graph. So we find that for 2011-24A has a peak to valley ratio of 1.54 and a theoretical central core size of 0.4. And for 1211-02, it has a peak valley ratio of 1.84 and an estimated plateau region of 0.54. And this, of course, is dependent on the bin size that we've done and also the time window that we analyze them in. And so one thing that we've started doing is to look at the time evolution of the ratio. So this is a graph where you can see the time evolution of the ratio of FRB 1211-02. So it starts off with its RP in the bimodal regime. It drops back down to the unimodal regime, and then it jumps back up again and stays in the bimodal regime for a while. So while this graph doesn't consider errors, it does show that the FRB tends to stay in like its particular window, and it doesn't just tend to jump sporadically. So that gives us something to think about. So to summarize, we find that we can create an observed bimodal energy distribution using a combination of a relativistic beam with a uniform central core with a log normal intrinsic energy distribution. The energy distributions of FRB 2011-24A and 121102 fall within our bimodal regime. And this result will allow us to constrain the plateau size, the parameters of the intrinsic distribution, and possibly the value of Lorentz factor. That's it from me. Thank you for listening to my talk, and feel free to contact me if you have any questions. Thank you.
So I believe Calendar is on Slack, so I think we should ask her questions there, and we should go to coffee break now. We'll return at 11.
Yep. Can I check if I think the slide advancing. So okay, okay, perfect. Thanks.
Okay. We could start. Magnetars, you'll talk about extreme scattering in the FRBs.
Thank you.
Okay.
Right. Hello, everyone. I'm Pawan, a fourth-year PhD candidate at Swinburne University of Technology. Today, continuing with the spirit of this particular meeting, I'll be talking about one more repeater, FRB2024-0114A. Oh, yeah. Is it better now? Yeah. Absolutely. FRB2024-0114A does not require any introduction. We have seen many talks about it over the last couple of days. However, I'm here to give you a unique perspective of this source using the UWL on Murray-Young Radio Telescope. Now, this is a very unique instrument in the whole wide world. Yesterday, we heard a talk about the follow-up of the source from ATA, wideband follow-up. However, I'm here to take that a notch higher, use 6:1 bandwidth or 2.6 octaves of bandwidth between 704 to 4032 megahertz, and then show you some unique characteristics of the source. The plot here on the right shows this beautiful emission across the whole band. If you look at the y-axis, it's 704 to 4 gigs for a Magnetar J1810. Now, because of this high fractional bandwidth, it makes it an ideal instrument for repeater follow-up, especially considering its reliable wideband spectropolarimetric information that it can give us. Now, coming to the source itself, this was reported by Chime back in January 2024, and a lot of us started following up the source. Now, to that effect, we have detected over 5,500 bursts from the source until 1st of June. And the reason 1st of June was because parks went under maintenance after that. And this is, mind you, with the entire information of about 3.3 gigs using the UWL. This gives us an unprecedented wideband insights into the spectropolarimetric and temporal behavior of the source. One of the brightest bursts that we have detected to date is about 2,500 sigma. The plot here on the right shows that, and this shows this beautiful SATCOM1 structure as well as multi-peak emission. I did this in November meeting as well. Back then, the cost per FRB was about 28 Australian dollar per FRB. Now it's 30 Australian dollar. It seems to have hit an inflationary patch, but I can assure you that this is just transitionary. Now, when we sort of zoom out and look at the whole follow-up of 16 months of the source and see how the burst activity has been evolving, this is what we exactly get. Now, let's walk through this slowly. The top panel, panel A, shows the burst activity over 16 months. The purple color shaded region shows the number of UWL hours that we have spent looking at this particular source. Eagle-eyed among you would have already noticed that there have been multiple burst storms from UWL that we have observed. And the panel in between, panel B, shows the spectral extent in the error bars, and the black color points show individual center frequencies of bursts, and the red color point shows the center frequency, average center frequency of all the bursts per epoch. Now, as we can see here in the bottom, if we only had a narrow band instrument, we would not have been able to catch many of these burst storms. The bottom panel shows the RM. RM had stayed fairly consistent over multiple months. However, starting about 6,600 MJD, we started seeing a precipitous decrease in the RM of about 0.9 RM units per day. Now, when we started the initial follow-up, we did not have a continuous coverage or uniform coverage of the source. That's why you see a lot of gaps here. However, starting October last year, we started getting more and more uniform coverage. And that is why we will focus on two of these burst storms here. Now, one of the very interesting things about the source is that whenever it goes into burst storm mode, it slowly ramps up and then it again ramps down slowly. However, in these two burst storms, we can see here that it ramped up, and then as soon as it had to reach its peak activity, the burst activity suddenly quenched. It ramped back up and then came down gradually, and that is what we see in another burst storm as well. Quite interestingly, this was also associated with a shift in the center frequency. For example, just after this burst quenching, which is shown here in the green color shaded region, in the middle panel, it shows this sudden quenching or sudden shift in the center frequency of emission. Now, in our quest to sort of understand what exactly is going on, we turn to one of the potential models, which is the extreme scattering event. Extreme scattering events are nothing new. They were first reported by Fleidler et al. Back in '87, and a Gaussian lens interpretation was given by Clegg et al. In '98. And this was sort of extended to FRBs by Cordes et al. In 2017. Now, the plot here on the right shows this sort of Gaussian lens interpretation. Because of plasma underdensities and overdensities, the focusing and defocusing regions would essentially cause caustics, because of which there would be apparent increase in brightness of this particular or of a source. Now, this has been observed in quasars, and this has also been observed in pulsars. For example, Coherent 2018 showed this ESC effect in young pulsar. If you sort of concentrate on the bottom panel, this is a narrowband instrument, and we can see this apparent brightening and debrightening of this particular source. Now, let's flip the switch here, and instead of pulsar, let's see how we would see an FRB in that context. Now, again, let's walk through this plot slowly. The top panel shows the MJD of individual epoch of follow-up. The dynamic spectrum is essentially taking all the bursts, about 20 sigma, in particular epoch, averaging across time, stacking them right next to each other. The white color stripes essentially show you the transition between one epoch to next epoch. In the initial days of follow-up, as we saw in our previous plot, we did not see any emission about 2 gigahertz. As we went along, we saw more and more emission across the whole band. It again sort of drifted back, went up, and then started emitting in the entire band, and went down and again did this chromatic kind of behavior. Now, this is not to be confused with chromatic activity of 1809-16B. This is way more complex than that. Now, one of the other things to notice out here is the fact that this has some sort of a spectral memory. Over weeks and days and weeks of time scale, we see this sort of lingering around of center frequency in similar bands over multiple days and weeks. Now, when it's not just the spectral memory over multiple days and weeks. We have been looking at spectral memory over multiple minutes, millisecond to minutes time scale. This has been sort of seen in 1202A observations using narrowband instruments. However, here is an example of fairly narrowband burst, for that matter. This is the whole band of UWL from 0.7 to 4 gigs. And the small burst, which was fairly bright, that we detected. Now, this also shows this preferred band of emission with same center frequency and same burst bandwidth. If I run through different bursts in the same epoch, we see these different bursts which have exact same center frequency, exact same burst bandwidth, which are separated about 10 minutes. This is sort of consistent with the amplification of specific bands through ESC. For example, if we just use the Gaussian lens interpretation and use 10 tens to 100 scale AU lens, this is what we kind of get in terms of gain parameter or sort of the gain function, or the band of UWL from 0.7 to 4 gigs. And the x-axis here is transverse scale, which is a proxy for time because we do not know the transverse velocity of the source exactly. And what we would see is if we take a slice across x-axis, we would see that there would be amplification over multiple of the same band over multiple time scales. Now, most repeaters have sort of been speculated or sort of known to live in a more complex magnetoionic environment. Therefore, plasma under densities and over densities, information of this is nothing surprising. Now, we can explain both of these using different length scales. For example, the long time variation or sudden burst quenching, as well as the spectral preferred spectral band of emission in a single E. Now, if we take that slice and then like stack all of these bursts that we detected, I've shown 3 of these bright bursts here, and sort of plot the gain function across the whole band, we would see that there is this specific discrete bands where it gets amplified, and which is kind of consistent with what we are looking at in terms of observables. Now, it's not just that. If this also sort of points, because we get very bright bursts of the order of hundreds of sigma. And as we saw in Manisha's talk today morning, high redshift FRBs are really exciting. And if we take this burst, which was about 500 sigma, and sort of redshifted, and this 3.5 megahertz at Moryang would be easily detectable by CHIME at a redshift of 6. Again, indicating an exciting possibility of detecting such sources in high redshift universe. Now, sort of summarizing and coming to the end of this talk, we have detected over 5,500 bursts by Moryang, this huge number of bursts with such large spectral bandwidth gives us a fairly unique view of the source. Combination of ESC and intrinsic effects are likely at play in some of the emission that we see from the source, and the macro spectral behavior in terms of spectral memory can be explained by multiple length scales due to complex magnetoionic environment. This also kind of opens up an exciting possibility of FRBs and high redshift universe. Thank you.
Nice talk. Do you have questions? Okay.
Hey, Pavan, it's Molson from here at McGill. And so I think there are probably a few people in the audience champing at the bit to ask the same question. So you had this big dynamic spectrum that's stacked up from all the different bursts over a wider time period. Have you done anything like just taking the power spectrum of that data to look for things like scintillation scales like they do with pulsars?
Yes. That's ongoing work, which is being sort of headed by one more PhD student. And we have been looking at scintillation and sort of analyzing what we can derive out of it. But yes, that is surely a thing that is.
And so I guess just as a very short follow-up, what's the spectral resolution for the UWL?
Oh, it's 0.5. We use 0.5 megahertz with 64 microsieverns. We can go down, but yes, that's
okay,
just
great.
data constants.
Thanks so much.
Very interesting results, Pawan. So quick clarification question on the property of the bursts during the peak of your outburst cycle. do you just see a switch in the central frequency, or do you also see a switch in the luminosity of the typical luminosity of the burst that arrive?
Yes. So there is apparent sort of brightening of that whenever we see the sudden or not sudden, like after this quenching.
Yeah.
In the lower band, we see more and more bursts which are higher SNR. Although it varies from burst cycle to cycle, so it's not strictly correlated, but yes, there is indication of that.
Very interesting. Thank you.
Can you pass it along to Duncan?
Pavan, this is Duncan Lorimer from WVU. Very nice talk. Could you show your sort of giant waterfall plot again? That one.
Yep.
So is it true that you almost always see it at the highest part of the band? It looks.
Oh yeah, so that's a good question. I was anticipating it. So because of the fact that we don't the calibration model that we have for flux calibration at Parkes is not very well behaved at higher frequencies. There are some of these, for example, these epochs where there are no bursts, but here there are truly bursts. These are just baseline issues.
Okay.
Yeah.
Right.
Yeah.
Ziggy Pleunis at the University of Amsterdam. Beautiful data. I have a question about your extreme scattering event interpretation. If you look at the rate of its ECEs are happening for quasars, for example, does it match up, or is it surprising that we find it in one FRB out of our sample?
Yeah, that's a good question. In terms of quasars, the ESCs are essentially because of, some of the Bannister et al. Essentially sort of constrain the plasma distance, lens distance, sorry. So that was more of a galactic scale. However, in terms of rates, we see for this, but again, we don't have a wide band information for a lot of repeaters. So I think it's more common than we anticipate, but yes, it requires wideband information in order to properly say that for sure. Yeah.
So you mean you are a little bit surprised that you find it in one FRB out of the sample?
In one of the bursts or for this particular source?
Just one sideline to one source out of all of the known repeating sources.
Yes. So I'm not that surprised, so to say. I would expect that because they live in more complex ionic environment, this should be more common. But again, there are 5 or 6 FRBs which have been followed up. So there is a combination of things. One, we need a highly active repeater. The second one is we need a wideband information in order to say that for sure. Here we had both of them. So it's possibly a more instrumental sort of observational bias rather than something related to the population itself.
Andrea Possenti from INE. Is there any trend between the central frequency of the bands when these events occurs and the flux?
Central frequencies. So when it goes into the quenching mode in these regions, we do see some fairly bright bursts, but it varies from burst to burst. Sorry, burst storm to burst storm. But in terms of strict correlation, in terms of high SNR bursts in specific bands, we don't strictly see any correlation if we take the whole 16 month of data. So yeah.
Thank you.
Yep.
Nice talk.
Thank you.
I think we have to move on. Please take the student. Next speaker is Meghna. I should talk about, AstroSat searches.
Yeah, I hope I'm audible. So hi everyone, I'm Meghna and I graduated from IIT Bombay. And today I'll be presenting the results from AstroSat CZTI searches for hard X-ray prompt emissions from FRBs. So first, a brief introduction about AstroSat. So AstroSat is an Indian multi-messenger space mission launched in 2015 in the low Earth orbit. And using the CZTI module on board AstroSat, we have already detected over 700 GRBs in the past 9.5 years. So for the FRB dataset that we used for our searches, we had around 968 FRBs and these are the publicly reported FRBs. And after correcting for the arrival time delays, we ran our search pipeline for detecting the X-ray prompt counterparts. And what we found was that for around 60% of the FRB sources, we had coincident CZTI data. And unfortunately, for any of these, we did not detect any X-ray candidates. But we did the next best thing and found the X-ray flux and fluence limits, with the most constraining ones coming from the 10 millisecond search bin. And in the plot for the X-ray to radio fluence ratios, you can see that the results are consistent with the limits that we got from our previous study, as well as the ones obtained from similar missions such as Swift-BAT and slightly deeper than the limits from CONUS wind search. And we can also observe that we have a lot of samples at a high value of eta. And this is consistent with the fact that radio telescopes are detecting fainter and fainter FRBs, but the sensitivity of X emissions has not improved by a similar margin. We also calculated the upper limit the energetics of the upper limits. And here we have two plots. One is for the isotropic equivalent luminosity and the isotropic bolometric emission energies. And we can observe from these limits that the equivalent luminosities of both short and long GRBs are actually higher than some of the limits for many of the events. And this points to the fact that short GRBs and long GRBs might not be, are unlikely progenitors, excepting the low luminosity GRBs, like the short GRB that was observed from JWST. And this also points for the need for searching for low luminosity GRBs, as was already discussed in some of the previous talks. So over here, I'll take the chance to promote Daksha, which is a proposed project. And this will have an order of magnitude higher sensitivity than the current project and an all sky coverage. So using Daksha, and we can, so not just Daksha, but we calculate the joint detections that we can observe in the next 5 years for X-rays and FRBs. And we observe that large field of view missions such as AstroSat, Fermi, and Daksha will complement large field of view radio telescopes like BURST. And I'll end over here. And if you're interested, please feel free to read our paper. Thank you.
Just have time for one question if anyone has any. Okay, do the next. Thank the speaker again.
Thank you.
Our next speaker is Maura. You'll talk about, I guess, R3.
Yes.
Yeah.
Good morning, everyone. So I'm going to talk to you about how we've looked for a counterpart, multi-wavelength counterpart of R3 in all these years. Just in case you get bored during these 3 minutes, here are my conclusions. We haven't found a counterpart over 5 years of, let's say, sparse monitoring. And we've learned that this detection is actually very challenging. But let me go back to the basics of this. So in 2020, the periodicity of R3 was announced. We started following it up with a Sardinia radio telescope. And during our very first observations, we found these 3 bursts at 300 megahertz. And we had a multi-wavelength campaign lined up for these observations. Unfortunately, let's say this burst happened during the day, so we didn't have optical coverage, but we did get to have a simultaneous X-ray and soft gamma ray coverage with XMM Newton and Agile minicalorimeter. Our upper limits on the energy of this burst were at the level of, let's say, 10 to the 46 Hertz, which were interesting because at the time, the only comparison we had was the brightest flash optical giant, X-ray giant flare over a magnetar in our own galaxy, SGR 1806. The thing is that since then, we've moved away from the idea that this can be the counterpart of fast radio bursts, both thanks to limits like ours, the non-detection in radio that was mentioned yesterday, and in particular, the fact that then SGR 1935 did a very different X-ray burst simultaneous with the radio burst, which was a very regular X-ray burst of energy of the order of 10 to the 39 Hertz. This, though, gave us a very much needed baseline, which is the ratio of X-ray to radio energy is in the range of 10 to the 5, 10 to the 6. And this is what we're looking for. So we published the results of our following part of the campaign in a paper by Matteo Trudo. As you see here, we added to the number of our telescopes, and this time we also had optical simultaneous observations. I want to stress that we're using 2 of the best instruments in the field. Unfortunately, they're not mounted at the biggest telescopes, but these 2 optical photometers, Aqui Plus and CFAP2, they can reach time tagging, photon time tagging of order nanosecond or sub-nanosecond. So in order to look for prompt counterparts, they are the perfect instruments. We didn't find anything in optical, but we got to very deep upper limits here. The ratio of energies between optical and radio is of order of 10 to the second. And unfortunately, this is not constraining because we don't have the equivalent of the galactic magnetar in optical. We just know that even in this case, magnetar hyperflares are to be excluded. Now, we haven't found a counterpart, as I said. In the X-rays with the new campaign, we got similar results to what we had with XMM. Basically, we're still 1 order of magnitude above what we need. And so we decided to calculate what it will take to find an X-ray counterparts with current instruments for R3. And basically, this got to a number that is roughly order of 100 hours simultaneously on the source, or equivalently a kilojansky burst. Not so encouraging, especially at the rate that X-ray telescopes are dying on us during this campaign. On the other hand, with the optical, we have a different issue. So we're not seeing optical bursts simultaneously to the radio bursts at a very deep limit. The thing is, we're seeing fast optical bursts at other times. But in order to pinpoint those to the FRB, we'd need at least 2 optical telescopes to be pointing at the FRB at the same time. And this picture shows, well, whoever has worked at the telescope here knows, it happens that one telescope doesn't work. If you're combining more than one, it happens that not all of them will be working together. But to end up on a more positive note, we have for this campaign some very good instruments in Italy. One is the Northern Cross that we've been refurbishing for our FRB studies, and this gives us a lot of time and sky coverage. It's our own telescope, let's say. And we're ramping up with 2 32-meter dishes that we have in Italy. We've been collaborating and learning from Hyperflash. Because what we need here, I hope I've convinced you, it's not high sensitivity. We're looking for the brightest burst because we need to get at least close to those ratios with X-ray and optical. Thank you very much.
Hi, Lauren Rhodes from McGill. I have a question about the optical observations. You said with the photon tagging.
Yes.
Were those observations like simultaneous to radio, or were they like triggered observations?
No, it's a simultaneous. No, we can't trigger. You don't have a fast optical photometers in triggered instruments.
Thank you.
Yeah, hi, Maura. It's Molson here from McGill. And so I kind of had a question that is again related to the like fast blue optical transients, like the prompt counterpart that you might expect. So I guess like the big experiments that have large all sky coverage, some of them do difference imaging to look for transients, but I expect the time scale is much larger than what you need. But I guess like that must provide some limit on really bright transients that would still show up in those images. Are those limits competitive at all, or just we don't even need to think about that?
So I'm probably not extremely qualified to talk about those limits. I think those were the ones that who was it described them this morning, the Kilpatrick results. Maybe it was Alex. So I think it's the same as for FRBs. If you're integrating over 1 second, then you might get to those, but it's very hard if we expect them to be on the order of milliseconds.
Okay, thanks.
Hi, this is Adam Dong from NRAO. I was wondering, you're looking at repeaters where, especially R3, which has 16-day period, so you know when it's going to come, you have radio. Is there any chances of like stacking many optical images on top of one another to find optical counterpart? And have you done it?
Yes, so it's very difficult because the optical background is also not very well constrained as we would expect. So we get events that we're still not sure what they are. That's also why we need simultaneous observations. I'm not entirely sure that we've done stacking. No. But I would say it's like in the X-rays, you're stuck in very rare photons. So the background is really something that you have to take into account. We are doing studies on how to take into account what's happening in our background, which is, as I said, very badly constrained in the open.
Thank you.
Okay. I think our next talk is online. Yep. Please thank the speaker.
Okay, Zhangxia, are you online to share a screen?
Yes, can you see my screen?
Oh, sorry, yes. Thank you. Yeah.
Okay, John is going to talk about self-absorption in PRS.
Go
ahead,
thanks.
Yep.
Can you hear me? Sorry?
Yes.
Oh, okay. Hello, everyone. My name is Chen Zhang. I'm glad to be able to give this online talk. So I will be focusing on some introduction and discussion of SSA of radio counterparts associated with the FRBs and its implications to FRB origin, with a special focus on the radio counterpart of FRB 2024-0114A. So we know as of yet, we have confirmed a handful of PRSs associated with the FRBs, and also some other candidates, including FRB 2019-04-70A, shown by Alex on Tuesday, and previous theoretical works by Yuanpei Yang et al. And observations support that PRSs are synchrotron emitting nebula around the FRB sources, for example, Magnetar wind nebulae or hypernebulae. In the past decade or so, despite a handful of radio spectrum of PRSs have been obtained, we still lack evidence of evolution and SSA in their spectrum. You can see here the plots show the spectrum of the compact PRSs associated with the FRB 2012-11-02A and 2019-05-20B. They both have a rather flat spectrum, but lack of a spectrum break in low frequencies. The precise numbers and their evolution are not clear and are also hardly achievable with even current VLBI facilities, therefore hindering more interpretation of their properties. So FRB 2024-0114A is an active repeater discovered last year. We first discovered the associated radio counterpart last year. Our observations and the VLBA observations from Bruni et al. Confirmed the compact nature of the source. In the upper plot, we can see the detection of a spectrum break at about 1.6 gigahertz, 6 gigahertz with VLA observations and low frequency UGMRT measurement given by Bashar et al. This is consistent with the SSA break. Combining SSA and equipartition arguments as shown with the orange and green thick lines in the bottom plot in this red circle, we can solve for the size and the B field strength. The size is 10 times more compact and the B field strength 10 times higher than other PRSs. This may indicate the source corresponds to earlier phase of FRB evolution and indicates a newborn FRB engine. As for B field configuration, we are able to investigate the line of sight B field strength. We have two solutions for DM. One is from the bursts. The other is from the energy density of the radio counterpart itself. We therefore constrain the line of sight component at least 3.4 times less than B equipartition value. For more moderate line of sight values, we can conclude that the line of sight value is much smaller, which points toward a point flux dominated outflow and a newborn FRB engine. Besides the peculiar spectrum we see here, the source also shows evidence of a radio flare. With the new observations taken early this year, we update the E-folding rise and decline timescale to just above 200 days, implying a compact nature of the source of less than about 0.2 parsec. With these timescales, we can compare them with that of some slow radio transients. As shown in the left plot, you can see the source is in the red circle in the space taken by the most luminous supernovae and the dimmest end of radio flares from low luminosity AGN. More interestingly, as shown in the right panel, the source tends to join the engine-powered supernovae. So I think more observations are needed to follow this source up to constrain the temporal and spectrum behavior. So I will stop here and thank you, everyone. I'm happy to take questions.
You have questions?
Hi, it's Bill. Could you go back 2 slides to where you showed this radio spectrum, please?
This one?
Yes. So you said that you think this is the synchrotron self-absorption break, but your low frequency spectral index is pretty shallow. How do you rectify that with it being self-absorption? Like, should it not be steeper, more like 2 or 2.5?
Sorry, 1.6?
No. The spectral index at low frequencies, you say there that it's
the low frequency is
0.7.
Yeah, 0.7 minus 0.7.
But at low,
low band, right? Low band, 0.9.
Yeah. But if it was self-absorption, would it not be steeper, more like 2 or 2.5 rather than 1? Like, how do you rectify that with it being self-absorption?
Because the spectrum is non-thermal and the brightness temperature is high, the source is compact, so we conclude it as a self-absorption rather than like free absorption process.
Okay, I'll message you. Yeah. Okay, don't worry. Thanks.
Okay, thanks, Robin.
Okay. Any more questions? I think we have to go to the discussion now. Okay. Yeah, let's say thanks. Yeah.
Stop sharing.
Right. Thank you.
Oh, yeah. Oh, slides. This one.
Yeah, we've had really nice discussions over Slack yesterday and today on some of the presented models, emission mechanisms, and so on. So this would just serve as a platform for others to join the discussion and take many unexplored questions forward. So we have three main questions that were presented to us by the organizers that we will moderate. Elias, who is online, and I will be will be sharing a few words about each of those questions, and then we'll open up the floor for discussion, just like what Jason and Miles did yesterday. We'll have 10 to 15 minutes for each question, and we welcome you all to chime in and share your controversial opinions. Hey, great. Elias, are you able to?
I'm here, Naveen.
Okay,
Can you hear me?
okay. Yes, we can hear you. Perfect. Are you able to see the slides?
Yes, we can see them online.
Okay, great. Thank you. Okay, so the broad idea here is to discuss some of the open questions, not only about the FRB mechanisms, but also potential engines that could power these emissions. Okay, so the first question is, can all FRBs be produced by neutron stars? And can all FRBs be produced by a certain type of neutron stars? This is motivated by, for example, the recent JWST follow-up studies that was presented today by Peter Blanchard. So it rules out isolated Magnetar for this 25O315A burst. There's a question already. Yeah. Sorry, go on.
Yes.
Yes, this is Calvin from UC Berkeley. Just wanted to point out that in this Blanchard 25 paper, they do calculate the probability of chance coincidence for the NIR1 source and its order unity. So it is order unity. So it could just be there by chance. Yeah.
Yes. Thanks for that context.
Yeah.
Yes.
So just to be super explicit, that first point is just wrong, right? It does not rule out an isolated magnetar. There could be an isolated magnetar there. It's totally fine.
Yeah, so I guess to be even more explicit, this statement that they rule out an isolated magnetar is the point that they make for NIR1 being too bright. So then the argument relies completely upon whether or not that FRB is associated with that infrared. Yeah, which is given the order unity, like
if the FRB is associated with this one, then it's important. But if you cannot be associated, agree, yes.
Great discussion.
Perfect. So if the FRB is associated with NIR1, then it rules out an isolated magnetar channel.
Just order unity.
Yes. Okay. Good. So the question is. Great.
Yesterday, there was a question about fallback disk and what kind of infrared emission they make. So maybe isolated magnetar, I don't know, could it have a fallback disk that's been hypothesized in the past? Maybe not totally ruled out. That's all I want to say. Thank you.
Great. So let's consider the cases where there are some other periodicities seen from some FRB sources. So, for example, periodicity seen from in the rotation measure of some bursts, at least claimed periodicities. So the question is whether we can conclusively establish the requirement of binarity in magnetar engines to produce FRBs, or whether we can observationally say for sure from some filters that a fraction of these FRBs do not have binary companions. Is that yes? So yeah, the first question is on binarity, whether observationally we can put some constraints on what fractions of FRB sources, if powered by magnetars, are a part of binary systems and not. There are some other post-galaxy properties and some other theoretical constraints, for example, based on population synthesis simulations, that suggest that of the order of maybe 10% of magnetars could be in binary systems, could be in binary systems. Can that be confirmed with FRB observations, potentially by JWST follow-up of nearby FRBs? Can that put some constraints on the theory? And we had a really nice talk by Junshuo Zhang yesterday on this hyperactive repeater, FRB2025 that has been emitting about 10 to the 47 erg or so, which is comparable to the magnetospheric energy in typical 10 to the 15 Gauss magnetars. So is that really a problem for magnetars, or can we circumvent that through some other channels? There were some really nice ideas put forth by Mr. Rauer and others on Slack yesterday. So is this really a problem or not? And do we need alternative scenarios? Are there any evidence for them? Are there any hints for alternative scenarios, say interacting white dwarfs or flaring black hole jets or whatever, and the observational constraints associated with them? Yeah, so these are the questions that we have for the first topic. Let us know your thoughts. Sorry, Elias, do you have anything else to add to this?
Okay, so I think one thing that, I think was already addressed largely yesterday. I think there's a lot of, I think, good synergy with those galactic mimickers, especially as you mentioned, the effects of binarity. Can you have like mode conversion in a companion magnetosphere? So I think even though the systems, as you say, may be different in terms of the physics that's operating, in terms of how relativistic they are, by and large, I think we can check for the existence of periodicity. And I think we'll see that also later in the discussion when we talk a little bit about other counterparts that we could expect, that we can use those systems to learn something. And I think that's something that I find also very exciting.
Mm-hmm. Any take on any of the points here? Do you want to add a few words?
So there's a galactic, is there already seeing University of Maryland, NASA Goddard? So there's a galactic center magnetar. Presumably there's magnetars in other galaxies near their cores. So do we see that? Why don't we see it? Is there some bias?
Yeah.
Shani, please unmute yourselves.
I had a question more for the theorists here, I guess, about this idea that the burst storms might lead to the magnetar energy being exhausted and there being a larger reservoir of magnetic energy deep in the core of the magnetar that can be brought to the surface. Is there any idea of what the limit on that reservoir might be? I mean, at a certain point, we're going to run out of that reservoir as well, right? Or is that thousands of times larger? I have no sense for that.
There's a limit on stability of the neutron star of about 10 to the 17 Gauss. So that's the physical limit, I guess you could say, of the reservoir.
Can that be tapped to produce FRBs or not? If it's all buried in the community.
I mean, that's an open, yeah, we don't know.
So, but that's 2 orders of magnitude. And then there's also the field volume, I guess, but that's not necessarily any larger than the magnetosphere.
Well, right. The limit is basically the gravitational binding energy of the neutron star, but a few like tens of percent or 1% of that is your magnetic energy reservoir that you could possibly ever tap.
Alex, feel free to unmute.
Yeah, I guess just on this point, all of the kind of estimates of how much energy you're depleting depend very sensitively on what your radio efficiency is. And currently, I think most of the works assume this is 10 to the minus 4, 10 to the minus 5. These constraints get much weaker if you have more efficient radio emission. So we know one source, SGR 1935, but we don't know whether fast radio bursts from hyperactive repeaters could be much more efficient in their radio emission, for example.
Yeah, I would just add that in that presentation, the field that was assumed was 10 to the 15 Gauss. And we routinely have measured through spin down, in the standard dipole formula, 10 to the 15 Gauss magnetic fields for some magnetars. And that's just the dipole component. So that really is just a lower limit, even for the surface on the field. So I think this point's really important.
Yeah. Also some comments for the energy budget for the magnetars. So even the hyperactive repeating FRB source 2024 0114 has shows maybe a challenge the energy budget for the energy budget of the dipole field of a magnetar, but there are still some free energy can store in the magnetar, such as the toroidal field can exist. So it can store much more free energy. So maybe more larger so I don't think it's actually the observation for the active repeater can actually challenge the energy budget for the magnetar.
Are there any inner magnetospheric emission models that can tap into the quadrupolar fields, for example, to produce FRBs? That is, if you run out of the 10 to the 15 or b square r cube, taking 10 to the 15 Gauss, would you still be able to produce FRBs by tapping the magnetic energies? Is that possible?
Do you have like a good model for to tap into the dipole like component of it?
Some might.
I'll do mine first. This is Robert Main at McGill. I just wanted to ask some people to maybe clarify, quantify some comments about there's a vast energy reservoir from the non-dipolar components or from the twisted fields. I would love to know is it a factor of a few? Is it an order of magnitude? Is it several? Could anyone answer how much energy there might actually be?
So is it safe to say that there is no prediction from the magnetospheric model so far on the amount of energy that can be tapped into FRBs? Could you take the
It would be some small fraction of the gravitational binding energy of the neutron star, right? So depends also on how efficient the radio emission mechanism is and how collimated or beamed it is. So it's the apparent versus the true.
So after this comment, we'll quickly take one additional comment on the issues with binarity, and then we can move on to the next one. Yeah, just after this. Yeah, Vicky.
So I also just feel, because he's not present, but there was a very well-known magnetar theorist named Andrei Belaborodov from Columbia University, who, if he were here, he would be quoting his paper from 2024 that says it's impossible to get FRB luminosities out of neutron star magnetospheres because those luminosities are damped in the magnetosphere no
Next
matter.
slide.
Yes, that's the next slide. Never mind.
Yes, Lauren. Wenfei Yu, can you unmute yourself?
Hi, this is Wenfei. Can you hear me?
Yes.
Okay. So actually, I'm talking about the 2024 01114A, and I would like to remind that the counterpart also, when we consider the energetics, we also need to consider the energetics for the counterpart, and that might be much larger than the bursts. And we have to consider that the source of that in order to understand the energetics for the repeater. And this one thing I would like to remind, we need to consider also the energy for the counterpart. The other thing is that, as we mentioned in some of our papers, we also mentioned that some kind of newborn sources that may be not that people, theorists usually consider, for example, just a magnetar or just a millisecond pulsar. But when we realize that maybe when the systems are newborns, then the situation may be more complicated. There's also additional energy in the system. So I think that might be, so I want to hear ideas from the theorists here and the possibilities. Yeah, that's what I would like to comment and ask.
Thanks. Would anyone like to comment on that? Yeah.
Yeah, I think before we
Could you introduce yourself?
We are from University of CS. Before we discuss the energy budget here, I think we should first consider several effects that may influence the energy budget calculation, such as the beaming factor, duty cycle, and effectivity. So a beaming factor also includes the individual beam factor and the global beam factor. So before we consider that, maybe the energy budget, the energy budget here, we calculate, we measure directly from the observation, maybe not the truly energy budget from it's not a truly physical energy budget here. So I guess the strictly upper limits for magnetar is the gravitational energy, the total gravitational energy here. So if one day we observe the FRB's energy budget is larger than the total gravitational energy, maybe we tend to maybe 10 to 43 or to 42 ergs. So it will be rule out. I think that will be rule out the magnetar case.
Okay. So just a final opportunity for anyone, if you'd like to weigh in on the effects of binarity. Yes, please. Marcus Lowe.
Hi, Marcus Lowe from Swinburne University. I guess a really quick comment on effects of binarity. I don't think I've seen it mentioned in this conference, but there is a system called the double pulsar. Some people may have heard of it. It goes, one of the interesting observational aspects of that system is that it displays eclipses, where one of the neutron stars gets eclipsed by the magnetosphere of the other pulsar. And when it goes through eclipse, we see some absolutely incredible propagation effects, especially in more recent high signal to noise meerkat observations. Some of which, could be related to what's going on in like FRB progenitors and tight binaries with like another neutron star, or some other stellar companion with a pair plasma filled or just plasma filled magnetic field. So I guess that's kind of also worth thinking about. And we have some really cool data from Meerkat on that.
Right. Agreed. Thank you so much. We will have to move on to the next next topic. Oh, there's Susana Araujo. Could you unmute yourself?
Hello, how are you? I was wondering regarding the multiple component of the magnetic field of Magnetar, is there some model or something that we can observe to be able to estimate the magnitude of this component? Because we can estimate the dipole component, but I haven't read anything about how to estimate the multiple component.
So I think we raised a similar question earlier, and I don't think we have a specific answer to that, except that we could tap in the buried magnetic fields somehow, and then buoyantly raise them out to keep replenishing the lost energy. Okay, if there are no other follow-up comments to that, I'd say we move on to the next question, which is related to what we have been discussing so far. There are a few more questions, but if there is anyone who has a comment on any of these questions, we can take, but okay. But we also have a few more slides to go on. Jason, or
So Brian Gainsler, UC Santa Cruz. Just on your fourth bullet there, just more on the whether these hyperactive sources can exhaust their energy. So I was just chatting in the Slack channel. So if these things are beamed, but there's just as many beamed away from us as beamed towards us, then I think the energetics will cancel out and the problem's there. But if these are pencil beams, then the energetics problem goes away. So the question for the polarization, perhaps the pulsar polarization experts, is does the rotating vector model that at least some FRBs seem to support, does that require pencil beams, or can it also work with fan beams? Because it seems that the energetics question really comes down to what shape the beams are. And if the polarization can say that the beams are pencils, then the energetics problem goes away. So I don't know if anyone has looked into this. I don't know much about polarization from fan beams.
Jason, do you want to respond to that with your question, comments? Or okay, it's unrelated. Okay. Jason.
So I have a somewhat different point. Sorry, Brian. I don't think I've heard anyone mention like the Jupiter-Io interaction at this conference yet. So Jupiter and Io have a magnetic interaction, and actually, sorry,
the electron cyclotron.
Yeah, exactly, and it's the only example of an object that is actually brighter than the sun at very low radio frequencies. It's the only object in the sky that is brighter than the sun, and is not true anywhere else in the electromagnetic spectrum. And we've seen from some of the LPTs that they're magnetically interacting, and we can see them to much larger distances, right? There have been a number of FRB models that suggest magnetic interactions of white dwarfs in very short orbital period systems. Like there's a Mottez and Zarka paper. I think there's a couple of them at least. Could well happen with neutron stars interacting magnetically as well. So yeah, I think it would be good if we are not so myopically focused on magnetar models,
Agreed.
because I think we have like evidence in our solar system and in our galaxy that this is not the only way of making coherent radio bursts. But I hear magnetars mentioned quite a lot at the conference.
Agreed. That was the idea of the slide. Whether you should think about
Okay.
it. Okay, I think we should definitely move on to the next slide, which is on which is related to what we have been discussing on what theory can provide. There have been substantial advancements over the last few years on numerically simulating the magnetospheres, on how waves can be launched, how waves propagate, what's the nonlinear steepening effects, and how certain particle energization method can happen, and so on. And there have also been advancements on these nonlinear propagation effects, high amplitude wave interacting with the plasma inside the magnetosphere. There have been some theories, for example, Andre's work that Vicky mentioned, that suggests that these FRB-like waves cannot escape from within the magnetosphere across the field lines. So there have been lots of advancements made, there have also been some advancements in understanding some crustal properties of neutron stars that Elias will take over very soon. Just quick comment on the top right panel. The weighting distributions, for example, from repeaters, they don't always follow a log normal distribution. So do they all arise purely from magnetar crustal quakes? Can the weighting distributions, burst arrival times, be used somehow to understand the magnetar crustal properties, or whether that could be used to discriminate the underlying emission surface, emission engines? Elias, would you like to add more to this?
Yeah, absolutely. So I wanted to touch on a number of points connected with this. I think you've seen throughout the conference in several talks, including Naveen's and Alex Cooper's talk this morning and many others, there has been substantial advancements, both in terms of the theoretical modeling of emission mechanisms, but also in terms of the global modeling of those systems. And two of the things I wanted to mention, and I probably just jump right to the image that we put there, is we can even ask a different question. We cannot just ask, what kind of emission mechanism can explain a certain observation, but also we can ask what actually at the source triggers the emission in the first place. And we heard a lot about this earlier today, about the impact of crustal physics. And what I wanted to show here, just to give you some example that this problem might be actually even more complicated than what we thought, is what would actually happen in this case, what is shown in the simulation, if we simulate a realistic star quake. So what's being done here is we took, this is work done by a visiting grad student here at Caltech, Louis Bernard, and also by postdoctoral fellow Ashley Bransgrove in Princeton, and myself. The idea being, we took a realistic elastic mode calculation for a star quake, and then we just injected that into a magnetosphere, because what we wanted to know is most of the insights in terms of, in part, both damping, but also in terms of those simulations of nonlinearity come from simulating individual pulses. And we wanted to know if we actually had a realistic event. So if the source in kind of an end-to-end modeling approach would tell us what exactly the injection is, what would the realistic feedback be? And what's shown in this figure is literally what that looks like. On the top, you see, basically you can think of that as being the alpha wave component. On the bottom, you can think of that as being the fast near-sonic component. And the situation is really complicated because effectively, if you think in terms of the talk earlier today, that there might be multiple chains of things being triggered, we basically see almost all of them potentially being active in the system. So we do see the formation of monster shocks, actually multiple of those. We do see the formation of current sheets. And large plasmoids, which you might be able to spot near the sort of equatorial plane of this figure. And even more so, after you have a continuous injection of all of those waves into the magnetosphere, you actually open up the dipole. So this is a non-rotating system, but then the nonlinear part rips everything open. And what you end up is a very complicated, twisted, distorted split monopole configuration. And on top of that, I think you would expect multiple of these mechanisms to operate. There's a periodicity in terms of the injection, and is really, really complicated. But on the other hand, what those simulations can also tell you, and I think there's a lot of opportunity there in terms of understanding what the source model can predict is not all of them have the same kind of energy in them. Even though you start with a fixed energy at your stellar surface, maybe only 1% ends up in the alpha waves, and a few more percent actually predominantly end up in fast waves. And so that, in addition to possible constraints observation, as we heard for those hyperactive sources, in efficiency of the emission mechanism, could give you a constraint of which one is favored and which one is not. So I think basically theory in terms of source modeling can meet also data right in the middle. So I think there's a lot of opportunity to be learned there, both in terms of, as we say, duty cycles, like at which point, can the system recover and then trigger another oscillation, or even if you have proper plastic modeling, or even if you model diffusion time of the magnetic field outside of the star, as we've discussed. And I think efficiency constraints there might also help a lot. And the nice thing is, what I want to say also on that slide is, this type of modeling has also been done for other systems as well. Like we had this question about Jupiter-Io interaction. And the nice thing is we can do exactly the same thing for the system, which actually for Jupiter has been very extensively studied, just because you have also strong observational constraints on the radiation belt dynamics. But also, for those systems here, we've done investigations of binary magnetospheric interactions for neutron stars, and you can put constraints on even what emission mechanism arises from the binary dynamics itself. So even the fact that, if you had a binary, would already constrain what kind of emission mechanism is favored from the dynamics. And so by kind of, studying the source properties, we can also get complementary constraints on those. With that, I hand it back to Naveen to handle the questions in the room.
So Jens, do you have comments? Yes.
Yeah, hi, I'm Jens Malmann from Dartmouth. So I want to add just to this beautiful overview. It's actually not just efficiency on the emission side, but also efficiency of the propagation. So even before that converts to gigahertz waves, there's a lot of exploration going on what kilohertz waves actually do in these intermagnetosphere, how they might be damped, how they might shock or not shock. So actually it's a multiplication of efficiencies, even if you focus on the emission.
Exactly. And the thing is, in this is a very good point, Jens, and especially in this simulation that we show, right? Even ripping up the magnetosphere, in this case, going from a dipole to this monopole, drains a lot of the injected wave energy. So overall, when we look at this, we have only efficiencies of less than 10% that actually ends up in the wave that can potentially escape or not, which is then the different question. But you lose out a lot of energy, even close to, to the nonlinear dynamics that Jens was mentioning. Yeah, that's a very good point.
Yun Hong, would you like to unmute yourself?
Okay, can you hear me?
Yes.
Okay, thanks. I want to follow Ilias' points to add 3 comments. So the first is, Ilias just said, we should not just care about what kind of model can explain something. I just want to add one thing is we should also check every models to look at what these models cannot do something. For example, just observationally from all kinds of diverse morphology, we see from the repeating FRBs, we know these FRBs are highly linear polarized, and the sunbursts are also highly circularly polarized, which means we need both X mode and O mode produced at the emission regime, of course. And we also see from repeating FRB, most of them are narrow spectrum, which means the relative bandwidth is extremely small. So this actually can put some very serious constraints, just like a scintillation. We can, based on scintillation to constrain the emission size, we can also use this bandwidth to constrain the different predictions from magnetosphere and shock. Second thing is, one thing we can do is based on different emission mechanisms to look at the efficiency of how many magnetic field energy convert into the radio. Actually, you will see different models really predict very different efficiencies. Just to look at the shock model, it's roughly 10 to the minus 3 divided by the magnetization. So larger magnetization you have, the lower efficiency you have, because the particle will take less energy if the B field is very high. But in this case, the sigma is very high. You will mainly produce a linear polarization. There is no circular polarization, and the flux will also drop. So this is like a drop back things. And you increase something, actually this will also cause you some very different observations. The third thing is propagation. After you trigger FRBs, can this FRB propagate? So I think this is related to two different questions. The first is like Andre calculated whether the FRB can escape or not. I also have a paper with Paul and Bing. We found as long as in the open field line region, the FRB is propagating nearly aligned with local B field, and as long as the plasma is relativistic moving. So we found the optical depths will drop. Okay, so this is like a one test particle, how this particle modify the cross section. The second propagation is just Navin mentioned, the monster shock. The fast mode, there is no monster shock for FN definitely, because E square is always smaller than B square. The MHD is always valid, but for fast mode propagation, just several weeks ago, the Alex Chen has a new paper on this topic. He found it's very easy to produce a monster shock at the quasi-perpendicular propagation, but as long as you the K is more close to the B, so you need to go to a larger distance to reach the E square rather than B square. And in this case, actually the plasma frequency is also dropping. So it's very hard to produce monster shock in the, they found a critical angle roughly at 50 or 60 degree. I don't remember correctly, but I still want to mention this. There is no problem in the open field line region. Okay, I think that's all I want to say.
Thanks, Yunhong. Yeah, so Yunhong's response was that FRBs could propagate along open field lines, but the okay. So yeah, there are a couple of other questions that are left here, which we can quickly explore before moving on to the next slide. Yes, Zoravar.
Okay, so I think we have to be a bit cautious of extrapolating what we know about normal magnetars to this sort of simulations. I think this is a force-free or MHD type simulation, right? And it's unclear if that's sort of like you could have a very vacuum-like magnetosphere, perhaps a very slow rotator or something just very benign, and then you have a quake, right? And in that case, you'd be very far from this MHD limit initially anyway. So I'm just wondering if these sort of MHD type waves is what will be actually realized in nature. Or maybe it'll be realized, but maybe this would not make an FRB. This would be something else.
Mm-hmm. And what's the multiplicity that you have in mind?
You would have basically a vacuum magnetosphere to start with, or something very very low charge density, and then you'd have a quake. So it's inherently a kinetic problem rather than MHD.
Yep. Thank you for that point. Makes sense. What specific predictions do observers want from theorists? Any quick predictions, especially from these kind of simulations of perturbing the magnetar crust, for example, or any other predictions from emission simulations that observers want from theorists?
One thing that I guess it hasn't really come up, but we found people have noticed some FRBs have microstructure, and some don't, and partly could be because of scattering. But there's cases where it doesn't look like there's there's not clear evidence for scattering, and yet we don't see microstructure. So I think, you know, why sometimes do we see that? We don't. Is that emission mechanism dependent? How often might we see that? Is that a geometric effect? There's, I think.
It could be a combination of many effects, I think, including these nonlinear propagation effects and the onset of various plasma instabilities upstream of the propagation of the FRB waves. So that depends a lot on the upstream temperature, magnetization, the luminosity of the burst, and the density, composition, and so on. So it's only natural that you do not see that for all bursts, and because you do not expect the conditions to be the same, and the properties of the burst are not the same. So depending on these luminosity, for example, or the wave strength parameter and various nonlinearity parameters, these instabilities could kick in, which could give rise to various temporal structures onto the bursts. I think that's right now on a theory front is very much under exploration, but anyone can add their thoughts on this, on Vicky's question on why we see these temporal structures in some bursts and not in others. These microseconds of structures and shorter, for example. Yes, Kenzie.
Hi, this is Kenzie Nimmo from MIT. Just to add to Vicky's point, I guess I have the same question, but also if there's time scales that are interesting, like for example, the circular polarization in some repeaters, you see it changing from 100% linear to close to 100% circular in short amounts of time. And then similarly with the microstructure, you see bursts that have it and don't have it. But yeah, that's on very short time scales. You see that change. And if it's propagation effects, do we expect it to change that quickly? Yeah, at what point does that start to become constraining?
Thank you. Yeah, good questions. Laura?
Yeah, I mean, as an observer, I would say everything, but maybe as a complementary dimension to what was just mentioned, I think all of these properties as a function of frequency would also be extremely useful. Now that we have these nice wideband receivers, we can not only probe sort of temporal dimensions, but also the frequency aspect of things like burst rate versus frequency. How does polarization change with frequency? How does time scale change with frequency? That's actually a pretty straightforward thing to measure. Things like this would be emission bands as a function of frequency is also a fairly straightforward thing to measure. So that'd be useful. So I forgot to introduce myself, Laura Spittler, MPFR.
There's one online question.
Yeah, I just had a quick comment. I just wanted to say that the predictions for IR luminosity to test with JWST imaging for nearby hosts might be useful. Maybe it could even like lead to a nice JWST TO proposal. So just saying, just wanted to put it out there.
Jason?
Yeah, Jason Hessels, McGill University. So regarding your question about predictions, I guess one thing that I wonder about is, you know, if we had radio telescopes to search for FRBs at 10 or 20 gigahertz or so, is that going to be a great boon for our science, or do we expect theoretically that the beaming fraction will become narrower and narrower, so the event rate goes down and down because these are shooting past the Earth instead of hitting it? Or could that be compensated by having just more energy at those higher frequencies? I haven't heard a lot of discussion about that.
That's a very good question. I definitely see that to be a low-hanging fruit. There are many emission mechanisms that put a strong upper limit on the emission central frequency, but there are other emission mechanisms that do predict millimeter wavelength, millisecond duration flashes. So I see that to be a worthwhile pursuit to constrain the emission mechanisms to. This may not be the counterparts to the FRBs, but these would be unique bursts that do not necessarily have radio counterparts. Okay, so
there's a written question online that I would like to read out. Not someone has written.
Okay,
Yeah. How is the high repetition rate of very active FRBs reproduced in these models? Does Brian at the back hear that? How is the high repetition rate of very active FRBs reproduced in these models? Anyone got a suggestion?
Well, I mean, I think the very active repeaters are somehow special, right? I think that's the only way, because they're super active, and it's some sort of observational bias that we see these very active sources, right? It's not like they're very common. So there's some, basically the argument is there's some sort of special magnetar, there's special configurations of the crust and the observer that in the magnetosphere that makes them hyperactive.
Elias, do you want to comment on this and then take over the next final slide?
Yeah, I can definitely like take it over. I think as Zorwa is saying, like it's a little bit hard to say these young magnetars can be very, very active. I mean, in terms of subpulse structure, as you can even see from like the elastic modes, I mean, there you might have some imprints. And I think in one of the talks earlier, we heard about like potential QPOs and hyperactive repeaters. And so there may be a connection, but that's something I think that can actually be tested from some of those models. And that's something that I think we definitely should do. And this sort of also brings us over to the final slide, where we are tasked to ask, what can we actually learn with different multi-wavelength or multi-messenger counterparts? Can they constrain directly some of the emission mechanisms? And I think already multiple people, I think throughout the conference and also just now, Yan Hong has also raised that point very well. For example, if we look at this particular event shown here on the right, which is very, very narrow in frequency spectrum, can that constrain the precise emission mechanism? Of course, the question is this in that case a propagation effect or not? And I think making the distinction of what's propagation, what's intrinsic, would help us definitely also for this one. Let's say where even the synchrotron maser mechanism has a very very narrow bandwidth and cutoff at higher frequencies. And then other things that we've heard and discussed, I think, in great detail is specifically X-ray counterparts and what we can learn from those, especially if we look at the galactic magnetar. We had a really great talk about the system where the thing has a lot of X-ray bursts, but then some of them might be special and maybe they have other properties that may better correlate with the FRBs or FRB-like transients observed from SGR 1935. And so the question is, what can that tell us? And I think one of the things that one could ask for those, given specific models, what's the ratio between the X-ray luminosity and the radio luminosity, which can vary very, very strongly and may help to constrain some of those models. We had a very good discussion initially about what we can do with optical counterparts, let's say from JWST, or other sources, or even in Alex Cooper's talk about how those can potentially place limits on the maser mechanism if we catch them early enough. So I think there's a lot of potential. And then there's like two things that we've heard briefly about. I can say a bit more about those as well. Those I think are more with should have more than one question mark. Some of these mechanisms can produce high energy neutrino emission. We just want to point that out. Like for the synchrotron maser, you could have from thermal synchrotron like a photon bath. And then if you accelerate some protons, you could have photohydronic processes and theoretically produce TeV or PeV neutrinos. The challenge is the efficiency for this process is even lower than let's say the radio emission. I think can be as low as 10⁻⁸. And so the fluency that you would see, let's say in ice cube, is well below the detection threshold. But in principle, some of those models could produce that. And then I think we also very briefly heard about cataclysmic models where if you were to associate a subfraction of the FRBs with things happening in binaries or even associated with gravitational wave mergers, bearing of course challenges with statistical associations between GRBs and FRBs, which so far have been unsuccessful. I think the question is, would that help constrain the emission mechanism? Actually, one thing I can say about that particular part is if you look at the binary dynamics giving rise to specific FRB emission, actually it turns out they trigger very specific different mechanisms throughout their sort of in-spiral time or their lifetime. And so in fact, if we were to see something, we could, I think, not definitely, but at least with high confidence, point to very clear suspects, because different from, let's say, the Magnetar case, not everything will happen in unison. There it's more like individual mechanisms that pop in at different evolutionary stages. So there, I think from the binary dynamics, we can learn something. And I think as we've heard in one of the suggestions, I think thinking about the Jupiter Io system as well, we can learn there, I think might help, I think with those binary models too. And with that, I think happy to open it up for more questions, criticisms, and suggestions on how can we use those tools, or even what instruments are needed, or what observations are needed to provide additional constraints that might help with the emission mechanism.
Thanks, Elias. We'll have just a few minutes taking a few comments on questions. Pawan?
Yeah, I just want to, this is Pawan from Swinburne University. I just want to circle back to a couple of points that were made previously in terms of repeaters, hyperactive repeaters being fairly rare. We've seen an explosion of number of hyperactive repeaters over the last year. It wasn't that they weren't there, and then we are seeing them now. It was purely new instruments came up, and therefore we started discovering more and more of those. So my question in terms of like, in terms of simulation, in terms of understanding a broad population of these sources, are there good simulations which are available in order to say how many of these sources could be possible in an ensemble of large number of FRB progenitors, and how can we sort of tie them down to emission mechanism if there is a way through just population synthesis?
So Robert has a comment.
I think Paz Benimini had a recent paper. He says that, or he found that the most active repeaters have a lower source density than less active repeaters. It's something like Zipf's law, which is like a law in statistics, or empirically, it's a law in like number of frequency of words, for example. It seems like the more active you are, the source density is rare. So you're seeing some sort of tail of a distribution is what I get from that. You're seeing a very active part of a tail or distribution.
Yeah, so one way to approach that is through this population approach that you just mentioned. But there's also this open question, I think, in the Magnetar theory community on how long it would take for the magnetosphere to get back to its original state that is required to emit multiple bursts. I think that's still a very open question within the Magnetar magnetosphere community. So these hyperactive repeaters, they put strong constraints on and challenge the different timescales that we have in mind for how long it takes for a magnetosphere to retain or come back to its position. Yes, an online, Yon Hong.
Oh, hey, I think my comments are follow Elias' several points. Is that okay? It's not about.
I would appreciate if you have just one or two short comments.
Oh, yes. Yeah, let me make it quickly. So since
thanks.
One important question is whether the narrow spectrum is coming from the intrinsic radiation mechanism or propagation effects, right? But the FAST telescope detected several thousand bursts, even several hundred bursts per day. Nearly all bursts, if we look at then use a Gaussian function to fit, the delta nu of nu is very much smaller than 1. And you will see each burst upper limit or lower limit is very different from each burst within millisecond time scale. I would say it's very hard for propagation effects to do this within millisecond time scale to change the absorption or some frequency to absorb the corresponding frequency. The second one is if we look at the shock structure, even we assume at each point is monochromatic emitting due to the high latitude effect, this will naturally broaden the spectrum, the whole spectrum. So the delta nu over nu has to be larger than roughly 0.58. So this is also contrary to what we see. But for the crust physics, this recent paper I wrote with Ashley, almost done. We just found the elastic waves propagation inside the crust. It's not like all frequency can escape from the magnetar. There are some lower limit, there are some upper limit related to some physics. And the final point is, I see this slide mention neutrino emission. And there are actually two papers. The first one is written by Brian Metzger. He calculated the shock to see how the P gamma interaction to produce neutrino. And the second paper is I wrote with my advisor Bing. We also calculated the if the P gamma interaction happening in the magnetosphere. We just look at the FRB2004, the galactic one. And since we know there's X-ray, so we can calculate how many gamma we have. But we found for 3 scenarios, magnetosphere, current sheet, or shock, the upper limit of the flux, the maximum flux is still below the ice cube sensitivity. So it seems there's no way to detect the neutrino.
Exactly.
It's roughly magnetosphere. It's roughly 4 order of magnitude
Exactly.
below the sensitivity.
Exactly.
Yeah, so it's not possible to detect ice cube high energy TeV to PeV neutrinos from extragalactic tens of megaparsec FRB sources. The one way is through galactic system, and if there's a 1806 like giant flare that also produces an FRB, and if the flare is propagating nicely along the direction of our line of sight, then that is the hyper optimistic scenario where you could expect neutrino signatures. Okay, great. So I've got nudges from the organizers that we are way past time. Thank you so much, Elias and the online participants. And thank you also. So we will continue discussions over lunch. And hi, Elias. Thank you so much.
Well, thank you, Naveen, and everybody.
Yeah, we couldn't spend some more time on this last slide because it looks like we ran over time.
Oh no, that's fine. I mean, I see we're already like almost 10 minutes over. But I think it was a really, really good and lively discussion.
Yeah. Thank you so much.
Well, thank you, Naveen. Thanks, everybody.
Bye. See you.
People are just a bit slow to get in, but we'll start in a couple of minutes.
Sounds good. Should I try sharing my screen?
Yeah, you can get set up. Okay, so Matt just introduced you, and it was so lovely. It was flowing, but we were muted. But please take it away.
Oh no. Okay, how's my audio, Amanda? Okay, so yeah, I'm Liam Connor. I'm going to be calling in. I'm going to be talking today about measuring cosmic baryons with fast radio bursts and all of the exciting extragalactic astrophysics one can do with these measurements. I saw this cartoon a couple weeks ago. It made me laugh. It also made me grateful to the organizers who have made it fairly seamless to just beam in and join remotely. Hopefully next year the international travel will be less fraught and I can join in person. Okay, so as you all know, cold plasma dispersion leads to this characteristic lambda squared dispersion sweep, where the dispersion delay is the line of sight integral between us and the source. And just to spell this out really explicitly, the free electrons that are causing the dispersion of an FRB trace the baryons. Most baryons in the universe are ionized. We think most reside in dark matter halos, and in between those halos in the intergalactic medium. And this gives us access to matter that's otherwise very, very difficult to observe directly, despite its outsized impact on things like precision cosmology systematics, galaxy formation, galaxy evolution, feedback, and so on. So this is a collapsed quantity for a given line of sight, for a single line of sight, without importing external information. You don't know what fraction is coming from the Milky Way versus the IGM versus the intervening CGM or the host and so on. Fortunately, for a large enough sample, each of these terms has a different probability distribution at a given redshift. And each of these has a different redshift dependence. So with a large sample, you can start to tease these apart. Now, a priori, the reason we don't know DM-IGM versus DM-CGM is because we don't know basic things like the fraction of the universe's baryons that are in the CGM versus the IGM. This is really central to the missing baryon problem. Some of you have seen this little animation before. This is just a line of sight simulated in illustrious TNG. And what you'll notice is that DM doesn't increase linearly on spatial scales of megaparsecs. It's kind of a series of discrete jumps. And I've chosen an extreme sight line where we'll intersect a galaxy cluster. And in this case, the intracluster medium will dominate the total DM. But it's worth keeping in mind that usually you expect DM to be a series of discrete contributions from filaments and sheets and halos. I always like showing this slide. This is the final sentence of Dunk's 2007 paper, where they say, if redshifts of their host galaxies are measurable, the potential of a population of radio bursts at cosmological distances to probe the ionized IGM is very exciting. Okay, so immediately they recognize that it's not just that FRBs are interesting by virtue of being cosmological and energetic and new, but they're also useful. So that paper was within 10 years of this famous Fukugita, Hogan, and Peebles paper in 1998, where they do a census of the low redshift baryons. And even when you're really stretching it, even when you make a bunch of assumptions about the plasma in groups, you still come up short. In this case, you can account for maybe 40 or 50% of the baryons you expect. And this is really what I would call the classic missing baryon problem. The fact that 50% of ordinary matter in the universe is missing, is unaccounted for. And so the question asks, can we empirically determine omega b at redshift 0 that agrees with the early universe measurements? Now, I'd like to propose a different framing where we kind of split it up into two different problems. The classic missing baryon problem, and then what you might call the strong baryon problem. And these are questions such as, what is the exact spatial distribution of baryons? What is their power spectrum? What fraction are inside versus outside of halos? What is the relationship between that gas distribution and feedback, whether AGN or supernova feedback? What does a galaxy halo connection look like as a function of mass? And then as Matt McQuinn pointed out on Monday, how do baryons at nonlinear scales impact precision cosmology experiments? I think this is probably our best chance, at least in the short term, of really impacting cosmology proper. So I would say since 2020, starting with the McCart relation, we have solved the classic missing baryon problem using FRBs. You sort of can't do it by other means because no matter how sensitive your X-ray telescope, you cannot image a void. And so the fact that FRBs are sensitive to all baryons means you really can account for the full omega B. We've started to chip away, take baby steps at the strong baryon problem, as I'll talk about later today. But really, I think the fun lies ahead. Oh, whoops. I think the fun lies ahead. The classic missing baryon problem is kind of amusing, kind of embarrassing, very important to address. But all of the messy, interesting astrophysics that come with the strong baryon problem are what we have ahead of us. Okay, let's dig a little bit more into the strong problem. So if you look at two simulations that have the exact same initial conditions, the same dark matter distribution, the same cosmology, and in this case, even the same collaboration, but you change the feedback prescription, you end up with very, very different gas distributions at redshift 0. So on the left is the original Illustris, on the right, Illustris TNG. The original Illustris had very strong feedback. TNG has sort of strong feedback. And by redshift 0, the boxes are almost unrecognizable as the same volume, okay? So distinct feedback prescriptions and star formation prescriptions lead to very different macroscopic gas distributions. So this is in addition to the fact that those baryons are extremely difficult to measure empirically. So it's not just that they're hard to observe, they're hard to simulate. Another way of looking at that is with gas fractions as a function of halo mass. So you can see that comparing 5 leading cosmological simulations, Eagle, Simba, Illustris, Bahamas. They sort of agree, they sort of converge at cluster scale halos, and that's because we're empirically constrained at those halo masses. Whereas below the group scale, you get these order 1 disagreements. Viewed from a different angle, the power spectrum, you get these order 1 disagreements if you look at the total matter power spectrum, normalized by the dark matter only power spectrum. So you really distill the impact of baryons. If you plot that as a function of K, you can see, again, order 1 disagreements between the simulations. In most cases, you have some baryon suppression, meaning there are smaller matter fluctuations in baryons than there are in dark matter, likely due to feedback. And this is really important for these very expensive, very powerful upcoming weak lensing surveys. These are billion-dollar, billion-euro experiments where you want to measure cosmological parameters to a percent, and yet you have these order 1 disagreements about the nonlinear distribution of baryons, which make up 16% of the matter in the universe. So my understanding is that surveys like Dark Energy Survey currently just throw those modes out. They don't bother trying to model them or to marginalize over them. They just say, we don't know what they're doing, so we're just going to ignore them. Wouldn't it be great if we, the FRB community, could measure this power spectrum, hand it to the cosmologists, and allow them to really make these precision cosmology measurements that they set out to do in the first place? Okay, going back to the kind of intellectual history of dispersion and dispersion before FRBs, this is a paper that I somehow missed in 10 years of working on fast radio bursts, or maybe I knew about it and forgot. Hadak on Sayama, 1965. This is the same Sayama of who supervised Stephen Hawking and Martin Rees and David Deutsch and all these people. The paper is called Proposal for the Detection of Dispersion in Radio Wave Propagation Through Intergalactic Space. And the basic idea was, and keep in mind, this is 2 years before pulsars were discovered. This is about 2 years after Martin Schmidt got a redshift for a quasar. And they knew that quasars fluctuated. They were time variable. So they said, maybe if there are short timescale fluctuations, you can actually measure dispersion from intergalactic gas. And they say you could measure this or else disprove these particular cosmological theories. They even have a little dispersion equation that you can see in the top right, although it took Steven Weinberg to correct this in his cosmology textbook. There's an error there somewhere. I also want to highlight that this paper is 1 page long, okay? Here's another set of papers, dispersion before fast radio bursts. Here they were saying, well, you know, we're going to have this extremely sensitive low frequency array, SK low. GRBs can come from high redshift, so maybe the radio afterglow will be dispersed by the ionized IgM if they come from sufficiently far away. So you can get a dispersion delay of 10 hours at 30 megahertz for an object at redshift 10. I also want to point out that at least the Ioka paper was 3.5 pages long, okay? In the same category of prescient short papers, McQuinn 2014. So at this point, we know FRBs are real. We have the Thornton sample. And he basically lays out all the things that we are currently doing today. These bullet points are not summary points that I've made. These are just sentences from the abstract. So it says, DM is quite sensitive to whether the missing baryons lie around the virial radius of halos or further out, which is not easily constrained with other observational techniques. The intrinsic contribution to DM could complicate things. So this is the host DM, of course, it's a source of noise. And then stacking analyses of 100 DM measurements would place interesting constraints. And finally, scattering may result from turbulence in the CGM. Again, noting this is a 4.5-page paper. I would point out that each of these bullets is now an active field of empirical science. These are, in some cases, as you'll hear at the end of this talk and later in this session, with actual detections. Okay. Prochaska in 2018 shows us the expected dependence on impact parameter for halos of different mass when you intersect a halo along the line of sight. I also want to point out that it's not the case that FRBs are the only game in town, far from it. There are all these other methods that are much older than fast radio bursts that allow us to go after the hot ionized plasma in the universe. But it's a little bit like the parable of the blind man and the elephant, where one is feeling the tail and one is grabbing the leg and one is feeling the tusk, and you're trying to make sense of the whole elephant. Even though you're with X-ray, you're kind of mainly sensitive to hot, dense halo gas because of this NE squared dependence. UV absorption spectroscopy, you're measuring metals effectively in the CGM, but not the full content of baryons. TSE, KSE, again, mostly halos. And these are really powerful probes, and they're getting more powerful every day, as we heard on Monday. But it really takes FRBs to measure the whole elephant. This is a blessing and a curse, of course, because you can't disentangle the different components. But it's a really powerful tool. And this was what McCart did, okay, in 2020. This is measuring the whole elephant with just half a dozen fast radio bursts. So I want to emphasize that the scatter in this relation actually contains a lot of information about some of these questions in the kind of hard baryon problem. The missing baryon problem was, can we measure omega B? The hard baryon problem is, what is their distribution? So I want to just emphasize that there's a lot of information in 1-point statistics. I was skeptical maybe 3 or 4 years ago, but when you're at the kind of level where you don't know anything, even a 10 or a 20% measurement is useful. So let me just show a cartoon that some of you have seen before. But the basic idea here is, let's start with the trivial universe, where you have no large-scale structure, no filaments, no host galaxies. You have a one-to-one mapping in this universe between redshift and extragalactic dispersion measure. So the slope of that curve goes like omega B times H naught times the fraction of baryons in the universe that are ionized. If we throw in intervening galaxies and assume that these halos are full of hot ionized gas, then you've injected some scatter, but because we have this cartoonishly smooth background IGM, you have a lower limit for how much DM you get for a given redshift. You have noise on top of that, which comes from the Poissonian intersection or non-intersection of intervening halos, but you always have this kind of minimum DM for a given redshift. If instead most of the DM were coming from the host, as we proposed very early on, then there should be no McCart relation at all, or it should be washed out heavily. If we have a more realistic universe like TNG 300, where you have reasonably strong feedback, you're kind of sloshing gas around, you have this homogenization process from the feedback, and you still end up with a kind of statistical minimum for how much DM you get along a given line of sight, because even if you miss all the halos, you still get a fair bit from the IGM. So in this scenario, about 4/5 of the universe's baryons reside in the IGM, and you have this pronounced DM cliff. If we have a baryon distribution that more resembles the dark matter distribution, where about half of the total matter is in halos, then we have a puffier distribution. There's more line of sight variance. It's a clumpier universe. You still have a DM cliff, but it's at a lower angle. It's a lower slope, as you can see, going back and forth. The way I think of this is kind of walking through a misty rain versus walking through a hailstorm. So When you walk through a misty rain, you always get pretty wet. And you get about as wet as far you walk, right? If you walk twice as far, you get twice as wet. Walking through a hailstorm is very high variance. You can get lucky and miss all of them, or you can get unlucky and hit a really big one. And that's the kind of scatter that you get in the scenario where most of the baryons are trapped in halos. This is shown explicitly by Kriti Sharma in a recent paper where she shows the relationship between these kind of McCart plots, these 1-point statistics, and 2-point statistics like the baryon power spectrum. So on the left, weaker feedback, like in Astrid, you get a lot of line of sight variance. There's more gas in halos. On the right, you have stronger feedback, like in Simba, where you have a more smooth universe, less line of sight variance, a steeper DM cliff. Okay, so what do we actually see? We now have of order 100 localizations, so we can start to test some of these ideas. If we extend the axes of the McCart plot, we get something like this. And if we plot over the sample as of, I think, January 2024, so already quite out of date, but you'll start to notice a couple things. The first is that we now have a high redshift sample. So we have FRBs going beyond redshift 1, indeed beyond redshift 2, which is extremely exciting. Didn't have time to remake this plot, nor should I have, I guess. But we also have low redshift FRBs spanning a total luminosity function or luminosity distance of 220. The other thing you'll notice is this unmistakable DM cliff. So there's nothing in our sample at that time below DM of 800 times redshift, which is remarkable. Like a priori, you did not know that it would be really hard to produce a redshift 0.6 FRB with a DM of 300. The universe could have been that way. But there seems to be this really pronounced cliff, which tells us that the baryon cosmic web is relatively smooth. At least some of the gas is outside or is expelled from halos, at least compared to the dark matter distribution. And when we fit a model to this, we find that 3/4 or 4/5 of the universe's baryons are in the IGM and outside of halos. So this is significantly larger than the fraction you'd expect if there were no feedback, where FIGM should be about half, roughly. So this indicates efficient feedback processes that can expel material or prevent gas from falling in the first place, which is in line with other measurements. So just to go back to this toy example, which is actually maximally conservative, this example where 50% of the gas in the IGM, and the IGM is perfectly smooth, that first cartoon that I showed you, you would have a DM cliff at roughly this angle, and just to overplot what we see, it's quite different. Okay, so if we import information from these other probes, like X-ray, the eROSITA cluster catalog, group and cluster catalog has 10 to the 4 objects. We now have thousands of SC groups and clusters. And so we can go beyond just saying IGM versus non-IGM, halos versus IGM, and actually partition the baryons into a complete baryon pie chart that looks like this. And this is in comparison with the state of affairs 10 to 15 years ago. This is from Mike Shull's paper. And there I'm including the baryons that could be directly measured, directly constrained. So now we've not only measured omega B, but we can actually partition the baryons into these different components. And what we see is in agreement with cosmological simulation. So if you turn off all feedback in Simba, FIGM drops down to below 60%. Whereas if you have all the AGN feedback and everything turned on, FIGM is north of 80%. And we're seeing a similar story from these other probes. So a recent cross correlation between KSC and Photo Z galaxies, I think Legacy, showed baryon deficient halos. I'm less inclined to try to interpret the X-ray data because it's so out of my wheelhouse, but my understanding is that the X-ray stacks also indicate baryon deficient CGM.
You've got 5 minutes.
Thank you. Okay, I might try to whiz through this real quickly, but these hints of strong feedback and large FIGM may help with the S8 tension in cosmology, just this basic idea of smoothing out the matter distribution. This tension comes from a disagreement between the inferred matter fluctuation amplitude from the CMB and what one actually measures with weak lensing. And I think you can do this without any new physics or breaking cosmology. You just have strong feedback and slosh the baryons around. We get a 10% measurement of omega B H70. It's hard to do better than this, actually, because the early universe measurements are measuring omega BH 70 squared. So you've got this H naught factor. So you can't do much better than 10%. Everything I just mentioned was totally agnostic about the foreground galaxies. And obviously, there's a lot of information in the large-scale structure that we can observe between us and the source. So FlimFlam is very maximalist about this. FlimFlam does these heroic spectroscopic galaxy surveys in the direction of fast radio bursts, and this allows them to do a full 3D reconstruction of the cosmic web towards those sources, and then use that as a prior on what you expect from the IGM component, the halos, and so on. Another method that you'll hear about in a few talks is by my student Mariam Husseini, where she's found one of the first detections of the large-scale structure using fast radio burst DMs. Her results seem to imply most of this is coming from scales much larger than halos, so likely from the IGM, not from the individual CGM of intervening galaxies. And we'll also hear tomorrow a very exciting result from Kiyo Masui's group. Hao Chen is going to tell us about the first detection in cross-correlation between unlocalized fast radio bursts in CHIME Catalog 2 and DESI Legacy Survey, the BGS sample specifically. So in the past 5 weeks or something, we've had the first detections of the large-scale structure with FRB DMs. These are the baby steps I was talking about before. And these will only grow more powerful with time, especially as we have more redshifts and we're able to subtract off the largest source of noise, which is the McCart DM. In the future, when we have many thousands or tens of thousands of FRBs, we want to move into a large-scale cross-correlation game. The most obvious one is spectroscopic galaxy survey, or some billions of photo-Zs from Rubin, let's say, cross-correlated against delta DM, so excess dispersion measure after subtracting off the McCart DM. And this will give us a cross-power spectrum that contains a lot of information about feedback and galaxy formation, and can also maybe help with this KSC tomography degeneracy. Another nice idea that Calvin Leung and Robert Reischke have proposed independently is cross-correlating weak lensing shear maps with FRB DMs. The idea here is that weak lensing is sensitive to all matter, dark matter, and baryons. The dispersion measures are sensitive only to baryons, and so you can kind of disentangle the contribution from feedback and from baryons. Here's a nice cartoon example from Robert, where he just shows what you get from Euclid in constraining the matter power spectrum with and without 10,000 fast radio bursts. And the point here is just that you can actually figure out what the feedback scenario is with the FRBs and allow Euclid's incredible statistical power to be used for the cosmological parameters that it actually cares about, rather than just constraining feedback. And we will have samples like this in coming years, thanks to CORD and SKA, DSA 2000. I would point out DSA 2000, if it's able to search the full field of view with effectively all baselines, could see something like 25,000 per year. This is a compute question. We expect to get localizations of 100 to maybe 300 milliarc seconds, thanks to the oversampling, the very good UV coverage, and an excellent PSF. The scary thing about having as much sensitivity as DSA 2000 and CORD and the square kilometer array is that we're going to find a lot of FRBs from really, really distant galaxies. So obviously, we don't know if the universe produces reionization FRBs, but it's worth noting that half of the DSA 110 sample would have been detectable at redshift 6 by the DSA 2000. So if such objects exist, we will find them, and this will give us a column to reionization. On the other end of the spectrum, there are these upcoming all-sky monitors, these enormous field of view aperture arrays that can see thousands or 10,000 square degrees continuously. These will find local universe events. Of course, the one that's trailblazing is BURST, but there's also CHARTS, which will be built in Chile. We are building the Coherent All-Sky Monitor, or CHASM, at OVRO, hopefully with the first on-sky data later this summer or early this fall. There's a cosmic antenna in China. And this is really nice because you end up in a scenario where you could find hundreds of FRBs within a few hundred megaparsecs. So when everything is coming from redshift 0.4, Follow-up is really hard. You kind of have no chance of detecting coincident X-ray emission or fast optical. And then also going after the CGM is hard because, as we've shown, it's really the IGM that's doing all the dispersion. However, if we had a local universe sample, the IGM doesn't contribute much. So we go from this scenario to this scenario, where really you just need to reliably subtract off the Milky Way's ISM, try to model somehow the host galaxy's ISM, and then you have this joint measurement of the Milky Way's halo and the host galaxy's CGM, which is a really clean way of going after the baryon content of Milky Way-like galaxies circumgalactic media. You may remember this paper by Vikram Ravi a couple of years ago where we found a local universe FRB 50 megaparsecs away whose total DM was lower than the value predicted by both NE 2001 and YMW. You'll hear more in the next talk from Ralph Konietzka, my student, about his amazing simulation work. This just shows what the sky might look like out to redshift 0.05, I think. So to wrap up, I know I'm a little bit over time. We've more or less solved the classic missing baryon problem using FRBs. And we've begun to take baby steps towards the hard baryon problem. So showing that FIGM is large, requires feedback, maybe suppression in halos from Ha Chen's work. We'll soon have huge numbers of FRBs, and where cross-correlation with other cosmological fields will be the name of the game. And I would just make a call that it's not just that we need 1,000 or 10,000 FRBs. We also need new theory, algorithms, simulations, and more expertise in non-FRB fields, in galaxy formation, KSC, and so on. This is happening, and it's led by mostly young people, Medlock, Sharma, Konietzka. But this work is really important. If you gave us 10,000 localized FRBs tomorrow, I don't think we could make much sense of it right away. We'll soon have a way of measuring the Milky Way CGM and host galaxy CGM. And with that, I'm more than happy to take questions.
Okay, we have time for a couple questions. You're next.
Hi, Liam. Thanks for the nice talk. It's Ilya in the process. I'm Ilya from Catholic University, Valparaiso, Chile. How does your constraint on FIGM and FCGM fractions change if you correlate your observed DMs with different simulations and not illustrious?
Yeah, this is a really good question. I mean, I showed Simba where you actually turn off fully all feedback and turn on different strengths of feedback. And you end up with distributions that we roughly expect. I mean, what we really need to do is do this in a simulation suite where you can turn all the knobs that you care about, where the volume is large enough that you can trust the cosmology. So something like Camel's 50 or Flamingo. But to answer your question more directly, we haven't done the experiment of turning all those knobs. But I would just highlight that we have P of DM given Z for different simulations with different feedback strengths. And I think our data sit in between TNG and SIMPA.
Hi, Liam. This is Rachel Darlinger from McGill. I was just wondering, you showed two scenarios with a DM cliff. How do you distinguish the DM cliff for the IGM and CGM so that you preferred one over the other?
Yeah, so I guess the point here is that when all the gas is in the CGM, you don't have much of a DM cliff, or at least it's at a very low slope. And that's because the DM cliff really comes from the fact that when you go through the IGM, you're guaranteed a lot of gas contribution because you're guaranteed to intersect 100 filaments and voids and sheets and everything. Whereas halos are small and they're easy to miss.
Great. Oh, there's an online question. Do you want to, Sunil?
Yeah, thank you. This is Sunil from UChicago Northwestern. Liam, great talk. So I guess this question goes back to the discussion session we had earlier during the conference, and in the use of photometric redshifts for the FRB hosts themselves. So I was wondering if you have a sense of how much better or how much worse we would be doing in, like, say, retrieving baryonic information from the McCart plot if we were to use photometric redshifts instead of spectroscopic ones. So I don't know if you had looked into that.
Yeah, I don't have a lot of intuition for this. I think if you're using photo Zs that are as good as legacy, in this stage we're at now, where 10% measurements matter a lot, like 10% measurements are good, legacy photo Zs would probably be just fine, honestly. That will maybe not be true in the future, but it's absolutely a question we can forward model and should do quickly. I mean, soon we will have all 50 million or 40 million spectroscopic redshifts from DESI, 10,000 FRBs, and of order 1 billion photo Zs. And so we need to figure out what to do with those data, basically.
Got it. Thank you.
Great. We'll do one more question from Lordrick online, and then we'll go on to the next talk.
Thank you. I'm Lordrick from UCSC. I feel like you answered half my question probably, but I was just wondering if we could.
Lordrick, I think your microphone's too far away because we can't hear you.
Okay, maybe I'll ask my question on Slack.
Oh, you came back just now. If it's a quick question, go for it.
Oh, okay. Yeah, so I was just wondering, so in terms of, I know how is a small payload is small and easy to need.
Unfortunately, you faded out, so I am going to ask you to ask the question on Slack instead. And Liam, please look at Slack for that question.
Sure.
I apologize, Lordrick, but I think the audio was too challenging there. Great. Let's move on to better understand how simulations are modeling our dispersion measure versus redshift. And so, Ralph, I'll let you take it away here.
Hello, can you hear me? Is the audio okay?
Perfect.
And can you also see me? I can't see myself, so I'm not sure if you can see me.
We see you and we hear you.
Okay, perfect.
Oh, sorry. We don't see your slides. We only see you.
Now you should see the slides as well.
Now we see the slides. Perfect.
Okay, perfect.
And we still. Thanks, Kayla. That's why we have you on the team.
Okay, am I good to go from your end?
Yep.
Okay, perfect. Hello, everyone. My name is Ralph Konietzka. I'm a PhD student at Harvard working with Lars Enquist and Liam Connor. And today I will be focusing on everything what happens between the origin of the fast radio burst and the Milky Way, meaning how is the cosmic web affecting the fast radio burst signal. And to this end, we will be using the illustrious TNG simulation suite, which simulates a box of the universe, a box of the cosmic web between the burst and us. And my talk will be structured as follows. I will first go through the methodology on how we can model fast radio bursts within illustrious TNG. From there, I will show how we can draw several different catalogs based on our technique, which then allows us to apply those catalogs to, for example, determine analytically the shape of the dispersion measure distribution function. So let's dive into the methodology. We have here a single simulation box of illustrious TNG, and what we would like to do is we would like to send rays through this box and then accumulate the electron density to get a measure of the dispersion measure. And once we have done so, and I will describe the details of doing that in detail soon, is we want to extend our measurement of a single box to several boxes to go to deeper and deeper redshift. Keep in mind that one single simulation box in the biggest TNG volume has a length of roughly 300 megaparsecs, while we want to go with a redshift of over 5 to more than 5,000 megaparsecs. So let's start with a single box first. And here we have to keep in mind that illustrious TNG is run on a Voronoi tessellation. So there's no Cartesian grid underlying the simulation, but this Voronoi grid. And if you want to know how much electrons were accumulated from the start to the end point here in shown in blue, we have to reconstruct all the line segments that were crossed within this Voronoi tessellation. And we develop an algorithm that does this on the fly, and I will outline the algorithm shortly. We first find for each cell, for the start and for the end cell, its cell generating point or its center, and construct this orange ray between the cell generating points. Then we can split the orange ray in half by a plane entitled E in blue. And if the blue cells were attached by construction of the Voronoi tessellation, the plane E would be the boundary plane between those two cells. But as the cells are not attached, the plane E gives us a new cell where we can identify a new cell center or mesh generating point shown in orange, and we can identify two new orange lines from where we repeat the algorithm recursively, finding new two blue planes that, as the cells are still not attached, give us two new cells, and we again continue. Now we are in the scenario where two cells are attached, here for example in the right. And by construction of the method, the blue plane is exactly the boundary plane between those two cells, and the algorithm stops here. Well, in this part of the algorithm, we have to go one step further to now find the last cell, and now we have reconstructed the entire Voronoi cell tessellation, in the sense that we got all the line segments that our ray crossed. So we have a good understanding how we can get rays for single simulation box, and now we want to extend this to higher redshifts. So we need more boxes. And the way we implement this in our method is the so-called continuous ray tracing approach. So we present this method where we trace rays under an angle through the simulation boxes. And here it's important to note that all the boxes have periodic boundary conditions, meaning that if you leave the box here, you enter in the same position in the next box. If you would trace the rays parallel to those boxes, you would go through the same structures over and over again. And to avoid this, we use tilted rays that then go over and over almost until infinity without crossing the same structures twice. And this algorithm is especially great because there are no gaps between the snapshots. And with this method, we address a problem in previous AstroSat-based approaches where the integration of the path integral was based on the trapezoidal rule. And this method introduced gaps between these different simulation volumes, which then lead to this distortion of the final dispersion measure distribution. You can adjust the mean of the distribution with this method, but not any of the higher moments. And I will now compare our blue continuous ground truth approach with the current approach from the literature, and we see across all redshifts, the trapezoidal approach heavily distorts the distribution, especially when we go to higher redshifts. And to analyze this not only in the distributional sense versus dispersion measure, but in the sense of the moments of the distributions, you see, as I already said, the mean is the same for both methods. The trapezoidal method basically accounts for the mean correctly, but any other higher moment, especially the standard deviation, gets changed by up to more than 50%. So it's really important to use an accurate methodology such that the width of the distribution is modeled accurately. And now having this implemented, we have a perfect methodology to now draw catalogs from AstroSat. And the advantage of this methodology is that we can trace rays with our continuous approach that reconstructs the Voronoi tessellation. We can trace rays on all angles of the sky, meaning that we can produce catalogs in the form of full sky catalogs. And I'm showing here our main full sky map integrated up to redshift 0.01. And you see how the voids in black are traversed by blue filaments and red halos. And it's especially important to note here that while the most fraction of the sigma arises from the filaments, the highest DM peaks occur within the halos that are highlighted here in red. And we can even zoom in using our pencil beam catalog in one of a patch of the sky essentially to see how the CGM around certain halos looks like in further detail. And if we now want to see how the structure was accumulated over distance or go even deeper in redshift, we can run our approach continuously and then see there's more and more dispersion measure accumulate. We see the foreground structure, the small modes fill up, and the higher we go in distance, the more the larger modes get accumulated until we almost see a fully blue sky in terms of dispersion measure at roughly redshift 0.5 and higher until we reach our final redshift of around redshift 1.3. And while we in all those runs so far have chosen one specific position of the observer, we can also rerun our approach with different observer positions where we locate ourselves always in Milky Way-like environments. So those are 4 different runs with 4 different start points of the observer. And we always make sure that we have a Virgo-like halo at roughly 16 to 17 megaparsecs from this Milky Way-like galaxy, as well as an Andromeda-like galaxy in the vicinity of the halo that we use as the observer. The Andromeda-like galaxies are roughly a megaparsecs away. And we see again wonderfully how the different environments give different snapshots of our local universe. And we can also trace those maps deeper in Redshift to learn how the large scale and small scale fluctuations change when we go to different Redshift slices.
You have 2 minutes left.
Thank you. All of these methods will be made publicly available. You can access them on this handy webpage. And now, finishing the catalog section up, I would like to show shortly one application of our methodology and of these color catalogs, namely what we can newly learn about the dispersion measure distribution function. In 2020, Marquardt introduced this normal power distribution, which is mainly a function of only the standard deviation, where the mean is intrinsically fixed by this X0 parameter. And based off that, Walker and Sharma in 2024 and 25 argued that maybe log normal distribution is a little bit better, and we now introduce a third approach showing them the so-called normal power 3-1 distribution, which is very similar to the Marquardt form, but we leave this mu parameter, which is for high redshifts, equal to the mean free and also change the slopes of the distribution. And with our ray tracing technique, we have now the tools to compare those distributions to each other to figure out which of them fits the best. And we apply an ensemble of distributions shown here in these other colors that I'm not talking about today. The main point is our proposed normal power distribution function gives a perfect match to the data, while the log normal and the distribution suggested by Marquardt are both not ideally matched to the data. They both are not able to properly constrain the high DM tail as well as the low DM tail. And this image is now shown at redshift 0.5. Even if we go to other redshifts, our normal power function, here shown in blue again, gives overall the lowest Kolmogorov-Smirnov statistics, which means it's the closest fit even across redshifts. So we've now found a distribution that only has 2 free parameters, and those general global shape parameters that fits the distribution function perfectly nicely across all redshifts and improves upon the earlier announced distribution functions. And with that, I want to wrap up saying, I have now introduced you this methodology of we can correctly ray trace rays through the illustrious G suites. We constructed several color logs from there and applied those color logs to a first problem or first analytical description of the distribution function. And with that, I'm happy to take questions. And if you would like to download and use the catalogs, feel free to access this QR code, where you will also find a Jupyter notebook that shows you how to plot the data, open the data, and also how to basically work with this new distribution function model that we proposed as an analytical description for the DDM distribution. Thank you.
Great, thanks, Rolf. Let's move directly to an online question from Isabel. Isabel, do you want to go ahead and unmute?
Yeah, hi, Ralph. Great talk and congratulations on the new paper. I had a question about your new proposed distribution. Do you have a physical motivation or an idea why the alpha equals 1 beta 3.3 works better than the previous Marquardt relation or the Kriti Sharma's
Yes. Let me share my presentation again. Can you see my slides?
Yes.
Perfect. So this new distribution accounts for the fact that the distribution function really wants a power law cutoff on the high DM end, which is not included in the log normal functional form, where it goes basically sharply down with an exponential decrease. And on the other hand, on the low DM side, you want to have an exponential rise that's not too strong. And the Marquardt rise here was a little bit too strong with this alpha parameter equal to 3. You want a little bit a shallower rise. And the reason then why a power law is a very nice fit, there's this idea that the high DM end is many dominated, as already showed from the full sky maps, by the halo part. So basically, the distribution function of the halos tells you how the high DM part looks like, and then also informs you how the shape parameter beta has to look like. While on the low DM end, it's mainly the filaments on the voids which shape the functional form, and then the form has to become more and more normal distributed, as shown in this figure here. So at redshift around 4 to 5, it's almost a perfect Gauss distribution.
Okay, thank you.
Great. Any questions in the room here?
Hello, this is Dylan Zhao from Stanford. Just looking at some of your diagrams by eye, even using this sort of tilted ray tracing trajectory through the repeated boxes, it kind of looked by eye that you would still, for the larger scale structures, kind of be overcounting these and hitting them more than once. So this may be just a function of how the diagrams looked, and it may not actually be a problem. So is this a problem that you have to worry about, and how do you deal with that?
That's a very good question. This was one of the core analysis parts of this work. It's not a problem, and we've checked for this with several different approaches. It's a matter of choice how you choose this ray, but if you choose this correctly, you can get along with that. And I'm showing here other approaches where you break those correlations that were introduced by the continuous approach using this so-called stacked ray tracing approach. You also rotate and shift the boxes, and those two approaches are consistent with each other. And we also tested what happens if you look in different directions on the sky, how these repetitions are imprinted, and we see that for more than 97% of all the directions on the sky, this effect does not matter. There's a slight bias, which you get around of that if you use plane parallel arrays, but even for the full sky catalog, up to not more than 2%, this is not a problem. Thank you for the question.
Great. Thanks, Ralph. Sunil, I do see your hand, but I'm going to ask you to ask the question in Slack, and we'll move on to the next talk. Isabel, do you want to unmute and share your screen?
Can you hear my voice and see the screen? The slides.
We hear your voice, see the screen, and we see you.
Okay, great. Thank you.
Is that correct, Kyo?
All right. Hi, everyone. My name is Issa Medlock. I'm now a rising fifth-year PhD student at Yale, working with Daisuke Nagai and the CAMELS collaboration. And I'm going to speak a bit about some of my previous work for the first half, and the second half is something that's more of a work in progress / a proposal. So to motivate everything is baryonic effects on cosmology and astrophysics. We all know that baryons have complex and wide-ranging effects on the physics of the universe, as many have talked about earlier, including on the baryon cycle and the circumgalactic medium, where all these processes such as outflows, accretion, recycling gas, and so on, are all shifting and moving baryons in the CGM. And then on larger scales, we have the larger scale structure. And if we look at, for example, the matter power spectrum, we see that baryons change the way the matter power spectrum behaves in relation to if we only had dark matter. And these predictions of how baryons affect both the matter power spectrum as well as the CGM gas distribution are hard to model. And even with simulations, they vary significantly depending on what subgrid models we choose to implement. So this video is from the CAMELS collaboration, and it's showing an example for 8 different subgrid models. In blue is the gas density, red is the gas temperature. As it evolves through redshift, just how significant these differences can be. And we call or usually refer to these simulations like SIMBA or Obsidian in the lower right, where the gas is being expelled much further as having stronger feedback than something like Astrid or even TNG in this case, which is a bit more tame compared to Simba, and Obsidian as having weaker feedback. So this is a really complicated issue, and we can't really directly observe the CGM and these effects because of how diffuse the gas is. So we really need nice probes. There are other probes like KSC and TSZ, X-ray, and so on, but each of those has their own caveat. And that's why something like FRBs is so exciting, something that is directly tracing the ionized baryons along their line of sight. And as people have shown before, from the host of the FRB to us, the FRB is picking up signal from everything in between, and that includes the DM host galaxy, contributions from the Milky Way, ISM, and CGM itself, but then also things in between, like intervening galaxies and halos, as well as the IGM, voids, filaments, sheets, and so on. So we get this number that encodes a lot of information. And as the video previously illustrated, depending on what simulation you use to make your predictions, you're going to get wildly different predictions. So this is why I've been using the CAMELS project. And the goal of the CAMELS project is to collect these sets of now tens of thousands of simulations, along with n-body simulations with different subgrid models. And these are all run with the same initial conditions, the same resolution, the same box size, in order to get them as close as possible and really be able to directly compare the effects of the subgrid models themselves. And in addition to just varying the subgrid models, within each subgrid model, they vary different parameters, including omega matter and other cosmological parameters, and then feedback parameters that describe, for example, the strength of supernova feedback or AGN feedback. And this results in a huge number, again, over 14,000 different simulations, each have slightly different physics. So you have this huge parameter space that we can look at. And in my prior work up till now, I've looked at the CAMELS simulations, specifically the first three that were available, TNG, Simba, and Astrid. And one thing I looked at was on the scale of the CGM, what do excess dispersion measure profiles look like as a function of impact parameter? And from that, we saw that initially we can see a pretty clear and distinct difference between what we see in a simulation with weaker feedback, such as Astrid, where we have these really boosted DM excess profiles, versus a model like Simba that has such extreme AGN feedback and really ends up pushing so many of the baryons out of the halo. We see these really suppressed dispersion measure profiles. And that, in general, was just indicating to us that FRBs are a really promising probe to be able to test the proximity to these different feedback models on the CGM scale. Another thing I worked on more recently was looking at the F parameter, or basically the spread at a given redshift in the McQuart relationship. And one thing we showed was that this F parameter pretty tightly correlated with the suppression in the matter power spectrum due to baryons with respect to if the matter power spectrum was only dark matter. And that's really exciting. I think it's more of a proof of concept that FRBs are a powerful approach to potentially doing this in the future. And recently, Kriti Sharma put out a paper with the new proposal for the log normal parameterization and a more in-depth look at the matter power spectrum suppression, which is really nice. So I think this is a really promising forward approach. But there's a big caveat to the work I've done so far, and then in general, any work that involves CAMELS. There's several, but the main one I want to focus on is the box size. CAMELS is a 25 megaparsec box size, which is way too small to properly capture cosmic variance in all the width of structures in the universe. So it's not something that we can use to actually apply to observational data. So this figure from Batten et al. 2021 really shows that you need a certain box size, I think at least 50 megaparsecs, but ideally more, to converge in the variance in DM, which is what you would need to properly measure something like the F parameter or whatever other statistic you want to use. So something that we've been working on is thinking of ways that ideally what we would want is a large number of really large cosmological boxes with, similar to camels, many different variations on cosmology and feedback, without having to deal with the fact that cosmological simulations are extremely computationally expensive and time-consuming. So I'm a member of the Baryon pasting project, which is led by my advisor, Daisuke Nagai. The Baryon pasting project's goal is to develop a simple physically motivated, computationally efficient analytic method for modeling baryons that is calibrated on both existing observations and hydrodynamical simulations. And what that means is that you would have an input of a dark matter only simulation, which is so much cheaper to run than a hydro simulation. And then based on the analytical model, which starts first from the center with gas and hydrostatic equilibrium with dark matter potential, and then adding different gas physics, it's a growing model. You can paste on where the gas would go and end up with a volume that contains both dark matter and baryons, which is much cheaper to get. And then from that, we can make predictable observations. And this has already been used successfully to create large-scale maps of the KSC and TSC effects. There are two main methods for this. Sorry?
You've got 2 minutes left.
Okay, thanks. There are two main methods that baryon pasting is done. A halo-based pasting, where we just have a model of how gas is distributed around halos and paste that on top. And here are examples for the TSC and KSC effect. And that one's very quick and works well for TSC. And then a more expensive model, which considers all particles in the field, including anything outside the halos, and that's pretty slow. And it works better for something like KSC, which is sensitive to the diffuse gas beyond halos, but that's still pretty expensive. FRBs, as many people have already talked about, including Ralph, depend significantly on the IGM. The number we get is very a large number comes from the IGM. So if we want to do something like baryon pasting for FRB observables, we need to have a good handle on what filaments and the IGM are contributing. So something that I've been working on in the last few months is developing a joint halo and filament model for baryon pasting to efficiently make simulated FRB maps, specifically working on a model for the filaments. Right now, we have two starter models, an isothermal model to model filaments, and another model that is based on halo self-similar collapse, but this is self-similar cylindrical collapse to describe filament profiles. And main work in progress right now is with Daniela Galarraga Espinosa, who is an expert on cosmic filaments in simulations, and we're working on refining the model and comparing to that to really bring it together. But basically, our main goal is to just develop this strong, robust model that we can then apply to thousands of different n-body simulations with different cosmology and different feedback physics to end up with many, many volumes of data that we can then use for FRB maps in combination with other observables. I think I'll end there with my conclusion slides. Thank you.
Okay, questions for Isabel? Rachel.
Hi, Isabel. Thank you for the talk. This is Rachel from McGill. I was just wondering if the pasting of the baryons affects the simulation based on how it could evolve to that point, or if it still works well.
Sorry, I didn't quite understand the question. So you're asking if the pasting impacts the evolution of the simulation following that?
Or the accuracy of the model based on the pasting in places where it hasn't evolved there?
The model it's applied at a given redshift snapshot, and the model has a redshift evolution as well to take into account for that. I'm not sure if that quite answers your question. But...
Yes, thank you.
Any other questions here in the room? Online? Calvin's got a question.
Hey, Isabel. Calvin here from UC Berkeley. Do you think that the N-body simulations, such as those that you're working on right now, or large-scale hydro, such as we heard from Ralph and Liam, are the way to go into the future for cosmological and baryon inference?
Yes, so I guess this project is not just intended for FRB purposes, although that's what I'm interested in primarily, but I think it's also just a way we're thinking of being able to generate more efficiently than having to run hydro simulations. Many models that could then also be run for inference and machine learning applications, and not just for FRBs, for other observables. Like it's already been done for TSC and KISC and so on.
Great. We'll take one more question online from Kriti. While she's asking, Shen, do you want to go ahead and set up?
Hi, thanks Isabel for your amazing talk. I just wanted to ask, so I think one of the other caveats of camels that I can think of is that it does not fix other observables while varying feedback. For example, the stellar mass function or say galaxy star forming main sequence, which are already very well understood. So is there a way to include that in ongoing or upcoming camels projects, or for example, in your baryon pasting algorithms?
So from the Camels project, from what I understand, their goal isn't exactly that every simulation or every volume is actually realistic. They're just going for like the most extreme range possible to look at all that. But I do think you're right that it's important that the volumes or the information we actually use is able to match observables that are well known. But I think we haven't fully thought about how exactly we're going to do that yet. But that's a good point. Thank you.
Thanks.
Great. Let's thank Isabel again. And the next speaker is Xian Andrew, and she's going to tell us about selection functions for the outriders.
It's fun.
Yeah. Should fit under your ears.
Wait. Can everyone hear me? I think so. Is it on? Louder? Okay. Can everyone hear me now? Yeah.
Louder.
Okay. How about now? Okay. Sorry about that. So my name is Xian Andrew. I'm a PhD student at MIT. And today I will be talking about the importance of selection effects in large-scale structure studies and how that relates to CHIME and CHIME FRB outriggers. All right, so what we want to do with FRB DMs is we want to use these DMs to tell us about the spatial distribution of electrons in our universe. And as has already been mentioned today, one way that we can quantify this is with the electron power spectrum measurement, which just tells us how much electrons are clustering on different spatial scales. And here is a comparison between Illustris and Illustris TNG. And as Liam has already said, these two simulations are more or less identical, except they model feedback differently. And based on these electron power spectra, you can imagine making this measurement to constrain different models of astrophysical feedback using whatever combination of hydrodynamical simulations that you want. So unfortunately, we don't have an infinite number of FRBs at an infinite number of redshifts. And even though in the near future, like as in the next decade, we might have thousands to maybe even tens of thousands of FRBs with redshifts, we won't have the millions to billions that are needed to reconstruct this underlying electron map with high fidelity. So when it comes to doing 2-point statistics, we really have a sparse reconstruction problem. But one thing that you can do is you can cross-correlate your FRB DMs with another tracer of matter for which there's an abundance of measurements. And that gives you a boost in your signal to noise. And that is really one of the main motivations for cross-correlating FRB DMs with foreground galaxies. And now the power spectrum measurement you get is an electron galaxy power spectrum measurement, which tells you about the relative spatial distribution of electrons and galaxies, which you can still use to constrain feedback. All right, and finally, because the DM is an integral of the electron density along the line of sight, what we really measure with real data is an angular cross correlation, which is just an integral of the electron power spectrum over redshift. But it turns out that if you have redshifts for your FRBs and you choose to cross correlate your FRBs with galaxies that are strictly in the foreground, you can measure this electron galaxy power spectrum measurement directly. And intuitively, this is just because only the component of the electron density that's co-located with that foreground galaxy will actually correlate with those galaxies. So you kind of extract that electron galaxy power spectrum slice for free. And it's really worth stressing that this is why we want to do this kind of measurement specifically with a large sample of FRBs that have redshifts. Because if you don't have redshifts, you can't enforce the condition that your FRBs are strictly in the background of the galaxies you're cross-correlating with, in which case you can't get the electron galaxy power spectrum measurement unless you model your FRB distribution in some kind of way, but that inevitably introduces error into your measurement. And then, as Liam said, the other big reason why FRB redshifts are nice is because you can remove this distance DM over density degeneracy by just subtracting off the Makar relation. Okay, so there's already been variations of this galaxy DM cross correlation measurement done in the literature with real data. So for example, Hao Chen has a 5 sigma detection with 3,000 FRBs from CHIME catalog 2, although those don't have redshifts. And right now, the number of FRBs that do not have redshifts far exceed the number of FRBs that have redshifts by about an order or two in magnitude. But even with just 60 host localized FRBs, there's been a 3 sigma detection with a galaxy stacking analysis. And I think Miriam's going to talk about that later today. So there's really a lot of power in these FRBs that have redshifts. And in the near future, we're going to have many more redshifts with CHIME FRB outriggers coming online, as well as many other next generation telescopes. So an era where we can make this galaxy DM cross correlation measurement with more and more precision is truly imminent. But of course, it doesn't matter how many FRBs we have if there are unaccounted for selection effects that significantly bias the measurement. So for an Outrigger's localized sample of FRBs that also have redshifts, there's multiple levels at which selection effects can be introduced. So there's the CHIME detection system itself. This is modeled with hundreds of thousands of injections. Kyle talked about this on Tuesday. There's also the fact that we only Outrigger localize a subset of all of CHIME detections. And of that subset, only a subset of that subset actually gets a redshift measurement because of optical selection effects. So when it comes to this specific measurement of cross-correlating FRB DMs with foreground galaxies, it turns out it's useful to think about our selection effects spatially. So that's to say it's useful to think about selection effects that arise due to observables that are local to the FRB itself and its host galaxy, and selection effects on observables that arise kind of along the line of sight. So when I say FRB local, I'm referring to selection effects like optical selection effects on the host galaxy itself. So how bright is the host galaxy? How large is the host galaxy? This also includes the DM or the host contribution to the total DM and the host contribution to the scattering measurement, as well as many different burst properties like the intrinsic burst width, the spectral index, etc. But those observables are not expected to correlate with the foreground galaxies. So the expectation is that those FRB local selection effects will not bias the measurement. But what can bias the measurement are selection effects that arise within the galaxy foreground redshift shell. So this includes DM-dependent selection effects. So for example, if you have a DM-dependent selection effect that makes you unable to detect FRBs beyond say 300, you can imagine missing sightlines that are tracing really large electron overdensities near your galaxies that you're cross-correlating with, in which case you would underestimate the extent to which galaxies are correlated with electrons. And this also includes observables that may be correlated specifically with the DM overdensities within that galaxy foreground shell, like scattering if you're observing your FRBs at a high enough redshift. Okay, so we can test the effect of these selection biases using ray tracing simulations. And this was work that was done by April Cheng, who's a PhD student right now at Princeton, as well as myself and Hao-Chen Wang. And what we did is we simulated a sample of FRBs. We ray traced them to get the DMs and then cross-correlated those DMs with galaxies. And we just compared the angular cross-correlation measurement with and without selection effects. And these FRBs were at a redshift of 0.4, and there were about 3,000 of them. So the first thing that we did was tested the effect of optical selection biases. So on the bottom panel here is the actual cross-correlation measurement. Without the bias is in white, and with the bias is orange. What we did is we just removed all FRBs originating from galaxies that were fainter than a magnitude of 20.7, which is a pretty aggressive optical magnitude cut. And here in the middle panel is the ratio of the two cross-correlation measurements, which is like completely consistent with one. So in other words, there's no bias that's introduced by optical selection effects, which is expected. So we also played around with the spatial placement of our FRBs on the sky. So we compared the cross-correlation measurement for FRBs that are kind of uniformly distributed over the sky to FRBs that preferentially traced galaxies with high star formation rates. And this also doesn't bias the measurement. So the cross-correlation measurement is really insensitive to the underlying FRB population that is measured. But what does matter are DM-dependent selection effects. So here, what we've done is place a pretty aggressive DM cutoff at 600. So don't see any FRBs with DMs that exceed 600. And if you look at the middle panel, the amplitude is suppressed by over 50% at small scales. So at least according to Illustrious TNG, the majority of the signal that we see in our cross-correlation measurement, it comes from a small number of FRBs with really, really high DMs. So it's important that our selection function doesn't remove those main contributors to the signal. And the good news is that if we place the actual time DM-dependent selection function, we don't see much amplitude suppression. The caveat here is that this is specifically for a sample of FRBs that are at a redshift of 0.4. So you can imagine that if you were doing this with FRBs at a much higher redshift, the overall DM distribution would shift upwards, and you would be removing some of those really high excess DMs with your selection function. But at least for a local sample of FRBs, it seems like we're okay. Okay, so finally, what about chime outriggers? We just came online, and we have yet to fully characterize our selection functions, even just our DM-dependent selection function, because the system is still kind of in a state of flux. But to kind of give you a sense of what we expect, this is our recovery fraction. So how many FRB triggers are we able to successfully localize with the full outriggers array as a function of DM? And it seems like so far we're doing pretty good, at least up until a DM of 1,000. So what happens beyond 1,000 is our baseband buffer gets cut off, and we only have access to a fraction of our band. In general, the VOBI astrometry gets worse the less bandwidth you have. But the other thing is our RFI bands don't necessarily overlap at each site. So even if we have 100 megahertz of bandwidth that's accessible at chime, we might not have that much bandwidth accessible at the outrigger sites if there's RFI contamination there. And the good news is that we're getting a baseband buffer upgrade, which will kind of remove a significant portion of this DM-dependent selection function, at least up until a DM of about 2,000 or so. There's other efforts that we're making to improve our sensitivity and kind of mitigate our selection effects, and Matthias will talk about that tomorrow. All right, I think I'm running low on time, so I'll just leave my conclusions here and take any questions now.
We'll start here. I'm going in anti-seniority order. Thank
you. I was wondering, you showed this important bias for the DM cuts at high DM, but of course it's hard for a telescope not to have a similar cutoff at high DM. So I was wondering if you properly characterize your selection effect on the DM, can you avoid the bias that results from that?
You could forward model it. Yeah, but which would be harder? Because you would have to do that for every simulation you're testing with. Yeah.
Okay, so it will be dependent on a simulation. That's what you're saying.
Thanks, Hyun. I think this is super cool. I was wondering whether you have some thoughts or you guys have thought about cross correlations with other tracers that are not galaxies. For example, intensity fields, intensity mapping, or UV background, things like that.
I haven't, but there are people who have. Calvin's thinking about doing this with lensing surveys, so I recommend talking to him.
Thanks.
Great. We'll do one more question. This must be a plant.
Oh, it's just you mentioned intensity mapping specifically. Intensity mapping is often hard for observables or line of sight integrals. Typically, they don't correlate because intensity mapping loses what are called the low K parallel modes, which are the ones that that contribute to those line of sight integrals. So those are generically.
Okay, let's Sean again.
Oh, hey, I'm here.
Great. And our next speaker is Yi Liang, and they're going to talk about cosmological parameters from persistent radio sources. And you've got 3 minutes and 2 minutes for questions. So I'll give you a 1 minute warning.
Okay, can you see my screen and hear me well?
Yep, all three.
Okay. So good morning, everyone. My name is Zhelang Zhang, a PhD candidate for UNLV. I'm very happy to have this chance to share our recent work about using FRB PIS system to do cosmology. Here's the outline of my talk. First, a short summary of PIS, and then I will introduce a very elegant model about the PIS, this so-called the luminosity IM relation, but I would like to call it the Young relation. Now, since we can obtain the intrinsic luminosity from a direct observable, that is RM, we actually have a standard candle. And in the third part, I will show you how we use such a relation to do cosmology. I'm not going to repeat the words about what FRBs and how they were discovered, since already have many sorrowful and wonderful talks from Monday to today morning, from history to current status. Now we have 4 confirmed PRS source until Tuesday and 2 PRS candidates from CHEM, Outrigger, and BLA. Yet I'm very happy to hear from Bororina's talk Tuesday about using the EVN to confirm the 5th PRS system. So except we know the PIS are compact and steady, we also know their spectrum are non-thermal. They are more likely some kind of synchrotron radiation. So in 2020, Yuan Peiyang, Qiao Chuli, and Bin Zhang proposed a generic relation for synchrotron nebula. They refined their paper in 20 and 22. Here is the basic picture of their pitch model. There is a synchrotron nebula and a central engine of FRB. When the pulse of FRB pass the nebula, it will take DN and R information the nebula. Now, the key idea is in the nebula, you have 2 different electron population. One is the thermal electron, another one is the non-thermal electrons. And the break Lorentz factor is called the gamma thermal here. And then the thermal electron will contribute the Rn, and the non-thermal electrons will dominate the radiation of the PRS. there's a factor of fraction or fraction zeta E here, which is the ratio between the non-thermal electron and the thermal electron. We add the emission from all the non-thermal electrons, we finally get the luminosity of PRS. We then can eliminate the number density here and the magnetic field, and to get the relation of between the luminosity and the Rm. Okay, as you can see, this elegant Young relation can expand the observation very well, at least like few weeks ago. There is a new non-detection PRS of a very high DM, a very high IN FRB from the ATEL. So, but further follow-up observation are needed. Anyway, let's assume this Young relation still work at least at this moment. Now, if we invert this relation and remind that IM of FRB is a direct observable, that means we can predict the intrinsic luminosity from an object in the universe. That means we can use FRB PRS system as standard candle. And if we expand the luminosity by the flux we observe, and if we know the Rm flux and the redshift, and plus this combination of this constant zeta, gamma, and R square, we can know the Hubble constant. But now there's actual things. We actually don't know this coefficient 1 over this 1 over zeta or something. In order to break the degeneracy between this coefficient and Hubble constant, we need an actual observable, which choose to use the DN. By some simple algebra manipulation, we finally get a very ugly relation about this coefficient here. And if you are interested in the detail, please refer to our work. The archive number is here. Now we have a framework about using PRS to do cosmology, but the sample size is very limited. Except using the observation data, we decided to do some Monte Carlo simulation to generate some MOOC FRB PR sample to test our idea. Among this MOOC sample, the gray point here, only the blue point above the detection threshold can be observed, and we can assume the distribution of that coefficient. Now we have the MOOC sample. Our strategy is the two-step MCNC fitting. In the first fitting, we can constrain the coefficient zeta and gamma square and R square, and we can use the posterior distribution of this coefficient as the prior distribution for the next MCNC fitting, and we can finally constrain the Hubble constant. We can see here we successfully recovered the inject Hubble constant from the Monte Carlo MOOC sample. But for the real PR sample, we are not able to give a very good constraint about the Hubble constants since we only have 6 samples. Okay, here is the summary of my talk. I'm ready to take any question online or on Slack. Yeah.
Okay, unfortunately, we don't have time for questions on this one. So please put your questions in Slack, and Zhang, you can monitor Slack there. The last talk of the session is the measurement that was talked about earlier. So Miriam, I'll let you take it away here. And you've got 3 minutes. I'll give you a 1 minute warning. I want you to have questions, so don't go over.
Hi, everyone. My name is Mariam Hosseini. I'm a graduate student working with Liam Connor, and I have about 200 seconds to talk to you about my science. So I better get to it. I am interested in the relationship between DM and large-scale structure, and more specifically, I try to do a stacking analysis in which I stack the DM as a function of the impact parameter of foreground structure, or like the galaxies in front of the FRB. But that doesn't, I don't know if that means anything to y'all. So let's go over what I did exactly. My apologies for the subpar art. I'm not much of an artist or a PowerPoint maker. But so we have the FRB coming in from the far right. That would be here. And we have us on Earth over here. It's not drawn to scale. And then we have all the galaxies that are in front of the FRB. Every time the FRB crosses close to a galaxy, it picks up a little bit of DM, it passes through a little bit more material. So we measure the distance between the line of sight and every galaxy that is in front of the FRB. And one satellite is not going to tell us much. So we do this for every single FRB that is in our sample. And then we make this plot where, like, in the x-axis, we have bins of impact parameter. That's the distance between the galaxies and the line of sight of the FRB. And on the y-axis, we are going to plot the excess DM for every bin that any FRB contributed to that bin. What we would expect is that, so for a plot like that, we would expect that at smaller distances, we're going to have a bit of a little bit more DM because excess DM, because we expect if a signal is passing through the virial radius of a galaxy, it'll be going through more gas, so you're going to have more DM, and we would expect it to fade quite quickly after the virial radius of the galaxies end, so at larger scales. We see something surprising. I'm gonna pretend that the surprise hasn't been spoiled in previous talks. We don't see the signal fading quite as quickly as we had expected. The signal actually persists a little bit longer, up to megaparsec scales, which is far beyond the virial radius of most galaxies. So that is an indication that most of the excess DM, or at least some of the excess DM that we're seeing, must be coming from the IGM. We tried to test this with a simulation. So we run a similar analysis on TNG 300, and it's illustrated, unintended, on this plot that the halos, the contribution from the halo, that would be the yellow line on this plot, decays about as fast as you'd expect it to, but the IGM contribution to excess DM kind of persists longer than we had been expecting it. And then one last thing, I want to show you a special subset of the FRBs that we have. These seem to not be crossing any halos on their way to us, and we try and analyze it and get a value for FIGM, or the fraction of the baryons that would be in the IGM. And we get that at least 69% of the baryons are residing in the IGM. If you want to read more about my methods and the results, you can scan the QR code and read the paper. But thank you so much for listening to my talk.
Great. Questions for Miriam? Brian?
Hi, Brian Gainsler, UC Santa Cruz. Have you looked into whether your DM fall off matches the RM fall off that people are starting to see with background sources?
That's very interesting. We haven't analyzed that yet, but that would be cool to look at.
I can talk to you in the break.
Yeah, that sounds good.
And for one more question. All right. Cosmology.
Matt McQuinn, University of Washington. A really interesting result. I guess I didn't catch which sample you were using, and I also was interested. It looked qualitatively like the IGM with and this larger impact parameter extent, which really interesting that you find like will match. But I wasn't sure if quantitatively it was able to explain your signal.
Quantitatively, as in.
Yeah, or if you plot the curves on top of your measurement.
The simulation curve on top of the sample.
Yeah.
Oh, yeah. We can. I don't think we quite did that. But yeah, also I'm a big fan of your work.
And actually, very, very appreciated. What are the? Is this? Is this chime FRBs or?
It's. I'm so sorry. It's almost like everything but chime FRBs. But it's 61 FRBs that are localized, mostly DSA, some ASCAP. And again, there's a table in the paper.
Awesome. Oh, I'll check out your paper. Yeah, that's super interesting. Thank you.
Yeah, thank you.
Okay, that closes out the session. So let's thank Miriam and all the speakers again. And coffee's served in the back there. You're so strict. You're so
Hi. Can you hear me?
Do it again. Go again.
Can you hear me? I'm just testing out my audio.
Yeah, that's way better. That's totally fine.
Okay, cool. Thanks.
Cool, thanks.
Hello!
Okay, thank you.
Oh, shit.
Do you need this?
Do I need this? Welcome everybody to the continued session on CGM and cosmology. Next up is the lovely speaker Stella Hawker, who's going to be talking to us about probing the CGM microphysics with FRBs and quasars. Give it up.
Give me a pocket. I feel pretty sure. Is this okay? Okay. Hopefully you can hear me. Okay. Okay. So today I will be talking about how we can leverage FRBs in tandem with other probes of the CGM, namely quasars, to learn more about the fundamental processes that are regulating multi-phase structure in galaxy halos. So as we've seen numerous times so far, foreground halos are very common along lines of sight to FRBs at greater than cosmological distances. But the contribution of these halos to the observed DM and scattering is debated. On the one hand, we see from the precisely localized FRBs that their pulse broadening and scintillation tends to be dominated by the interstellar media of their host galaxies and the Milky Way. And based on scattering budgets that are currently available for FRBs, we think that scattering in the CGM is largely negligible, although there are studies that suggest CGM scattering could become more significant at higher redshifts. However, there are also studies that suggest you could have significant scattering from the CGM, either generically due to the ubiquitous presence of cool gas or under special conditions. For example, Jacob recently led a nice paper showing that a highly scattered FRB detected by DSA 110 may actually intersect a high velocity cloud due to the rare overdensity of halos along its line of sight. So altogether, it's really unclear whether the scattering we currently observe from FRBs could have any plausible origin in the CGM, and more broadly, how to interpret the distribution of FRB scattering in the context of CGM physics. So today, I'm going to tell you how we can empirically predict the amount of scattering that occurs in the CGM using quasar observations, and thereby demonstrate how we can contextualize the scattering we observe in the landscape of other CGM probes. How do we do this? Well, it turns out that turbulence is actually observed in the CGM now, and where there is turbulence, there can also be scattering. So the first main way that turbulence is actually observed in the CGM, and arguably the most direct way, is through integral field spectroscopy, or IFS, of CGM emission around bright quasars. So how this works is that you have a spatial map of radial velocity fluctuations in the CGM, and you use this to construct the velocity structure function, which you can see an example of on your right. So you can see that in this particular case for the CGM around a quasar at a redshift 1, that the velocity structure function that's observed, shown by the black points, is actually beautifully consistent with Kolmogorov turbulence, indicated by the orange dashed curve, between spatial scales of roughly 5 to 50 kiloparsecs. These observations are thought to predominantly trace turbulence in the hot gas of the CGM. The next main way that turbulence is now inferred in the CGM is through measurements of non-thermal broadening of quasar absorption lines. So these absorption lines yield non-thermal line widths, which are shown on your right, and separate photoionization modeling of the absorption line profiles yields the densities, temperatures, and sizes of the cool clouds that are responsible for these absorption lines. And so when you compare the distribution of non-thermal line width to cloud size, which are two independently inferred quantities, you see that they are broadly consistent with a power law as expected from turbulence, and broadly consistent with, albeit a large amount of scatter, with the power law expected, again, from Kolmogorov turbulence, but this time over smaller spatial scales from much less than a kiloparsec up to a kiloparsec. And again, these are based on absorption lines that are tracing predominantly metal ions that are produced by cool, roughly 10 to the 4 Kelvin gas in the CGM.
So we can use these quasar results to anchor the turbulent power spectrum at large spatial scales. So here you can see a notional sketch of the fluctuation power spectrum as a function of spatial scale. And so quasars provide us with constraints on velocity fluctuations at the largest spatial scales in this spectrum. Now, because density fluctuations arise as a passive scalar in a turbulent cascade, they are related to the velocity fluctuation spectrum by the Mach number. And so it turns out that the two power spectra of the velocity and density fluctuations, which are shown on the right, can be directly related to each other, again, via the Mach number. So if we assume that the turbulence responsible for these velocity fluctuations observed actually extends all the way down to the scales where turbulence is expected to dissipate, then we would expect a range of observable effects from FRBs. So between roughly the Fresnel scale on the order of a few AU to the sizes of typical clouds, you might expect various refractive effects, which I'll actually largely ignore, but I refer you to Luis's talk later for more discussion of that. Below the Fresnel scale, we would expect various diffractive scattering effects. These include angular broadening, pulse broadening, and diffractive scintillation. And if dissipation of the turbulence occurs at plasma kinetic scales, which would be on the order of hundreds to thousands of kilometers in the CGM, depending on the gas phase, then we would expect that FRBs will be scattered by these density fluctuations, and that in fact the FRB scattering that's observed will be sensitive to density fluctuations going all the way down to those kinetic scales. Now, how does this work? Well, if you remember Robert's talk, he showed us that density fluctuations at the smallest length scales in a medium are responsible for the largest scattering angles and hence the longest time delays. And so if you have significant density fluctuations at spatial scales much smaller than the so-called diffractive scale, then you would expect significant scattered flux in your FRB at time delays greater than the diffractive scattering time that's commonly measured. What do I mean by this? Well, there are two ways of looking at this. Here you can see a cartoon on the left of a scattered image. Typically, we assume that the scattered image is a Gaussian. And so the angular broadening or characteristic scattering angle that you infer is related to the diffractive scale or our diff. But it turns out that if you have density fluctuations going all the way down to kinetic scales, then you would not expect a Gaussian scattered image. Instead, you would expect an extended halo with these long wings in the image. And those wings precisely arise from the density fluctuations at these tiniest spatial scales. If we translate this to the shape of the scattered pulse, then instead of seeing an exponential scattered pulse, we would instead see a pulse with a very extended scattered tail, and the extent of that tail would depend on the inner scale. And so it turns out that in this regime, which we actually expect to be the case in the CGM, where you have density fluctuations below spatial scales equivalent to the diffractive scale, then it turns out that your scattered pulse will have a mean delay that is greater than the 1/e time that's commonly measured. And critically, this mean delay will depend on the dissipation scale, or often referred to it as the inner scale of the turbulence spectrum. So for this reason, we can now actually use the quasar observations to predict the level of scattering in the CGM, again, assuming that the turbulence extends across this huge range of spatial scales, all the way from the fraction of a kiloparsec up to 50 kiloparsecs probed by quasars, all the way down to the thousands of kilometers probed by FRBs. So here you can see a general schematic of the methodology. So we have two different tracers of hot and cool gas turbulence, which I just described. We use the velocity fluctuations to infer the amplitude of the density fluctuation power spectrum, Cn squared. And then we use this to evaluate this composite density fluctuation parameter f tilde, which I'll describe in a moment. And this then gives us a prediction of the scattering timescale. So I've shown a version of this slide, I think, at every single FRB meeting I've ever attended. So I apologize to those of you who keep seeing it. But this time it's a little bit different. So we can relate the mean scattering delay to the underlying density fluctuations via the simple proportionality here. It's related to the observing frequency nu, this geometric leverage factor, G-scat, which depends on where the scattering medium is located along the line of sight, the DM of the scattering medium, the redshift of the scattering medium, and then finally this composite density fluctuation parameter, F tilde. So F tilde is related to both the statistics of density fluctuations in the medium. So this includes the properties of cloudlets, the volume filling factor of those cloudlets, variations in the mean density of the cloudlets, and it depends on the properties of the turbulence cascade. So you can see here in this proportionality that F tilde is directly related to Cn squared, the amplitude of the density fluctuation spectrum, as well as the dissipation scale Li. Okay, so what do we actually predict? So using the quasar results that I described, we can predict both Cn squared and the fluctuation parameter for both hot and cool gas in the CGM. And you can see here on the left that the Cn squared values we infer, this is again the amplitude of the density fluctuation spectrum, it's orders of magnitude smaller than values we typically infer in the ISM from pulsars. When you look at the hot gas and the cool gas, you can actually get up to values that are comparable to what we encounter in the ISM. Similarly, on the right, you can see that the fluctuation parameter behaves in a similar way. One important caveat is that in the cool gas, these values of Cn squared and F tilde are inferred based on properties of turbulence within individual cool clouds. And so these are really local quantities. What do we get for scattering? So here on the left, you can see the distribution of the mean scattering timescale and the scintillation bandwidth in the scattering lens frame for the hot CGM. And then on the right, you have it for the cool CGM. And one of the main things we find is that, unsurprisingly, observations of turbulence in the hot CGM indicate that you would get negligible scattering regardless of if your halo happens to be placed fortuitously along the line of sight with large geometric leverage. By contrast, in the cool CGM, you can actually have detectable scattering, but only in cases where your DM and geometric leverage are large. But if you examine the actual values of the scattering timescales and scintillation bandwidths shown here more closely, you'll see that in practice, these values may actually be indistinguishable from the galactic ISM. Now, another fortuitous thing is that because these quasar observations give you an independent estimate of this composite density fluctuation parameter from the FRBs, you can actually combine the two to place a constraint on the dissipation scale of the turbulence. And so here you can see a comparison between the fluctuation parameters we infer from quasar results relevant to the cool and hot gas compared to two different FRBs that intersect foreground halos. And long story short, we see that the upper limits on F tilde for these two FRBs give us a constraint on the dissipation scale that's comparable to plasma kinetic scales. In future, if you have a really firm constraint on scattering in the CGM, then this could become a much more powerful constraint. Now, it turns out that you don't even need to detect scattering from the CGM in order for that to be informative. So all multipath propagation, whether it's diffractive or refractive, requires that you have density fluctuations at spatial scales much smaller than the so-called multipath scale. Here you can see the multipath scales that we predict as a function of the integrated Cn squared that we infer from quasar results. And one of the things you see is that in cool gas, the multipath scale is on the order of 0.01 to 1 parsecs, which indicates that you would need to have density fluctuations within cool clouds in order to produce scattering. And so if you can say very conclusively that there is no scattering happening along a CGM on your line of sight, then that implies that dissipation, at least for the cool gas, would be at roughly cloud scales. Okay, so here's my brief summary. The main point I want to leave you with is that this is all demonstrative, right? But ideally, we would actually combine quasar and FRB sight lines through an individual galaxy halo. And with sufficient observations, you could then use those two observables in tandem to constrain the amplitude, the spectral index, and the dissipation scale of the turbulence. All of these methods are also applicable in the ISM of FRB host galaxies, which could be readily studied in emission. And if you were confused by anything I said, please come talk to me later or read the paper, which is linked here. Thank you.
Heidi, we have time for a couple questions. Couple questions for Cellular?
Oh, my bad.
Ilya Khrikin here. How many quasar sidelines do you need to actually put constraints on all these parameters? Maybe I missed this. Like in real observations, how many do you need to put side constraints?
Yeah, well, in principle, if you have an FRB and one quasar sightline that happen to be superimposed or very, very close to each other, then that might be enough. But on the other hand, maybe having a large sample of FRBs and a large sample of quasars through one halo, like we have in M31, would be the better way to go. It really depends. So I think, yeah, depending on the sample you have, you could get varying levels of precision in your constraint, basically.
Thanks.
Online.
Sunil, can you unmute yourself and ask your question, please?
Hi, thank you. Sunil here from Northwestern U Chicago. Great talk, Sela. I was just wondering when you mentioned that similar measurements could be made for the ISM. I wonder if you have looked into the velocity structure function for like manga galaxies or something like that and tried to put constraints on the scattering in the ISM.
Yeah, it's a great idea, Sunil, and the short answer is no, I haven't done that yet, but I think it would be really cool to do.
Cool, thanks.
Liam, you can unmute yourself and ask your question?
Hey, Stella, it's Liam from the previous session. Great talk. This seems like a powerful idea. I know you thought a little bit about simulations. Can you speculate on how this could be done in like a zoom in fire simulation where you forward model both the quasars and the FRB scattering?
Yeah, so the short answer is I think we could definitely do this in FIRE. We would probably need to use a subgrid model, and basically all of the analytic expressions that I provide in my work, I think would be the basis for such a subgrid model. Yeah, so I think it's doable.
Awesome. All right, let's get to another round of applause. And next up, I'm going to online.
Yeah.
We have Laura Trevina, who's going to tell us about probing the M31 halo using the dispersion method of FRBs. Laura is online. Amazing.
Hello, everyone. Can you hear me?
Yep, we can hear you. Go ahead and take it away whenever you're ready.
All right, thank you so much. So my name is Lodrick Kahinga. I'm a PhD student at UCSC. And once again, thank you for inviting me for this talk, where I'm gonna talk about essentially just studying the M31 halo or CGM using FRB dispersion. And below some of the main contributors, I work with X and Sunil and Calvin, and both were very essential for this work, and I cannot understate the contribution from the above collaborations, namely F4 and Chime. And the sample actually I was using for this analysis was the Chime FRBs catalog too. And so, I don't think I should even go into this. We've seen a lot of talks from Monday with Sanskriti Das and Matt McQueen and Liam Connor, and Ralph did a very good summary for what this is today. So I won't even go into it, but just as a reminder, it's basically when you're thinking CGM, it's the connecting medium between the ISM and the IGM. And this plot on the right here is just to sort of show all the stuff that's happening in terms of feedback and gas exchange and all these things, all these fun things happening in the CGM, and we would want to understand that. But I will be focusing on basically one question, and the second question is sort of related, where I'm just thinking of what is the baryonic mass inside the CGM? And this, I think, just rolls off part of the strong missing baryons problem that Liam Connor was talking about earlier. And another thing that we sort of want to think about in terms of distribution of baryons is just how many of these baryons are inside the halo? How many does it retain after they fall into the halo? And so this is basically the two questions we set out to sort of think about. And we were especially looking at the M31 halo. And so the M31 halo, as you know, is the Andromeda galaxy. It's the nearest galaxy here. It's an L-star galaxy. It's very similar to the Milky Way. It subtends. It's about 770 kiloparsecs away. It subtends about 30 degrees in the sky, which is fantastic. Because when you're thinking about for example, the CHIME sample or the unlocalized FRBs in CHIME, they have 0.2 degrees, about 0.2 degrees square on average localization. And so when you look at the plot on the left here, this is 0.2, and sort of this is about 30 degrees, and this is all 300 kiloparsecs. And so you can confidently assign what FRBs are going through the halo and what FRBs are not going through the halo, and that's great. And you can get quite a few FRBs going through M31, and we'll talk about that sample later. Another property that you might want to think about is the mass of the halo. And that's about 10 to the 12 solar masses. And so that's great. It's a very Milky Way-like galaxy, maybe a little bit more massive. But yeah, so then how would you essentially do this? So you'd have a sightline. It's going through the M31 halo. You'd have another sightline that's not going through the M31 halo. In our case, we're using FRBs that are not localized, and therefore they have no redshifts. But as Sunil was talking about yesterday, not having redshifts in your FRBs doesn't stop you from doing science, and so that's essentially what we're trying to do here. So we're trying to compare the M31 FRBs, that is FRBs going through the M31 halo, and the ones that are not. And so statistically, the ones going through through M31 should have some excess DM, if you like. And so here's a CHIME sample. Naman Jain did a wonderful job of describing catalog 2 yesterday, or the day before that. And so what I'm just going to mention here is that on this plot, the blue sightlines that the FRBs we're going to be using and the yellow sightlines are excluded. The reasons we're excluding these yellow sightlines that are within the ±5 galactic latitude, as close to the galactic plane, and have a DMISM greater than 100 parsecs per square cube is we want to exclude all the FRBs that are sort of have a high Milky Way contribution. And so once you do that, and basically the black line here is just showing where the Andromeda galaxy would be in galactic coordinates. And so once you do that, then you sort of think about more sort of selection. You want to make a better sample. And so what we do here is something we call a differential experiment, where essentially you want to use the M31 FRBs or the FRBs going through the M31 halo to essentially construct a control sample. How you would do this is you would match FRBs, the M31 FRBs and the non-M31 FRBs, or sightlines that are not going through the halo, and you'd use the M31 FRBs to essentially, you're matching FRBs that have similar galactic latitude and that have similar DM-ISM, or the dispatch major contribution from the ISM. The main reason we're doing this is just to have very similar distributions in terms of Milky Way contributions, such that when you essentially measure any M31 contribution, it should be attributed to just the M31 halo itself, and not some discrepancy between the Milky Way contributions between the two samples. So that's the whole motivation behind making a control sample. And so just speaking of the M31 signal, or rather the M31 contribution, this plot is just overplotted against an MNFW prediction of what would be the DM when you're looking at the halo. And so just to give you an idea of the kind of signal that we are thinking about, and we have maybe 100 parsecs per centimeter cube, sorry, getting ahead of myself. Would have about 100 parsecs sort of centimeter cube sort of contribution there. And so how would you compare these two samples now? You have your M31 FRBs, you have a control sample. The first thing you think about is just going for a case analysis. And so we did that, get a p-value of 0.24. So it's not a statistically significant detection. And so what you'd expect when you look at the plot on the left, you split the M31 FRBs to have like an apparent shift on the CDF towards the right, which is not apparent for the higher DM, but it's kind of apparent for the lower DM, which is where we're expecting most of the DM contribution to be. And so this then prompts you kind of have to think about a weighting scheme. So how much signal does each particular sightline have? And so to think about this, so once again, think about dispersion measure as sort of a proxy for distance, if you like. And so if you have, for example, the red line here is showing just some sightline which have a high DM and so longer. And so if you have an FRB with high DM, a lot of the signal is going to be IGM and maybe DM host and all these things, and a small fraction of it is going to be the M31 contribution. And so essentially a high DM FRB will have a lower signal to noise ratio in terms of M31 dispersion measure contribution. In contrast, if you have a lower DM FRB, like the blue line here, most of the signal is going to be from the M31 halo. And so that then means that you're going to need a weighting scheme, or we apply a weighting scheme that upweights the lower DM and then lower and then gives lower weight to the higher DM FRBs. And so we adapt a weighting scheme that's very similar to the Wu and McQueen. Actually, it's identical to Wu and McQueen paper back in 2023, as shown in the above sort of exponential weighting scheme. And so we went and did this. So essentially what you do is just take a weighted mean of FRBs going through M31 and the control sample, and that should give you some excess DM, if you like, or the M31 contribution, which is these error bars shown here. We wanted to make a DM profile. However, we couldn't. We only could bin it into two regions essentially, and that's because of the data. We could only allow 2 bins, but as you can imagine, with more FRBs, you want to have more bins. But what else can we do? We can also try and constrain using different models. And so the shaded region here is sort of that constraint, which we do. So what we do is we define a goodness of fitness statistics shown in this equation here. And what I want you to think about looking at this equation is just, this is an observed DM, and this is DM predicted from some model. And so once you do, we sort of do, you subtract one from the other. And then if you have your perfect model, this number should be as low as possible. You normalize that to get a chi-square. And so your best model would have the minimum chi-square, essentially. And so you can use that to, if you models, yes.
Lord Rick, you have about 1 minute left.
Okay. If you have different models, you can then constrain your maps. And so actually I'm almost done. And so in conclusion, we have used those DM to constrain the mass. What I want you to sort of also think about, at least if you take the mass constraint as face value, it appears that M31 has retained most of its baryons, but once again, we still have very, very large error bars. So we predict that if you have 20,000 FRBs, you can first of all, you can have 5 radio beams with greater than 95% confidence limit, and you can also do a really good job of constraining the mass. So just lastly, we're going to look out for this paper, probably somewhere towards the end of this month. It's going to be on archive, and I would love questions and to chat. Thank you.
Thanks for a great talk, Lord Rick. Does anyone have any questions? Yes.
Thanks, Lordrick. This is Duncan Lorimer from WVU. I was wondering if there are any significant differences in the sensitivity of chime in the control sample versus the M31 sample. And did you take those into account?
Come again, I'm wondering sensitivity in terms
so the 2 samples are in different parts of the sky, and so presumably there's some difference in the sensitivity of the instrument in those different areas, and that could lead to different DM ranges.
Okay, that's a good question. I guess I hadn't considered that the main motivation, like I said, for the control sample is just to get very similar distributions in terms of Milky Way contributions. But I guess I'll have to think about that. Thank you.
Okay.
Yeah.
Awesome.
All right, let's maybe move the rest of the discussion to Slack. Give Outrigger another round of applause. And next up, we'll have Luis Masrivas, who's going to tell us about scattering in the CGM, refractive scattering in the CGM.
I'll get them. 2 minutes. 2 minutes. Okay, thank you all for being here. Can you hear me all right? Yeah, okay, excellent. So yes, I'm Luis from University of California in Santa Cruz. And we have a paper on archive that I want to talk a little bit about that we did together with Matt McQueen and my boss, Expo Chaska. So let's get to it. So we have heard a lot of CGM during these days, especially today, and tomorrow we will hear a bit more, but I just wanted to re-emphasize. Lordrick just mentioned this, Stella did as well, but let me just say a bit more, or again, about the CGM. So why do we care about the CGM is because where cool stuff happens. So the CGM is the separation between the IGM and the galaxy itself, and it's where cool gas is accreted that will be reused to form stars, and at the same time, these stars produce metals and materials that is re-ejected and enriches the IGN. So if you are interested on galaxy formation and galaxy evolution, you want to understand the circumgalactic medium. And for doing that, we would like to know all the physical processes that are happening in the CGM. And today I'm going to focus on, in particular, on two properties or two parameters, which are the density and the size of the gas clouds in the CGM. And this is because the physical processes that happen in the CGM shape these two, or the values of these two parameters. And on the other hand, or vice versa, if you know the sizes and the densities of your gas in several regions, for example, then you get information about these physical processes. So that's what we are trying to do. Also, we will be looking at extragalactic halos. So as Ilya Trikin and many others have emphasized, and we are starting to see, we should not only care about the host and the Milky Way of the host of the FRB and the Milky Way, but it's also possible that intervening halos contribute to the quantities that we measure, DM, magnetic fields, scattering. So we would like to quantify how much this contribution is. And in particular, if you imagine that these intervening halos contribute a lot to scattering the FRB signal, this signal can be so diffused that maybe we are not seeing some FRBs just because the signal gets very, very scattered. So that could be one possibility. Also, as we heard, especially on Monday from Robert Main, who is a great astronomer and karaoke singer, as we discovered last night, these halos could also impact the scintillation that we observe in the Milky Way. This has been discussed in many papers. For our work, we have been following very closely Dylan's Joe fantastic paper, which also treats this aspect. And this has the name that I would call the two-screen system or the two-screen scenario, depending on the distance between two halos or screens. If they resolve each other, depending on the properties of one and the other, the scintillation of the Milky Way can be suppressed by the other, and so on. This usually happens considering the host on one as one screen and the other being the Milky Way. But what I'm trying to say here is that these intervening halos can act as the host, and they can also impact the scintillation from the Milky Way. Okay, and why refractive scattering? I think Stella just gave a super beautiful talk that took care of most of diffraction here, but I just want to remind that the two parts of scattering that we have in radio scattering in radio are refractive and diffractive regimes, and they are usually separated by the Fresnel scale And this means the size of the scatter of this radiation. When you have scatters or gas clouds or particles that are very small below the Fresnel scale, then you have diffractive effects. If you have clouds that are large, then you observe refractive effects. That corresponds, if you look at refraction, that corresponds to scales of parsecs and kiloparsecs. That's the refractive regime. And that to us is interesting because we can make clear and simple comparisons with observations. It's difficult to have observations of very small scales when you think about observations from gas effects and such. So another cool thing about refraction is that it's very simple, the formalism. So I just wanted to show you 2 or 3 equations here because I think we can all understand how this works. And to me, it's a very clear picture of the science here. So imagine that your medium is empty and you have some clouds of given size and density, and then you have light going through. This ray is hitting 3 clouds here, and then the wave phase of this ray will be advanced. And the advance of this wave will depend on the size of the clouds, how many clouds you hit, and their density. So all the time you can see that I'm playing with the density and the size of these clouds. But you don't only have one ray, you have a wavefront that hits different paths. And because sometimes you hit more or less clouds, what happens is that in the end, you will bend your ray. So this change of direction corresponds to that angle, and that's what we call refractive scattering. So now you can understand that if the light, instead of going straight, is going to take some angle, it's going to take a longer path. So the light that goes in that path is going to arrive later than the one that goes straight. So that results in a time delay, which is one of the quantities when we talk about the scattering. And here you have, again, the dependence with densities and sizes. And another important thing, very important, that I learned also from Dylan's paper is that you have to consider that we need multiple images for this to happen. So by definition, the time delay is the time delay between images that take different directions. So if you only have one image, there is no different directions. So there is no effect. And you can see that there's a strong dependence here on the size of the clouds, meaning that when you have, was this very small or very large? I forgot. Very small or very large clouds, very small, then the number of images that you produce is very small. So this will be a limiting factor for whether or not you will produce scattering, a strong constraint. Okay, let's apply this. So let's imagine now that we have a halo that is 10% fill of these clouds. They are all the same size. They are all the same density for simplicity. And you have the 2 equations here. So let's fill this parameter space. And this is what we see here. First of all, I just want to highlight this range between these vertical lines here. These are the inferred densities that come from quasar spectroscopy, quasar absorption lines. So most of the gas in the CGM tends to be, or is expected to be, between 10 to the minus 2 and a few times 10 to the minus 3 particles per cubic centimeter. So this is what we expect most of the CGM gas. And you can see in the parameter space that big white area on the upper part, and all that white area corresponds to where scattering by this halo cannot produce more than one image. So there is no scattering effect. In other words, all that parameter space does not affect a scintillation, does not impact the FRB signal at all. So in other words, most of the gas in the CGM of this halo does not affect the FRB signal. That's one main takeaway. There are other regions down here where we could have high density. We are going to the right side, so this is high density and quite around 1 parsec size. These dense clouds of gas, these ones could impact a scintillation. We expect this gas to be localized more in the center of the circumgalactic medium, and actually these sizes and these densities correspond to what Jacob found in his paper, that maybe something like a high velocity cloud could be responsible for scattering. This is the type of objects we are talking here. We know these exist in the Milky Way. We don't expect them 100 kiloparsecs, perhaps, but they are close to the center. So these ones could affect the scintillation, meaning that they could suppress a scintillation. So these are my two main takeaways here. But the cool thing, if we care about the dense gas, which we do in the CGM field, we can try to put constraints for this dense gas. In particular, even hitting one single clump, one single cloud of gas with very high density, 1 particle per cubic centimeter, and 0.1 parsec, that is enough to suppress a scintillation from an FRB, say at redshift point something, and at 1 gigaparsec you have one of these clumps, and that would be enough to suppress a scintillation. So then you can wonder whether you can use that to put constraints on this gas. And in particular, this gas in the CGM is usually traced by a metal, or ion, which is the one-time ionized magnesium. So there is a large bibliography or large literature about magnesium-2 gas clouds to explain the CGM. So the idea here is to make connections between FRBs, this dense gas, and then to magnesium. And in particular, we are checking all this with mouse salmons and some others. The idea here is that if we take a large number of FRBs, for example, CHIME catalog 2, and we look at what fraction of these FRBs have suppressed the scintillation, that would give us kind of a limit of what's the probability of hitting one of these clouds in all of these sidelines. So that in turn could give us constraints on this dense gas, the size, the densities. And if we talk about magnesium-2, then we talk about the equivalent width of the absorption lines. And just some preliminary calculations depending on how big these clouds are, the densities, and the equivalent width of the magnesium-2 absorber systems, the large lot of data in the literature. We can see that we expect suppressions that go from a few percent to tenths of percent. But this is just some theoretical calculation. We are waiting for the data. So in summary, refractive scattering, which if it happens is added on top of any possible diffractive scattering that Stella has been mentioning. We would account for both of them. Most of the gas in the CGM seem to not play much of a role for refraction, but the dense clouds that we expect to be closer to the center, if you intersect them, which is not easy, the probability is low, if you hit one of those could contribute and they could impact a scintillation. So when you do calculations of a scattering, please remember about refraction, especially if you expect some dense gas or something, think about it. And if more statistically, using a large population of FRBs, you can think that what fraction of those are non-scintillating, and then try to connect that to, yeah. I lost my line of thought now, but I'm pretty much done. And I don't have any picture of a pet or anything, but I just took some pictures last night that I just wanted to put here, and I'll leave it here. Thank you very much.
Thank you so much, Luis. Any questions? Yes.
$50.
I am curious regarding the N images. Can you go back to the formula? So, what? I'm Barak Zakai from Weizmann. So this N images, yes. It seems to me that you can actually measure it if it's less than 1,000 using the high SNR bursts. Do you find this particular measurement useful? Do you think this is a good thing to do?
Sorry, I missed you said thousands? Or?
I think that if N images is smaller than 1,000, you could actually get an estimate of it from the actual scintillation pattern, from its fluctuations.
Okay.
Do you find this measurement useful?
I would like to know more about this because I have not thought so much about that. So what we think is the more images that might help somewhat or contribute to
the extended tail somewhat, but I think the diffraction is multipath propagation is more responsible for the extended tail. From a scintillation, from the scintillation, you could infer the number of images. That's what you're suggesting.
Yes.
Okay, I would like to know more because I don't know much, but yeah, I would like to hear more about this idea. Thank you.
All right, let's go to Luis again.
Online.
On the line.
Yep. So Aurora, if you could share screen.
Yes, I'll do that. Can you confirm if my audio is okay?
Yep, we can hear you.
Awesome. Can I start?
Yes. Next, I'll just introduce you real quick. We have Swanali Patil, who's going to tell us about a spatial gap in the sky distribution of FRB detections coinciding with galactic plasma overdensities, potentially answering some of the questions that we were all just wondering about. But yes, take it away.
Thank you, Jacob. And thanks the organizers for organizing this virtual mode also so smoothly. I'm Swarali. I'm a PhD candidate at West Virginia University, and I'm going to present about my upcoming paper on the spatial gap that we see in FRB sky distribution in the catalog 2 of CHIME FRB. So FRBs, as we know, are excellent probes of the intervening media and because of their propagation effects. And scatter broadening can smear FRB signals below the detectability thresholds. Like you can see here, there is a crisp FRB coming from an extragalactic source, but as it travels through intervening medium, it gets smeared out. And this effect is especially pronounced at low radio frequencies. And so it's known that we see fewer FRB detections in the galactic plane. It's also postulated that scintillation boosts faint FRBs above the thresholds at higher galactic latitudes, but within the galactic plane, this effect is suppressed because of scattering. So Stella wrote this fantastic paper, Stella and her collaborators, where they defined this galactic scattering zone of avoidance, which is a frequency-dependent region of the sky where enhanced scattering suppresses FRB detectability. And they quantify this really nicely in this plot where they have plotted the signal-to-noise reduction factor as a function of the observing frequency. And as you can see, it is more pronounced in the chime band, which is at lower frequencies. And based on the estimates of DM and scattering timescales from electron density model NE 2001, they postulated the area, the galactic latitudes and longitudes that are spanned by this galactic scattering zone of avoidance. And previous studies of FRB sky distribution have been limited because of fewer FRB detections, and also difficulties in combining data from different instruments because of their differing sensitivities and selection effects. And these studies have been mostly focused on the galactic latitude trends. For example, these two independent studies by Emily Petrov and Sarah. Even in Catalog 1, with a sample of 536 FRBs, Alex Josephy and collaborators found no significant dependence on galactic latitude. However, with CHIME Catalog 2, we have a sample of over 4,500 FRBs. The catalog is coming out soon. And out of these, over 3,600 are unique lines of sight. So that gives us an opportunity to probe these effects along all these unique lines of sights. And this is the largest uniform sample from a single instrument to date. And so what do we see in the Catalog 2 spatial sky distribution? We see this visually striking gap in FRB detections depicted by black dashed lines here. And the white markers are all of the FRB positions in Catalog 2, and the cyan points are FRB sight lines that intersect through H2 regions. I'm going to come back to that later. And we find that this zone of avoidance or detection gap spans between these galactic latitudes and longitudes. And this aligns with the Cygnus X region, which is a dense turbulent star-forming complex within the Milky Way, and it's rich in H2 regions. our total sample of FRBs was 3,165, and it's overlaid on the Fink-Banner H-alpha intensity map. And as you can see, there is you can qualitatively see there is an anti-correlation between the intensity of the H-alpha map and the number of FRBs detected. And here is a zoomed in view of the detection gap. It's roughly circular, centered at those coordinates. And we use triangulation to find the convex polygon that encloses this detection gap, and the area of that was 237 square degrees. And to check whether this is just a mere chance, we use rejection sampling, accepting positions based on the sensitivity and exposure for 1,000 realizations, generating twice the number of FRBs that we see in catalog 2. And we find that this detection gap is extremely highly significant with a very low p-value. And this is a strong evidence against the random chance. There are some other alternative explanations that we test are free absorptions, which is negligible at the chime frequency, misclassified sources from FRBs being missed due to the chime detection pipeline DM cutoff. But that can be ruled out very easily because in this, especially along this line of sight, the bias is in the other direction, meaning DM is heavily underestimated. Pulsars misclassified as FRBs could be a possibility. We do not see any repeat bursts in the current sample that we use for this study, but this can't be conclusively ruled out. We would need separate dedicated studies for that. DM smearing is also not that dominant, but we would need a selection function for updated selection function for catalog 2 to make conclusive statements about that, because we know that even though high DM values are underrepresented in the catalog in chime FRB, those are not rare. So we don't see that as being the main cause behind the detection void. And the diamond, red color diamond that you see here is the only FRB that's been detected in the detection void, and that's the fast FRB from the Galactic Plane Pulsar Snapshot Survey, and that has a DM of approx 2000 parsec per cubic centimeter. Another extremely scattered pulsar that we see in the detection gap is J2022, and that's known to be lying behind an H2 region. And so, based on what we know from catalog 2, even though we don't have an updated selection function, what can we say about the data that we have and the intrinsic properties of the bursts that we have at hand right now? And so, if we plot the scattering timescale and intrinsic burst widths of these bursts, we can draw detectability curves for a fixed value of flux based on the single pulse radiometer equation in this burst width and scattering timescale space. And so we use the fit burst parameters for both of these burst width and scattering timescale, and we use a well-measured scattering timescale cutoff at 0.13 milliseconds. And basically what we are doing here is assuming a hypothetical scenario where all the bursts were to lie behind the detection void. We check if we would still detect them given the foreground effects or not. And on the top panel, you see a cumulative distribution function of the detectable bursts for 2 different fluxes and the probability distributions for 2 different fluxes. Namely, blue is the 90th percentile and orange is the 50th percentile. And what we see from this is the lower limit on the scattering timescale along this line of sight, which is 4.36 milliseconds. And so this was about the Cygnus X line of sight, but in general, are we missing highly scattered lines of sight in our sample? And so what you see here is on the background, the Fink-Banner H-alpha map, and the black contours are the intensity contours logarithmically plotted. And a good laboratory for ionized medium within the galaxy are H2 regions. So we check whether these FRB sight lines pass through H2 regions, and the white circles that you see are the WISE catalog, the H2 regions from WISE catalog. Cyan points are the FRBs that do not intersect through these H2 regions, and line points are the ones that pass through them. Here is the detection gap, and the size of these markers is scaled based on log of their scattering time scales as measured by Fitburst.
So I think you have about a little over a minute left.
Okay, I'll wrap it up. The case statistic of scattering timescales of intersecting and non-intersecting FRBs is not that significant, even though the mean values differ a lot. So we plot this emission measure comparison for all of the CHIME visible sky versus at the FRB locations. And what you see here is the weighted number density. And so we can just, to conclude from this, we can say that there is a FRB deficit at higher emission measures. So FRB sightlines tend to avoid higher emission measures. And I'll leave here my conclusions for you all, and I'll be happy to take any questions here or on Slack. Thank you.
Thank you so much. That was an amazing talk. Any questions? Yeah. Oh man, I don't want to throw it that far.
Thank you. Really beautiful talk, Swarali. This is Stella. I was just wondering, have you considered also trying to do comparisons to other tracers of dense ionized gas like radio recombination line maps? Because these H-alpha maps are inherently limited by dust extinction, particularly for, lines of sight that are integrating across the entire galaxy.
Yeah. We tried looking for some data and couldn't find it in the archives, but that's a really good suggestion, Stella. I think it'll be something super important to try out. Yeah.
Any other questions? Yeah.
Hi, this is Adam Dong from NRAO. I was wondering, so I guess a really cool goal was to probe the material in this cloud. So to do that, one of the easiest ways would be to detect an FRB in this region. Is there any chance of doing it through, for example, imaging? If you integrate over 10 milliseconds or something, and so you don't depend on DM or scattering, you're just integrating the intensity there.
Are you saying with CHIME or?
No, not CHIME. Like, let's say you got VLA visibilities in that region, and you just image it with like fast imaging, like real fast can do, or something like that.
Yeah, I haven't thought about that. We did check if we would see some sort of if we can resolve basically scattering with the CHIME outriggers, but I haven't thought about this. Thanks, Adam. I will write that down.
All right, let's move the rest of the discussion to Slack. Thank Swarali again.
Thank you.
All right, lovely. Finally, we have a lightning talk by our very own local verificator on searching and identifying coherent phase correlations from multipath propagation in FRB baseband data.
Yeah, right.
Zarif, do you want a minute at the end, or?
That's already. Okay. Okay. Hi, my name is Zarif. I'm a PhD student here at McGill, and my primary research interest is working on searching for coherent lensing and trying to develop methods to identify them and applying these search methods to CHIME baseband data. Yeah, so over the past year, we've been developing a simulation tool to model coherent lensing as it propagates through different lenses. This simulation tool works in the Icono limit, which is it's the merging point between geometric optics and wave optics. So it takes
considerations of rays, light rays, but it considers the phase information that gets propagated along with it. And we use the simulation tool to model coherent electric fields as they propagate through multiple lensing scenarios as they make their way to a radio telescope. And so, yeah, as just an examples, we model everything from gravitational lensing to plasma lensing and even multiple screens, such as a 2-screen scattering system that I'm showing here. It's all available as a Python package that should be pretty easy to install. And I do want to highlight that I am going to focus on FRBs, but really this works as modeling the electric field propagation in the iconal limit as long as you have a point source. And so the main focus of this tool has been to try and understand the phase decoherence that can happen, especially when you have a gravitational lens and some scattering along the site. And what we've really been trying to do is use the simulation tool to test and evaluate which lensing systems can maintain this coherence to an observer and what observables can they provide that we might be able to measure this degree of coherence. And so at Chime, we've been using the simulation tools as well as data to develop the methods to search. One of the methods that we primarily employ is that we correlate the complex voltage data in the baseband using a match filter in time for each frequency channel independently. One of the interesting things we found was this first FRB2020-0413B that does seem to show correlation signature, which is shown by the shadowy features on the right-hand side. And so we've been doing a lot of analysis on this event and trying to understand what might cause this. And so here are the main summaries of the findings. The first is we find the signature is only present in the power of the correlation and not in the phase of the correlation, which suggests that it's not entirely a coherent phase phenomenon. When we're analyzing the intensity spectras of these bursts in correlating getting the ACFs for the scintillation and trying to measure a scintillation bandwidth, we find that all these subcomponent bursts seem to have a similar scintillation bandwidth, which really suggests that they're all kind of unresolved, whatever's happening, and they're all getting propagated through a similar scintillation screen. Nonetheless, one of the things that strikes out about this burst is the morphology of it, in that one of the things we notice is that this branching morphology that you see is what leads us to believe that it might be a plasma lens FRB, in that if you have a lensing occurring near a caustic, you can model the frequency time morphology through this manner. But because we don't see the magnification that might be associated with it. So overall, is it lensing? Well, unfortunately, with no coherent phase detection, we cannot claim this is coherent lensing, but there is a correlation present. And what we interpret this correlation signature to be is that in a possible 2-screen lensing system, one of the screens is unresolved and is creating the scintillation, or the scintillation screen is the one that's consistent and has an unresolved point source to the other screen. Of course, without phase coherence, the argument for plasma lensing is only going to be a morphological one. And so we're trying to actively see if we can get a lens morphology fit to this event. And so as a final note, I do want to highlight that with our simulation tool and trying to understand and analyze this event, we're developing the search methods and trying to understand the ways we might be able to detect coherent lensing candidates and identify them in data. And we're hopefully using this to find a gravitational lens event in the future. So stay tuned.
Thank you, Zarif. We have time for one quick question before we move on to the discussion session.
Hey Zarif, it's Lauren from McGill.
I know nothing about lensing, but can one predict how many gravitationally lensed FRBs you should be detecting by time?
It depends on what type of lenses you think there are and
Okay.
what type of so one of the, if you think that lenses are just like stars and whatnot, the chime rate is not enough to see it just yet. And the other one is if you think, you know, compact dark objects might compose of these lenses, then you get into the regime of like how much dark matter is compact objects, and that the rates can change. And I think the most optimistic is like 1 in 1,000.
Thank you.
Thank you all again.
And now we'll transition into the discussion session led by Mawson and who else? Seth. There you go.
Yeah. Then Google Stars. We should activate this after people speak. Okay. All right. Hi, everybody. So this is the final discussion session and it's the final session for today, final discussion session too. And so that'll be on the cosmological applications. And so we've heard a bit about this throughout the course of the week. And we'll have a few questions that we'll dive into, but it seemed prudent to kind of recap a little bit of the context, and so we're all on the same page. And so one of the first kind of questions that we want to address are, you know, how can we use FRBs as cosmological probes beyond the Magnetar relation that is fairly well studied. And so the reason we're interested is that FRBs clearly have demonstrated some power to contribute to cosmological problems. And so we want to see what other parts of the parameter space can we extend into. The reason why we think we can extend this further is that FRBs are pretty potent probes of propagation along the line of sight. And so we think we're really getting like impulse response function of the universe that can tell you a lot about what is going on over cosmological scales. Seems obvious that we can do cosmology. So kind of the big ticket items for things that we might be able to do, there are things like galactic feedback, which we heard from Isabel earlier, where, you know, different strengths of feedback blur or make very discrete the contributions to your DM and how much the scatter in your Magnetar relationship should evolve as a function of redshift, and how this correlates in with kind of known simulations in the power spectrum for some of these fluctuations. The another one is the measuring the expansion velocity of the universe, where your Magnetar relation, the slope of this line that dominates the kind of average expectation, is degenerate between the baryon density and the expansion speed of your universe. And so if you had some estimate of 1, normally we want to estimate the baryon density, but there's no reason that we can't also be simultaneously constraining H0 as well. Similarly, there's an approach to constraining expansion history using gravitational lenses as well. So this is called time delay cosmography. It's done by other teams in the field for kind of a semi-long time now, using multiply imaged quasars. With a variability in your quasar, you track and time the delay between the images, and that's dependent on the Hubble expansion. So similarly, we can time FRBs pretty well, and so we think that maybe this is a potential avenue. That same timing might let you search for gravitational lenses as a way to look for compact dark matter objects. And then finally, you might be able to also probe more complicated distributions of dark matter, where kind of this figure from Geraint Lewis's paper back in 2020, shows this idea where if you have some macroscopic image, like one of the images in your galaxy lens system, if it's microlensed by compact objects that are sub that scale, you might end up with an FRB that shows some gravitationally scattered profile that you might be able to use to constrain the power density, the density of fluctuations on the power spectrum of dark matter. And then finally, one of the other items is reionization. So we're measuring dispersion measure as a function of redshift. If we can really reach out in cosmological distances, we might be able to help constrain at what point the universe goes from ionized to neutral. And so here, at this point, I think that's kind of sufficient context to kick off one of the first questions for how can we use FRBs as cosmological probes other than their Mercator relation? And I took the liberty of screen grabbing a few of Matt Quinn's slides from earlier in the week because they kind of address exactly this topic. Dylan. Yes.
Hello, this is Dylan Zhao from Stanford. I just wanted to give a little bit of context, I guess, because on one of your points you said FRBs have shown some potential for cosmology. I want to push back on the word some, right? The missing baryon problem was one of the major problems, open problems in cosmology, right? And essentially FRBs have solved this problem. I think we are starting off on a more optimistic footing than I think we're giving FRBs credit for a little bit. In fact, I just Googled the missing baryon problem on Wikipedia, there's no mention of FRBs at all on the Wikipedia page, which one could solve. Maybe I could solve it. I don't know. But the point is that, we've already made quite significant progress in cosmology with FRBs. And so there are many great things that we can continue to do, but I just wanted to point out that, there's already, there's reason to think that we could do a lot more than what we've already done. And also I wanted to point out, Stella's talk, if you looked at those plots, we're talking about using scattering to probe inhomogeneities in the CGM down to 1,000 kilometers, right? That's sort of this diffraction scale. That's incredibly tiny, right? No simulation is ever going to simulate down to those scales, right? So I just want to say that, cosmology is interesting, and I think FRBs will be able to do a lot. I don't know if I'm going to throw it across the whole row of people.
Thank you. This is Daniele Michilli from the Laboratory of Astrophysics, Marseille, France. And I'm very interested by the potential of fast radio bursts that are strongly lensed. So I wanted to do some shameless self-promotion, and because me and my group are starting this project called FLAME to try and detect the first examples of fast radio bursts that are strongly lensed with the upcoming CHORD telescope in the next years.
Matt?
It's Matt Dobbs from McGill. Cosmology is cool. And cosmology consists of measuring the fundamental parameters in the universe. And we saw lots of examples of ways to potentially do that throughout the week so far. And then in many cases, we saw that the challenge of mapping our experimental results onto the theoretical expectations is even behind where we are for like how many FRBs we have versus redshift. It's really hard to do things like just map dispersion measure to redshift. And so when we think about doing cosmology with FRBs, I think we should be thinking not just about how we can measure things like the fundamental parameter of the universe, but also about how the astrophysics that we probe will feed back into the simulations to allow other people to measure the fundamental parameters of the universe. So as a key example, one of the things that CHIME does and other 21 centimeter experiments is that we're measuring the baryon acoustic oscillations. And as soon as we get to the fine angular scales, like the third or the fourth peak in the BAO, we're dominated by astrophysics effects that are probed by FRBs as they travel along the line of sight. And there's not much in cosmology today that happens with one probe doing it alone anymore. And we've really been thinking of examples like how can we do X or Y with one probe? If our probes, don't serve to measure something fundamental on their own, they might either constrain the astrophysics on those very, very, very small scales that are like wide open, ask 5 simulators what they think and they get 12 answers, or in cross correlation with other things.
Hi, Kiyo Masui from MIT. I just to follow on, I think one of the pleasant things I've seen in the literature since the last meeting and 6 months ago was this shift from the literature trying to do this alone and say like measure the expansion rate, be supernova 1A, type 1A supernova, to talking about the power spectra in general, right? So these either indirectly through P of DM given Z and mapping that to the power spectra, or these direct measurements of the power spectra through cross correlation analyses. And the nice thing there is that we're now talking the language of large scale structure surveys, right? And can really measure things. If we measure a power spectra, then the weak lensing survey can use those power spectra very kind of natively without using intermediaries of simulations or trying to disentangle that. So I think that the field has really come, in just 6 months has really come from trying to do it alone and trying to measure like the expansion history by itself to move towards what I think is a more symbiotic relationship with the rest of cosmology. Great.
Yeah, I guess I just like to echo Matt McQuinn, University of Washington, some of these sentiments. And for my talk, I was defining cosmology as precision cosmology or dark matter. And I think you guys are going to do some really interesting stuff there. As Kiyo just mentioned, but yeah, there's FRBs are interesting. They're like coming into this like from this weird, different perspective that doesn't look like they a lot different than a lot of these other cosmology surveys. And there are questions that you guys are probing that are super interesting. Missing baryons being one. I mean, I think it's just like in this era where we're constraining things at the couple percent level, like the fact that we don't know where the baryons are in dark matter halos and around them at the order 1 level is like kind of crazy and interesting and totally matters for galaxy formation. And even things like why some galaxies are like not turning red and like not forming stars, and like there are big galaxy formation questions out there that you guys are helping to answer. And then one thing that was mentioned, reionization, which like I think we've seen a lot at this meeting, that there are like some really bright FRBs at higher frequencies that you guys are potentially gonna see that could see at high redshift. Like I guess there's no. It seems like they should be there if the star formation is happening at high redshift. We also don't have really good methods of constraining the reionization history of the universe. Our best measurements are the integrated Thomson scattering optical depth, And there's even like some controversy there that if you like change the Planck value, like yeah, like some of these controversies, like evolving dark energy go away. But I could totally see, like, I think it would be super interesting to have a bunch of high redshift FRBs, either where you're finding the galaxy, or you could even imagine that like once they get high enough redshift, you're just gonna, and these DMs are getting like crazy high, like over 5,000, like during reionization, and could imagine that the host galaxy contribution to the DM is small, but you can bound kind of the total integral of electrons through the universe, because even though you have some host galaxy contribution, like it's giving you an upper bound on on this electron column, and that's constraining the same thing that the CMB is constraining, and I think that's like super interesting. Okay, that's a lot. Sorry.
All right.
Hi, everyone. Calvin here from UC Berkeley. I'm going to disagree that FRBs are unlike anything else. They are actually they're actually very, very similar to weak lensing. So weak lensing measures all the matter. FRB measures all the electrons. So everything you do with weak lensing, you can do with a smaller number of FRBs because of the way the different noise and signal contributions work. But we have a recipe to follow, and that's whatever the weak lensing people are doing. And we should really be looking into that literature.
I think there's a contribution from online as well. Liam, would you like to unmute and say something?
Yeah, just quickly following up on the reionization stuff. It's amazing. Like Manisha talked about this Redshift 2 FRB. The rate, like the brightness of that source at Redshift 6, assuming a flat spectrum, is only 10 times lower, right? And I think DSA 2000 SK would probably detect something like that. Obviously, it depends on like delay time distributions. If FRBs are from old objects, then maybe it'll be hard. But yeah, I think we probably will have a pretty good sample of very high redshift FRBs in the not too distant future. And the question then just becomes, how do you optimally follow them up and ask JWST for 20 sources or whatever?
Kiyomizu, MIT again. Is there actually, and JWST gets redshifts of high redshift galaxies all the time, but those are optically selected and therefore intrinsically, or infrared selected, and therefore intrinsically bright galaxies. If you're FRB selecting galaxies, or any chance, like the average star, average, star formation rate weighted galaxy at redshift 6, is there a chance of getting its redshift even with JW?
It's a good question. I don't know.
I think there's a good chance.
Matt says he thinks there's a good chance with JWST.
So do we have anybody in the audience that thinks that they've got an additional cosmological problem we might be able to contribute to that hasn't been talked about so far?
This is Sachin from McGill. My question is, if we want to probe reionization, we need something like 6,000 plus FRBs from those redshift that range from 6 to 9 or something. And how realistic is that we'll be able to, with the localizations from DSA 2000 or code, actually able to follow up that deep? I mean, like, and find the host, have the host association. Somebody.
That number sounds way bigger than what I recall from Paz Benyamini and Pao and Kumar's paper. Do you mean unlocalized, where you don't know anything about the redshift?
Yeah, they need the redshift information. This is a paper from folks from MPIA Heidelberg. I forgot. Yeah, it's a recent paper, 2024 paper, where they did some simulations, and you need the temperature. Yeah, they have. Yeah, I don't know the I can't explain the details in detail, but.
This is Om Gupta from UT Austin. So you only need order 100 FRBs with Redshift to probe at least to first order how reionization progressed. But you can, if you have a lot of unlocalized FRBs on the order of 10,000, then you can just do with that also. Yeah, but localized, you just need 100.
Hey, Daniele Michele from Marseille, France. So to answer Moson's question, to answer Moson's question about how to use fast radio bursts as probes that have not been published. I don't have a good answer about cosmology, but I think that some more thought could be put into use them as astrophysical probes. For example, in the context of strong lensing, we could get incredible results about the lens itself, as Moson hinted in his slides. And one example is the granularity of dark matter, which is something that many experiments around the world are looking for. And with the small scale that we can probe with fast radio burst, we could start looking into that.
Yeah, I can completely echo that statement. The best part about FRBs for this is that they're by and large the most angularly compact sources that we have, right? And so your lensing is sensitive to the size of that angular source. And so by having these very small sources, you're probing a regime of like clusters mass that is well beyond what other people can do.
Yeah, exactly. And this is just an example. You can, study things in the lens that are way beyond any other probes in terms of angular scale. You could measure single stars in there, study the luminosity function with a resolution that has never been probed before, and whatever source there you may find interesting in small scales.
And so that probably leads fairly well into our our second-ish question, which is like kind of in a sense tied into the first in like highlighting which ways FRBs are actually kind of distinct as probes. What ways can they be competitive with other methods? And I think we've heard a little bit from people in the room about just this, in that FRBs are providing a complementary probe of the kind of things out there in cosmology on small scales that are otherwise unable to be kind of distinguished. And so it seems like we can be pretty handy in this area. Don't know what further comments people had.
I mean, here the obvious one is gravitational lensing. There's just nothing that can compete in this timescale that ever will exist. And so like we need more FRBs so we can find that first one and then go further into it. We need to extend the range out to which we're reliably measuring FRBs so that we have more lenses in the way of the ones we're seeing. And we know exactly how to do this. We know why we have biases there. So that we have a greater chance of seeing gravitational lensed FRBs. That first one's going to be like the most valuable, and then it's going to just build from there exponentially.
Yeah, so we'll go to Liam in a second, but to put a final comment on that, I guess I expect the first one, like breaking the ice in a way that is pretty definitive, I think will convert a lot of people to exactly this domain because it will be really powerful if we can do it as we expect. Yeah, Liam, did you want to?
Actually, if there are other comments on that, then don't let me interrupt because.
No, I think you're free to.
Yeah, I agree. And relatedly, so obviously there's dispersion and scattering, which are really exciting, but then just the coherent nature of FRB. So I would love to hear people's thoughts on like how to practically take seriously this idea of space-based VLBI and measuring the geometry of the universe with repeating FRBs. I feel like only a very small number of people have thought about this carefully. Basically, Matt and this collaborator or student, I'm not sure. But yeah, like how do we find these high frequency repeaters? What is the optimal strategy for mapping those out? They should be kind of local universe-ish. We'll probably detect them at lower frequencies and then just hope that they're broadband. Yeah, what do observers think? What do instrument builders think?
Why do you say we have to see them at lower frequency?
My thinking is just that you kind of want an all sky monitor, or you want something with an enormous field of view, which pushes you to low frequencies. And if you're building an aperture array, then you get lambda squared in collecting area, so you build a burst or a chasm. And even if you're in a dish, at 6 gigahertz, you don't have a lot of field of view. So blindly detecting repeaters is hard.
But I mean, the strategy that's already worked is just like look for more R1s, right? There's like R1 is already in the source list, right? It's discovered. It's you can see it at 8 gigahertz. Those are the, and it's at redshift more than 0.1.
Yeah, that's a good point.
So I mean, like we just rather than like we just keep doing what we're doing and then follow them up at higher frequencies to see if they're there.
Yeah. Okay. So just more L band or 600 megahertz FRBs, and some of them will be broadband.
Yeah. Wait for them to go hyperactive and then follow them up with GBT, right? Or fast or something with a high frequency receiver.
Yeah. I mean, they need to be bright because you only get the geometric mean of the thing that's in space and whatever's big on the ground.
So a fast size ground station is also key here.
Maybe on the moon.
And about the repetition, I think we need to get better to find subsequent repeaters. And I think that for these instruments like DSA 2000 will be a great support because you need a lot of sensitivity and a lot of field of view to observe many sources at once, because no big dish is going to give you hundreds of hours to follow every single fast radio burst. So I think that in this sense, DSA 2000 may really change the field.
But actually, won't Chord be better for this? Chord will find FRBs with like 5-to-1 radio bands. And so you'll just assume, well, if it's 300 to 1500, then of course it's at 3 gigahertz.
Well, I was just thinking about your paper that says that, you want a follow-up telescope that has the highest possible sensitivity with respect to the discovery one. So I just think that DSA 2000 can leverage its very high sensitivity.
Right.
I think Pavan had a point over here.
Hey, Pavan from Swinburne University. So I was just following up on the observer point of view. There are examples of radio telescopes which have been put in space just because they wanted to escape ionosphere for very low frequency observations, and there is precedence for that. So I was just curious, what sort of baselines would you be thinking, and in terms of having an instrument with in orbit or something like that, what is the thinking of having the optimal frequency to be? Because we have seen a couple of hyperactive repeaters showing fairly broadband behavior in S band and L band as well. So yeah, just in terms of the temperature of the room.
I think in terms of baseline length, I don't know why there would be an upper limit per se. I suppose it becomes hard in the interstellar medium with some kind of Helier correction for the changing kind of plasma environment, but probably that will get difficult on short baselines anyway.
I want to go back to a point that I'm not sure if we've explicitly said, but the simple fact that it's really hard to catch the second, third, or fourth image of a lensed FRB means I think you do have to go to some telescope design where you see the whole sky all the time. A coherent all-sky monitor is what we need.
And in terms of that as well, actually, in terms of strategies to be used, if you have, I think there are some domains where this becomes easier, in that if you're looking at one of these galaxy lens systems and you already have from the what you can see from the galaxy some kind of estimate of what the arrival time should be, but not pinned down to a very large accuracy, you might be able to point your instrument in some expected window where you think the burst will arrive. And then as in terms of detecting it, if the coherence is preserved, you should be able to detect these bursts down to a much finer signal to noise ratio by correlating the voltage data for the burst you already observed with the incoming stream to look for the lensed copy. Now, that is a pretty strict requirement for preserved coherence, but not between galaxies, but for stellar mass black hole systems, maybe.
Within your delay. Sorry.
There's a regime where the delay is outside our window, and we could be finding sub-threshold bursts this way, I guess.
Did you want to say more, or?
Just that the time delay time for these small objects is they're still in our beam. You know, we have time crossings that are, you know, up to minutes to hours, and in some cases, the North Celestial Pole all day. But even in the 20-minute zone, the objects that we're talking about, you know, being that size, have delays that already fall within our beam. What we need is more beams, more computing power, so that we don't miss that second flash. And the ones that are, you know, 3 hours or 4 days or 6 years away, I think they just aren't going to maintain the coherence.
Yeah, for galaxy lens fast radio burst, our strategy will be actually to, you know, as Morton said, to predict when the second image will arrive. So with missions like Euclid, you can have a pretty good time window where to look for the second image, and then you can just use telescopes around the world to continuously look at that field. And if you have VLBI, you will see the two images arriving with a separation of about an arc second and about a week delay. Yeah, I think that, you know, with telescopes like CORD and DSA, which have a limited field of view, predicting where the future image will arrive is the only way to actually detect it.
Yeah, seeing it an offset.
And seeing an offset is a smoking gun.
Yeah. And that's easy comparatively.
Vicky Caspi McGill. One thing that, well, you asked a question before, so it is, I'm changing topics a little bit, but you know, what are other potential cosmological applications? And one thing we didn't really hear much about, but I'm not sure why, and maybe it's because actually you can't do it, but magnetic fields in the universe. You know, RMs are very easy to measure with FRBs, and we've heard some talks about trying to model those, but aren't there interesting questions about how magnetic fields are generated in the universe and evolve, and could FRBs not be helpful for that?
I expect the obvious answer is yes, but let's hear from you. Nice.
I mean, I think that the Kiyomasugi, MIT, the argument against that has been that quasars are so much more abundant, and they're like FRBs are less special, and that I can measure RMs from many different types of sources. And there are many types of sources that are much more abundant than FRBs, and with DSA 2000, it's going to be, you know, it's going to be wild how many non-FRB RMs will be available. Now those are those are all from the nuclei of galaxies and stuff like that, right? So maybe there's some special niche why FRBs are better for in some way, but the naive counting sort of says that you should do better with another source.
Jason, I think behind you.
Hi, Ayush Pandey, University of Toronto. You get DMs, right? So you get magnetic field strengths for free. You can trace like magnetic field strengths in spiral galaxies out to whatever redshift you can detect them. Obviously, dealing with the fact that you have to know DMIGM, RM from the host galaxy, and so on. Like you have to be able to constrain those uncertainties, but yeah, you don't get DMs for AGN.
Yeah, Daniele Michele again. On this, I actually have a question. For the IGM, do you expect the net RM to be 0 due to random configurations of magnetic fields along the way? Or do you expect cosmologically some net value in one of the two directions?
I think Brian Gainslow, UC Santa Cruz. I think for the ability that we can actually measure RMs beyond ionosphere and systematic effects, the IGM mean RM should be 0, but the scatter should increase as you go to higher redshifts. So if you have a sufficient number of FRB RMs that are not contaminated by the hosts and at a range of redshifts, then you should be able to see the statistical signature of the IGM.
We have a comment from Liam.
Actually, more of a question, less of a comment. For Brian, so is it the case that like if those cosmic magnetic fields are primordial, not astrophysical, they can kind of have arbitrarily large coherence lengths, and therefore you could actually have non-zero average RMs for some distances?
Yeah, I think that's right. But I think those fields would also produce RMs that are so small that you couldn't measure them. Like there'd be much, I think that they're, from memory, they're less than 1 radian per square meter.
Gotcha, thanks.
Okay, and we might move on to our kind of final question, which Seth was gonna give us the lowdown on. Yeah, sure.
Yeah, so just to give some context, so here I'm showing a plot from the first overview paper, Lin et al. And it does a nice job of displaying the current and future radio telescopes in the space of like field of view and SCFD. And you can see that, in the next few years, we're really going to pass the 10 FRBs per day boundary. And these will all be, well localized FRBs, sub-arc second localizations. So this morning we heard from Lawson on RB Float, which was the first CHIME FRB Outrigger detection across all 3 Outrigger stations. Very soon we'll be seeing order 300 per year, less than 100 milliarc second localizations from CHIME FRB. CHIME FRB sample, we're seeing FRBs primarily from a redshift of around 0.5, but some likely up to 2.0. Burst will soon be detecting FRBs if they haven't yet already, and expect to see 100 per year with arc second localization, more local universe FRBs for which we'll be able to obtain archival redshifts very easily. And then, sort of early 2027, Chord is expected to be full in line, and we're anticipating order 3,000 FRBs per year. These numbers are sort of uncertain at the factor of 2. Although for DSA 2000, I have 3,000 per year. I heard Liam say earlier 25,000 per year, so maybe this is uncertain at the factor of 10. But yeah,
even better localizations due to the wide bandwidth, and sort of pushing to smaller field of view, but deeper, higher redshifts. So I think with CHORD, we expect to detect handfuls of FRBs out to redshift 3.5 or 4. And similarly, DSA 2000 will be even more sensitive and probe even further. And then sort of on the 5-year time scale, we have SKA, which will move in that same direction. So smaller field of view, higher sensitivity, and higher redshift FRBs. But in the next couple of years, we're going to be having 300 well-localized FRBs per year, and then it's rapidly going to expand to almost 10,000. So I think, am I missing any samples? Are there any other samples we should expect in the future? And what are their biases for these different cosmological applications that we just discussed?
Oh, sorry, Adam Dong, NRAO. It's excuse me. I just have a quite naive question. How are those estimates optimistic, on point, or are they pessimistic? Because I don't know about other experiments, but I know CHIME only localizes the brighter ones, right? And 300 means 1 a day or slightly less than 1 a day. So I was just wondering, yeah, how optimistic they are.
I feel like I took this from one of Shion's slides.
Okay.
Can you comment how optimistic this is?
Okay, great. It's pretty realistic. Yeah. So for people online, Shion said it's pretty realistic. Okay. Is it Kelvin?
We should think of something collectively to do with. This is Calvin from UC Berkeley. We should think of something to do with all the FRBs whose hosts are not luminous enough to associate with the bursts, or for those FRBs which are so far that we will never have a hope of doing something. How do we classify those into well-defined subsamples without host information?
Hey, Daniele Michele. I think we may get a hint for that from, for example, the GRB community, right? It's not so different. So what are they doing with those sources? I am not sure, but probably ignore them. I don't know. They do cosmology with them, so they basically, Pesilo is saying, they spend enough telescope time to follow all of them up and localize them. That's what you're saying?
Saying that they're not interested in doing cosmology with the PRBs, so the potential for use of FRBs is higher, right?
Okay, so yes, I'll summarize it. He's saying that they are allowed to ignore them because they're not used for cosmology, whereas we shouldn't. Is there a fair? Okay.
Sorry. I mean, it's Kiyomasui again. It's application dependent, right? Like what there'll be some of these things we just talked about where you care, where you need to catch all of them. I think Shion showed that in her the selection bias things, that for these cross correlation analyses, it's okay if you miss them. And there'll be other things where you care about catching them. Maybe because it's a bias, or maybe just because you don't want to miss an opportunity for when you have small numbers that are really contributing to your constraints. So I don't know if that you can ask that question outside of thinking about a particular application. So I think you develop the proposals for the measurements you want to make, and then you think carefully about what your requirements are for that measurement, and you have to do that measurement by measurement.
Oh, yeah.
Just another question that would be nice to have feedback on. So you see 300 per year with the outriggers, but of course we detect more like 2 or 3 per day with just chime. And so so that means, roughly more than half of chime FRBs, unless we can find a way to localize those two, will not have localizations. And so are they still interesting? I think for finding repeaters, 100%. We definitely we're not going to throw them away, but are there other uses for them?
So I guess like a case study of exactly this is when does some of the ZDM related things. If you're trying to pin down H naught or be it whatever cosmological problem, if you have a well-defined model for how you expect your FRB observations to go, and then you're calibrating that model with FRBs where you have all the information, the redshifts, the dispersion measures, what kind of galaxies they lie in, estimates like that. The unlocalized FRBs they're not no information, right? That's if you have a very large statistical sample, it's still boosting the ability to evaluate your model on reality. You're just marginalizing that value over the redshift axis. And so I think the amount that they contribute to solving a problem is certainly lower than the localized bursts, but there's still value. They're not like trash to be thrown away. It's still useful. I think Andreas had a
Andrea Possenti from INAF, Italy. First of all, I am amazed by these numbers, which of course we all hope to become real in 5 years time scale. As far as the question what to do with this large number of objects, I'm hearing this question since when I started my life in pulsar astronomy, because after the first 100 pulsars, according to some of our colleagues, everything was over. So why bother of discovering more pulsars? And we understood that the larger the population, the more interesting the exotic objects are. And so why not expecting when we will have 100,000 FRBs to have some of these just grazing Sagittarius A star? Or why not expecting to find some of these in very strange environment? And they will teach us a lot of things. So, of course, you cannot invest all the time for following up all of them, but keep on discovering objects, even of the same class, will certainly reward you a lot in the end. This is at least what we learned from pulsar astronomy.
Thank you. Catherine?
Hi, this is Amanda Cook from McGill. So I think I'm just thinking about foreground studies because that's what I do. But I also think that the super precisely localized ones will make the just large statistical sample a lot more interesting. Like I can imagine for the galaxy, if we want to map out like the halo, if I actually had a distribution to pull from to estimate their redshift, to estimate their host DM, then I can really use like the full sky exposure in these thousands of FRBs, but right now we just simply don't have that information. And so like statistical probabilistic statements about what the host and IgM contribution are kind of meaningless. So I think that things like that will be really interesting when we get a better feel for the with the precisely localized FRBs.
Is there a question online? Okay.
Hi, Adam Dong from NRAO. I actually thought Amanda was going to say what I was going to say, because I was just going to point out Amanda's work of constraining the halo and galactic DM contribution, right? Like that's, as we've seen, important for cosmology things. And the non-localized FRBs can give you bounds on the galactic and halo contributions, which would then help with the other things that you can do with the localized ones. That's just my comment.
Liam, do you want to go ahead and unmute?
Sure, thank you. Just a follow-up question for Vicky and Keo and others. I mean, given you've already gotten over the hurdle of permitting and power and infrastructure at these sites, isn't the marginal cost of adding collecting area to the Outriggers kind of low, and therefore you could reclaim all of your detections? Or is it not quite worth it with cord coming and all that?
So I think Matt wanted to say something, but I'm just going to give it to Keo really quick to make a response.
Foundations are infinitely expensive. Foundations. Concrete is so expensive. And steel. Yeah.
Response, it's Matt Dobbs from McGill. Response to Keo, foundations for small dishes are probably a lot cheaper. And we already heard a few days ago that we know how to build a telescope that is completely free from intermittent RFI. That is a larger outrigger. So we should do that. We should build the same scale in the outrigger sites and require consistent triggers between the two. So there can't be an RFI influence. Comment on those ones that don't have redshifts. Gravitationally lensed FRBs are the coolest thing ever. And every one of them is equal no matter what their localization is. We just have to look for that coherent lensing. And so let's keep collecting them all, get more.
Yeah, I guess to circle back to the question that was asked at the beginning of the slide, which is, how should we think about future surveys and especially design with these cosmological questions in line, right? So we heard from Shion that selection effects matter, right? And DM dependent selection effects clearly are the ones that are most relevant for the measurement that I'm most interested in, right? So I think the people that are pushing individual measurements should think about their survey requirements, their sample requirements, and communicate those to the instrument designers, right? So we for that particular measurement, we've discovered that DM dependent selection effects are the ones we care about, and we have to find a way of either designing a search algorithm that doesn't have them or subsampling after detection in a way that doesn't have these DM dependent selection effects, right? For that particular measurement. And if you are pushing some measurement, you should think about what selection effects you care about. And then you should think about, is there a detection method or a detection algorithm or a subsampling method that avoids that systematic error without decimating your sample size, right? So we're just these instruments all are in various stages of development. It's not too late to influence the decisions they make. If you have a measurement that you're pushing, then think about selection effects and think about survey requirements and communicate that, right? Write papers saying, by the way, Cord, please don't have this selection effect and do, but this other one is okay.
I guess on that point, something that we've thought about a little bit for the core design is that coherent dedispersion, doing one correction and changing the baseline DM of your search is kind of free. You could have all the data that's ingested in your pipeline coherently dedispersed to 1,000 and start your search there such that the best DM that you could find would be at 1,000, and then your DM dependent selection effects start to tailor off your distribution either side of 1,000. And so you really could be honing in on a particular window in dispersion space that you're interested in. And currently we pick that window to be DM0. And so kind of it's the wrong answer, and that we should, and so given that we're thinking about these configurable quantities, there's power for nuanced search strategies in the future.
Just to this Vicky from Miguel, just to come back to what Liam asked. So if you you know you would be limited by, so you could increase the area of the outriggers, but you're limited by the sensitivity of chime. But with more computing, you could have more beams and be more sensitive with chime, and then detect more with the outriggers just that way. And it so happens we have a proposal to do that. And so if one of you is the reviewer of that proposal, please keep this in mind.
Yeah, I think we've got like a couple of minutes, so we're basically at time. So I think we've got like a minute or two.
Okay.
It's Matt Dobbs from McGill. As we talk about these future instruments like Chord, we're talking about ways to extend them to do more, and exactly the things that Mawson's talking about, that Vicky's talking about, are choices that we're making because they usually cost extra money. Another question for folks: it seems to be within reach that we could have baseband buffers, sorry, Andre, that are hours long by putting them in new solid state drives instead of RAM. And so imagine you had a telescope, you had Chord, or you had chime. It was looking at a big region of the sky, and the entire astronomical community had up to 2 hours to tell you which few milliseconds to pull out of your baseband buffer. So when DSA 2000 or DSA 110 sees their event that we don't trigger on, they could tell us later and say, hey, grab that. How valuable would that be? The price tag is $590,000, we think, which is like the cheapest VLBI piece of machinery you've ever bought. How valuable is that? And like, why won't someone give us $590,000 extra dollars? Or would you rather have more collecting area on the outriggers so you get a larger fraction of them? Or would you like to have microsecond timing? Or, oh, there was the third one. Oh, or would you like to have the 2 experiments so that you could eliminate local RFI. I think maybe we don't have time to answer that today, but we are talking about our future experiments tomorrow, and people could vote or express opinions on all these ways to spend a tiny, tiny amount of money compared to the projects.
Great. Okay, I think we'll leave it there, I suppose. Thank you for coming along to the discussion session, and
Yeah.